I'm Will Bird. Welcome to, I think it's the 5th annual Mini-Canron and Relational Programming Workshop, co-located at ICFP in Seattle. And I welcome you on behalf of myself and my co-organizer, Nada Amin, who can't be here unfortunately, and the program committee. Thank you for coming, either virtually or in person. And we've got some very interesting papers, research papers, and also at the end of the day, we're going to have a discussion on the future of Mini-Canron and relational programming, which directions might be interesting to go and where we should focus our research and implementation efforts. It's a small community, so having some sense of direction I think is important. Many of the people in the community, even though it's a small community, it is, I think, bigger than it looks in that there are people around the world doing research, especially the group, Dmitry Buchalov's group from St. Petersburg State University has a large group, in addition to people from Indiana University, Dan Friedman's students, of which I'm one. And there are other people who've learned about logic programming and constraint logic programming, relational programming through Mini-Canron and through Jason Heeman's micro-Canron system, for example, through implementing that. So we do have a bigger community than it might look, but it's hard to get everyone together at once because we're in Japan and Russia and all over the world right now. So welcome now and later for people watching recorded YouTube videos. Today we're going to start with a Mini-Canron tutorial. Now, it's a little tricky for me to give Mini-Canron tutorials to an audience like this because I've probably given 500 Mini-Canron tutorials. I'm not sure. I gave one yesterday to someone. And the part that's tricky is that we have some people in the audience who maybe haven't heard of Mini-Canron. And we have other people in the audience who've implemented Mini-Canrons and written PhDs on Mini-Canron. So I think what I'll do is I will give sort of my standard introduction to Mini-Canron. I introduce the language and show some of the interesting things, or at least what I think interesting, that we can do with Mini-Canron, in particular writing an interpreter for a subset of scheme in a relational style, and showing some of the neat tricks that we can do with that. And from that point, I think because we do have an audience here of people who are experienced with Mini-Canron, I think I'll open it up a little bit and try to make it interactive. And so if people would like to talk about aspects of Mini-Canron or want to try implementing something, we could try doing something a little more dynamic because we do have a bunch of people who have expertise in Mini-Canron. So if nothing else, it could become a little more of an open session or a Q&A or talking about aspects of Mini-Canron that maybe you're aware of but haven't had a chance to talk to, between the people in the audience today. We actually have a fair number of papers on Mini-Canron and research projects and implementations and things like that. So I think there's lots of expertise in this room, so we can make it interactive. Okay, without further ado, I've got about an hour, 22 minutes. And so we'll begin with the basics of Mini-Canron and what is Mini-Canron and why might you care about Mini-Canron or relational programming, and then we'll go into the details of how to write Mini-Canron programs. So the first thing I'll point out is that Mini-Canron is usually, although not always, viewed as an embedded language. So in this case, we're using the scheme programming language, which is a variant of Lisp, as the host language. So you can think of Mini-Canron as an extension to the scheme language. Scheme, like most Lisps, has a very powerful macro system that allows you to extend the syntax of the language. So if you have a version of Lisp that doesn't have a for loop, you can add a for loop. If you have a for loop in the language and you don't like the way the for loop works, you can change how the for loop works. So we take advantage of that in Mini-Canron to add syntax to the language, to the scheme language for logic programming, or in particular constraint logic programming. And we'll talk about what that is. But the first thing to understand is the reason I'm starting SheScheme is that we're going to extend SheScheme with some primitives. Now, Scheme is a Lisp, and it is a multi-paradigm programming language, but is often used for functional programming. And if you're not familiar with Scheme, I'll show you just a few examples of Scheme, so you get used to the syntax and to how it works. Here we're in an interactive session of what's called the REPL, the read-eval print loop. And so I can write things like +2, 3, and get back 5. By the way, is this font large enough for people? I can make it larger if you need. Is it okay? All right. You can also sit up. We have some open seats, so if you need to move a little closer, it's possible. Okay. So you can see that in Scheme we have what's called prefix notation. So we have parentheses that denote a procedure application or application, and then in the first position of the application, we have the operation, the function that we're going to call. Okay, so here, if I want to add 2 and 3, I just write left paren plus 2, 3. 3 is an expression that evaluates to the value of 3. It's a self-evaluating expression. The first expression I typed in, left paren plus 2, 3, right paren, that is also an expression that evaluates to the value 5. So in Scheme we have expressions and we have values. There are a few other things that I'm not going to talk about in Scheme, but for our standpoint we can think of expressions and values. Now, what I just showed you isn't really mini-Canron, because in mini-Canron we have to deal with addition in a particularly careful way that in most programming languages you don't have to deal with. Okay, so I'm going to be careful to try to show you things that are purely mini-Canron from now on, but I will show you 1 or 2 more things that will pop up later that are worth showing you. So first of all, we're at the International Conference for Functional Programming, so probably most people here know something about functional programming. Most functional programming languages, traditional functional programming languages that we see here, are based on the lambda calculus, Alonzo Church's lambda calculus, and most functional programming languages and many sort of more traditional mainstream languages such as Java and Python and C++ support something called lambda. So I can write a lambda expression in Scheme like this. So this is saying I am going to create a representation. This is an expression that represents, there's a lambda expression that evaluates to a procedure. Okay, you can think of that as a function. There's a function that takes one argument called x and then adds that argument to itself. And if I evaluate that lambda expression, I get back a procedure, which is an opaque object. I can apply that procedure to, say, a number, the result of adding 3 and 4 by wrapping an extra pair of parens, because parentheses in Scheme mean procedure application, with the exception of something like the lambda form itself. So we have special forms, which is syntax, and otherwise every pair of parentheses means procedure application. So here we have a procedure that will take a single argument and add it to itself, and that will be applied to the value of +3, 4, which should be 7. And sure enough, we get 14 back. Okay. And I'll show you one other thing of Scheme that's important to know. In Scheme, we have lists. And so we can say list 3, 4, 5. Okay, so the list function, when it's called with a number of arguments, will construct a list. And of course, we can have expressions in those argument positions to list. Okay, and we can create a list like this. We can also create a list using quotation. Okay? And a quote turns out to be extremely important in list programming. So quote of any datum is just datum. So quote of the list 3, 4, 5 evaluates the list 3, 4, 5. We'll see this quite a bit in the future. And in particular, notice that there's a big difference between something like plus 3, 4, which evaluates to 7, that expression evaluates to 7, versus quote plus 3, 4, which evaluates to a list plus 3, 4. One other thing that you should know is that to create lists in Scheme, there's a more primitive mechanism than calling list. So in Scheme, there's something called the empty list, which is usually written as the expression quote empty parens. That's the empty list. And then to build up lists, we use something called cons. So I can cons 3 on the quote empty list to get the list 3. And I can cons 2 onto that list to get the list 2, 3, and so forth. If I want to get the first element of a list, I can take the car of that list, car, which sounds like a strange name for an operation. You can think of this as first or head of a list. In some languages are called first or head. Car is a historical name. The history is very interesting. I won't get into it though. So car gives you the first thing in the list. Coulter gives you the rest of the list, the rest of the elements of the list. And I'll just show you one more thing. And so I'm basically giving you a crash course in Scheme. The other thing you should know is that internally inside of Scheme, there's something called pairs. So you can think of these as a memory cell that contains 2 pointers in memory, if you're familiar with pointers in memory. And so we have the car pointer and the Coulter pointer. In this case, the car of the pair is just the concrete value 3, the atomic value 3, and the Coulter is the atomic value 4, but we're allowed to cons up things that are more complicated. So I could say cons 2, 3 onto cons 4, and you can see we have this nested tree-like structure. And so the car pointer is pointing to another pair, which has 2 and 3 as its elements. And I can do things like take the car of that value and get to that 3. And if I want to, I could take the Coulter of that value. And last thing you need to know about Scheme is that you usually won't see these dots in what's called a proper list. So, if I cons 3 onto 4, you see the dots, 3.4. But if I cons 3 onto cons 4 onto the empty list, you don't see the dots. You see 3.4. But I can assure you that the dots are there, they're just hidden. So that's actually 3.4 empty list. So I can just quote that whole expression, and it prints out as the list 3, 4. And the reason the dots are suppressed is that it can get tedious to read dots when you have complicated structures. Okay? So that's it. That's all you need to know about Scheme. We've seen variables in the form of lambda. We've seen application and lambda and procedures, and also quote and lists and pairs. Okay. All right. Any questions so far? Okay. So now I will introduce. So I'll do this a little backwards than how I do it sometimes. I'll introduce the core parts of mini-Canron. Okay. And then we can take a little break and talk about why we've seen this little language and what we might use it for. So notice I'm also not justifying why I'm showing you these operators in Scheme, because most of us here are familiar with functional programming. We understand why there might be a use for lambda and application and so forth. But of course, people who have never seen functional programming are going to be mystified by this. So I'm going to show you a couple of operators that are similar. I mean, this is logic, constraint logic programming. So it's not exactly functional programming, but once again, just like we can have extended lambda calculus, we're going to have a few operators which are useful for constraint logic programming. So I'll introduce those operators and give a couple examples, and then we'll take a step back and talk about why we might use those and how to think about those programs that we can write as opposed to the way you would think about functional programs. Okay, so we're done with Scheme. I'll get rid of Scheme. And I'm going to start Scheme again. So we're back in Scheme, but We're going to pretend we're not in Scheme. I'm just going to load miniKanren. Okay, so I'm using an implementation called Faster miniKanren that was created by Michael Ballantyne, building on prior work from other people, and at this point, other people have also contributed to it. But to load the version in Scheme, I have to do this magic incantation. Okay, so now we have extended the Scheme language with miniKanren. miniKanren has 3 core logical operations. The first and most important logical operation is equal equal, which is a type of equality operator which is implemented using something called the unification algorithm. And you may have heard of the unification algorithm in terms of artificial intelligence research, or maybe in terms of type inference or things like that. Okay, so unification algorithm comes up in many guises. It comes up in automated theorem proving and so forth. Okay, so what does this operation do? Well, it takes 2 arguments. And so the syntax for it is, I can say equal equal T1 and T2. So that's what a use of equal equal looks like. So T1 and T2 are what are called terms. So terms are kind of like values in Scheme. So values we're used to, so things like lists and numbers and booleans and so forth. But we're going to have one other feature, which will be what are called logic variables, a special type of variable, which really is more like a special type of value, can also be part of a term. So we'll see that in a minute. But you can think of, from an analogy, of equal equal as like a form of the equality check in most programming languages. So in a language like most Lisps have an equal question mark operator to tell if 2 values happen to be the same. Equal equal is the metaphorical equivalent in constraint logic programming. Now, I could write something like equal equal 5 5. Now 5 and 5 do have the same value, but instead of saying that equal equal 5 5 is true, like we might in functional programming, we say that equal equal 5 5 succeeds. So instead of talking about true and false, we start talking about succeed and fail. Now, if I run this equal equal 5 5, if I try it out, I don't get back succeed, I get back a procedure. We've already seen a procedure before when we're in Scheme land. A procedure is what we get back from evaluating a lambda expression. So under the hood, I'm sort of leaking something about the implementation of Faster miniKanren. Under the hood, there's some Scheme functions flying around, but we can ignore that. However, because Scheme doesn't know anything about miniKanren, we have to have an interface between functional land and miniKanren land, or if you can think about Scheme land and miniKanren land. Okay, so somehow we have to have a way for Scheme to interact with miniKanren, and the way that is something called run. So run is our interface operation. So I said that there are 3 core logical operations. That's true, and there's also one interface operator or syntax, and that's run. And so run is syntax, a special syntax. It's a macro. And in this case, I'm saying I would like one answer, if it exists. And I have this Q thing, which is what's called a query variable. And then we have the body of the run, which is equal equal 5 5. So one way to think about this is we're asking a question. For what value of Q is it true that 5 is equal to 5? Okay, that's one way to think about this metaphorically or philosophically. For which value of Q is it true that 5 is equal to 5? And the answer is for any value of Q. For any value of Q, that is true. That might sound like a strange question to ask, but as we get into more interesting questions, I think you'll see why we ask these sorts of things. And we get back this baffling answer. We get back a list of length 1 that contains _.0, which is a Scheme symbol. It's a symbol. Okay, what could that possibly mean? What that means is that we have a representation of our query variable q, and this is a representation that q remains unassociated. It doesn't have a value as part of this computation. And in some sense, what that means is that q could represent any value whatsoever. So the answer to our query or question is that q could be any value. And for any value of q, it is true that 5 is equal to 5. Okay. Now, let's ask a slightly different question. Okay, so now we're asking the question, for which values of q is it true that 5 and 6 are the same? And so for which values of q is that true? That 5 and 6 are the same? No values, okay? So we get back the empty list. There are no values of q for which 5 and 6 are the same. It becomes a little more interesting if we involve q in the computation itself. So now we're asking the question, for which values of q is it true that q and 6 are the same? And in this case, obviously, well, when q is 6, then q and 6 are the same. Okay, so these are simple sounding questions. Let's make it a little more interesting. So we could say, how about this? For which values of q are q equal to q? Well, for any value of q. So we get back the answer we saw previously, this _0. All right, let's try to make it a little more interesting. What about this question? For which values of q is it true that q is equal to the list containing q? Now, what should we return in this case? I don't know. In mini-canren, we decide that we return the empty list. We say there is no answer. There is no q, so it's that q is equal to list q. So our version of equal implements what's called the occurs check. So if the variable q that we're unifying with this other term, if the other term contains q, it's not equal to q, but is a structure containing q, then we say there is no answer, because in order to have an answer, q would actually have to be infinite. We would have to have an infinite term or an infinite tree in order for q to be the same as list q. And so we've decided to make that illegal. I should point out in some logic programming or constraint logic programming languages, this decision isn't made because it's expensive to implement. It's expensive to do this check. So in many logic programming languages, they just don't do the check. And then furthermore, so like in Prolog famously doesn't do this check. But in other languages like Prolog 2, they say, oh no, that's okay. It's okay to have infinite terms. Okay. In fact, there's a version of mini-canren that people have played with where you are allowed to have infinite terms. They're called infinite rational terms. And you're allowed to get an answer back. So just like in Scheme, you're allowed to create circular data structures. You're allowed to have a list whose car or cdr points back to the list itself. Okay, so you're allowed to do that in Scheme. You can also be allowed to do that in this logic programming, but we don't make that decision. Okay, so everything you see about mini-canren, if you're thinking of it from a research standpoint, you should also be thinking, for every decision that mini-canren made, what would happen if you did it differently? Okay, so we could make this a different choice, but we've decided, at least in the standard version of mini-canren, to enforce this occurs check. Okay, but it's not the only choice you can make. All right, and then, okay, so let's make this a little more interesting. Let's introduce another one of the 3 logical forms in core mini-canren, which is called fresh. What fresh lets you do is introduce locally lexically scoped logic variables. Now, we've already seen a logic variable. As our query variable q is a logic variable. Here we also are introducing x and y. We are allowed to refer to x and y within the body of the fresh. So one way we could do this is we could say q is equal to the list xy. Now in this case, we are saying that Q has some structure. It is a list of length 2, but we're not saying what's in that list. So if I run that query, I can see that we get one answer back, and that answer is itself a list. So we have a list of answers, contains one list of length 2, and our representation of x, the logic variable x, is _0, and our representation of y is _1. If I make the list a little more complicated, I could put another x in there, and we see that the numbering gives us another 0. And that's because the numbering of the zeros and ones refers to the distinct logic variables that don't have values at the end of the computation. So x has the numbering 0 because it's left to right in terms of the answers. Y has the number 1, and because we have 2 x's in that list, you can see that we have 2 zeros. Now, we also can add more than one equal. So here we have one use of equal or unification, but I could also add another one. And this is a conjunction or an and. So I could say, not only is Q equal to list x, y, x, but we also have the case that x is 5. And so in this case, we can see that our result is a single list where in the x position we see 5 both times. For y, the number has changed. It went from 1 to 0 because we always renumber our answers from 0 to 1 to 3, 2, 3, so forth, from left to right when we have a variable that hasn't had a value associated with it by the end of the computation. And of course, if I wanted to, I could give y a value. Now, I could give y a value like 6, and it would work as you expected. But I could also do something like, say, y has the value of x. Okay? And that might look like an assignment. These might all look like assignments, but they really aren't. They're more general than the sort of assignment or a let binding that you're used to. So first of all, we don't have mutation. So it's more like a let binding in functional programming. But it's not really like a let binding in a way, because we're allowed to reorder these expressions any way we want. And so, and in fact, we don't ever have to give concrete values to x or y or q if we don't want. In this case, we're saying that x and y have the same value, but we're not saying concretely what they are. So we can see that we have a list of one answer, which itself is a list of length 3, and our representations of x and y are all underscored at 0 because even though x and y are all what we call fresh or unassociated logic variables, because we've tied them together by unifying x and y, they get the same number. And if I were to associate with either x or y with a value, say make y is 7, then we would see that same value repeated. Importantly, we can reorder any of these conjuncts, and we can also, within a single call to equal, we can reorder, we can swap those arguments, okay? All right, and the program still has the same meaning, has the same declarative meaning. So this is a form of declarative programming. So we've now seen 2/3 of the logical language and 3/4 of the core language, and we're going to have one more thing that I'm going to show you for the core language, which is the ability, you could think of it as the ability to make choices, but it's not really the way to think about it. It's not so much the ability to make choices as it is the ability to collect multiple answers. So, and that is an operation called cond, which syntactically looks something like McCarthy's cond operation. Okay, it's sort of metaphorically inspired by cond. And so the simplest version I could show would be something like this. All right, so in this case, we have a cond expression. E stands for every. We're going to collect every, or try every clause. And we have one clause where we say Q is 5, and another clause where Q is 6. Now, if I were to hit return, what we see is a list of length 1. In this case, it happens to have a 5 in it. So we got Q is 5. Now I could also ask for more than one answer. So I could say, give me 2 answers. In this case, I get a second answer from the other Kandi clause, which is 6. I could also ask for 10 answers. In this case, there are only 2 answers. It can be annoying to have to guess the number. So if you want all the answers, we have a shorthand, which is just saying run star. You have to be a little careful with run star because you can get infinitely many answers from minikenran. But you also have to be careful by putting, when you put in a concrete number, because it's also possible that there are only 2 answers. And if you ask for 3 answers, either you will get back 3 answers or your program will go in an infinite loop, which we will see. Okay, so that's a way to make choices. And in Kandi, we're allowed to have more than one what's called a goal expression. Goal expressions are Kandis and freshes and equals. You're allowed to have more than one goal expression within the Kandi. So I could do something like, say, x is 5, y is 6 in this one. And then here I could say y is 7. And I could also, within my fresh, because that's a conjunction, I could say q is equal to the list x, y. So in this case, this program, which is starting to get a little more interesting, q is going to be a list of x and y, and we have a choice here. In one case, x is 5 and y is 6. In a totally distinct case, which has nothing to do with the first case at all, y is 7. So if I run this, I will see 2 answers. So I see that q is either associated with the list 5, 6, or it's associated with the list _0, 7. If I wanted to, I could reorder the Kandi clauses. So I could say, okay, I want to swap these 2 clauses, and I get back the same list of answers, but with the answers in a different order. Okay, so you can think of these sort of as a set. You can get a little trouble if you think of it strictly as a set, but if you write your program to be non-overlapping, you can think of the answers sort of as a set. We can also do sort of more aggressive reordering. So we could make the Kandi come first. I can swap the equal calls within an individual Kandi, and my program will still have the same behavior. I might get the answers back in a different order, but I will still get the same answers so long as those answers exist. If I ask for 3 answers or all the answers, and it turns out there are only 2, my program could either give me a list of length 2 or it could go in infinite loop. So those are sort of the choices. One way to think about Kandi is it is a disjunction or an or of conjunctions. So we have 2 choices here for the Kandi, and within each Kandi clause, all of those goal expressions all the goals have to succeed. Okay, so that is the basic logical operators of minikenran. Now you can see that we're inheriting a little bit from Scheme because we do have numeric constants. Okay, so we have 5 and 6. Those are inherited from Scheme, and we're also piggybacking on the fact that Scheme has lexical variables. So this fresh x, y, and the q, those are actually Scheme variables that we're sort of repurposing. We're binding those to our own internal representation of logic variables. Okay, so we are using part of Scheme. And another thing from Scheme that we can use is define. So I will show you sort of the hello world example, which is very common from, this is basically the hello world example of logic programming, which any Prolog programmer will have seen. So here we're reusing define, and we're actually reusing lambda. Okay, so we're saying we're going to define a function called appendo. By convention, we end our relations. This is a definition of a mathematical relation with an O. That's due to Dan Friedman. There's a long story behind that I won't get into, but makes it sounds kind of like Italian or Spanish or something. So this is appendo. And appendo is a relation that takes 3 arguments. So we take 2 lists, L and S, and L plus S, our third argument, is going to be L concatenated with S, or L appended with S. That's going to be their 3 arguments. I think most people here probably have seen append in some functional language, so I'm not going to go over that version right now, but I'll just show you what the mini-cannon version would look like. So we want to have more than one choice. Appendo is going to be recursive. So one thing we have to have is a base case. In the base case, if L is the empty list, then we have to associate some value with L plus S. You can think of this metaphorically as the return value in the functional version. So in this case, I will say that L plus S is equal to S, the second argument coming in. Okay. So that is our base case. Now, this already is a working relational program, and if I wanted to, I can run this. In fact, might as well. Okay, so it's okay to have a cond that only has one clause. So I could say run one q appendo empty list to list ABC to be Q, and then sure enough we get back ABC as the argument, the third argument position. Okay, so we can already start testing things out. Let's go ahead and add the recursive case to complete it. In this case, we're going to need some placeholder variables, so I'm going to introduce a fresh, which I'll fill in a minute. And here we're going to check to see if L is the pair of AD, that's a convention, or it's like first rest, or however you want to call it. So we're going to need 2 logic variables, A and S. If that's the case, then we're going to append D onto S to get some partial result res, and then we're going to associate our output argument, L plus S, with the result of consing the first element of A onto res. Okay, so if you've ever written append in a pattern matching style, this actually is reminiscent. Okay, so probably a little easier to see as pattern matching. Now, if you haven't seen mini-cannon before and you're seeing cond and equal and fresh for the first time, this might look a little bewildering. We've got plenty of tutorials on minicanron.org and books and theses and all sorts of things, videos that describe how to write this sort of program in great detail. I'm not going to talk about that right now. What I really want to do is show you kind of how these programs feel. Okay, but we can see at a high level on the outer part of the program we have a cond, we're making a choice. The first clause isn't recursive, we're just doing these sort of equality constraints. And in the second clause we have this recursion, so we're basically breaking apart L, we're destructuring L, and then we're putting together the results of the recursion with the first element of L, and saying that's the third argument, which you can think of as the output. Okay, so now that I have appendo, I can go back to my run query. Okay, so this should still work, sure enough. I can still append the empty list to ABC, but now we can start doing more interesting things. So I should be able to append AB to DC, okay, and that works the way we would hope. Now, if that were the end of the story, wouldn't be very interesting because these are things we're used to doing with functional programming. However, the part that's interesting is that because we've written appendo as a relation, there's no distinction between the first 2 arguments and the last argument. In functional programming, we have this distinction between inputs and outputs. The whole idea of relational programming is we're erasing that distinction. They're just arguments. It doesn't matter. Okay? Now, in this case, we can say the output should be ABCD. And in this case, we see that our query variable remains unassociated. So this is showing that we have consistency, that appendo of AB, DC, ABC, AB, DC, AB, DC, yeah, is consistent, okay? Now, I could change the answer and throw in an E, we get back the empty list instead of the list containing a reified version of Q. So here you can see that we have the three arguments are not consistent. Okay, it's not that the answer is wrong. You shouldn't think in terms of answers or outputs. You should just say that this relation does not hold. We have a three-place relation. The relation holds when we have AB, DC, AB, DC. And the relation doesn't hold when we have AB, DC, AB, DCE. That relation doesn't hold. So you can think of this in terms of maybe a giant database table or just a giant data table. We're writing down metaphorically every triple, every three lists that go together, where the first two lists appended together are equal to the third list. So you can imagine writing down that table, and in a sense, we're just doing a query over that table. The table just happens to be infinite. So this is sort of like a database lookup. It's just our database is infinite, and because it's infinite, we have to construct the table during computation time. We can't just actually create the full table and look at it up. Now, the more interesting things we can do is we can do what people often refer to as running backwards. So we could say, all right, if we were to append AB to some list Q, which we don't know, and the two appended together should be ABDC, what must that second list be? In this case, we can find out that it's the list DC. We can also go further than that. We can say what two lists, X and Y, appended together will give me ABDC. And here's one answer. So I've asked for one answer with my run one, and I can say the empty list appended to ABDC would give me ABDC. I could also ask for a second answer. So give me two answers, and in this case you can see that the second answer is the list A and list B, DC. And in fact, let's see, there are three answers, great. Four answers, great. Let me just format these. Okay. All right, in fact, there are going to be 5 answers in this case. And sure enough, we get 5 answers back. Now, the interesting thing here is what happens, there are exactly 5 answers. What happens when I ask for 6 answers? One of two things will happen. I will either get back the 5 answers I've already gotten back, or I will get back an infinite loop, which is not coming back at all. Let's see what it is. All right, I think we know the answer now. The answer is infinite loop. There is no 6th answer, and in mini-Canron and in Turing-complete logic programming, constraint logic programming in general, it is, in general, impossible to tell there is no answer from infinite loop, because what mini-Canron is really doing is it's doing a search. It's doing a search to see if it can find any answers. And the search space includes all possible lists. Because there are infinitely many lists, it's possible that the search will just keep looking forever, even if there is no answer. So that's the case we have here. Now, in the particular version of Appendo I wrote, we can do better. And the reason we can do better is that mini-Canron, like most constraint logic programming languages, has sort of an Achilles heel, has a problem. And the problem is that our conjunction, our and, isn't really commutative. I have to put an asterisk when I say that our and or conjunction is commutative. It is true that I can reorder these clauses, and the program has the same declarative meaning. Okay? The program means the same thing as I reorder these goal expressions. However, it means the same thing modulo a certain claim, which is, right way to put it is, if I do a query and I ask for n answers, and there are n answers, I will, in theory, get the n answers back. Now, I might need, giant amounts of memory and time, I might need trillions of years to run the query, but in theory, the query would return. However, if an answer doesn't exist, then one of two things will happen. Either I will get back a smaller number of answers, maybe 0, in a finite time, what's called finite failure, or the program will go in an infinite loop or diverge. And there's no way in general for me to tell those two apart. However, as a general rule, you want to put the recursive calls at the end of the conjunctions. Now, Jason Heeman and Michael Ballantyne, I believe, are working on an optimizing compiler that might be a little smarter about some of these things. Or you can imagine doing a rewriting of your program or whatever, or static analyses or dynamic analyses or whatever, to try to tame this problem a little bit. Okay, certainly this syntactic transformation you can do automatically. The problem is when you have multiple recursive calls, there's no way to put them all last. Okay, you could, and it turns out that depending on the arguments coming in, you might prefer one recursive call ordering versus another recursive call ordering. So that's kind of the bad news. So I may as well tell you the bad news up front. In this case, if I reorder the goals like this, so the recursive call comes last, then I have no problem. So I can do a run star. Everything works beautifully, and so I can fill in the gaps. And in particular, probably the most interesting thing to me isn't really when you're running it backwards, but when you're doing things like this. So I can also write this sort of program. We haven't talked about quasi-quote and unquote, but this is another type of quotation. In Scheme, this is saying I have the list that begins AB, and then the continuation of that list, or the rest of the list, is represented by the logic variable x. It's an unknown. So I could say, if I have a list that begins with AB and has something else in it, maybe, either nothing else, that could be the empty list, in which case the whole list is AB, or it could be arbitrarily long, appended to some list y, and to get A, B, D, C, what would x and y be? What are all the choices? And in this case, there are two choices. There are three choices, actually. Okay. All right, there are three choices. So either x is the empty list and y is list DC, or x is the list D and y is the list C, or x is the list DC and y is the empty list. Okay, so this to me is the most interesting case of all, because you can imagine what's called function inversion. If you just want to run your functions backwards, you could invert the functions, and there are techniques for trying to invert functions. And you would have a version of append running forward, a version of append running backwards. But the interesting thing to me is that here we're not inverting the function. There's no way you could invert the function to get this sort of behavior. Rather, we are allowed to have terms. I said that unification operates on terms. And here you see a term that contains a logic variable, but it's partially ground. Okay, so we're allowed to have terms in any position that contain logic variables, but also have some structure. So to me, this is the interesting part of relational programming that sets it apart from other styles of programming, is that we're allowed to write this sort of thing. So we're allowed to put holes representing unknowns anywhere we want in any arguments at any time, and it still works. And this also means that every problem in Minikanren can be thought of as a synthesis problem. Everything is a program synthesis problem in some sense, okay, if you want to think of it that way. So that is kind of the core of Minikanren. Now, I want to jump from append to sort of our most fun example, which is the classic, now classic relational interpreter. So I am going to, okay, so first of all, yeah, that's fine. So let me load. Actually, I'm going to jump to the full version right now. Okay. Okay, so if you're familiar with functional programming, you've probably seen or likely written an interpreter for a little functional language or for lambda calculus or something like that. So what I've just loaded is an interpreter for a subset of the scheme language. So you can think of this as an extended call by value lambda calculus, if you know what those terms mean. And the way we're going to use this interpreter is by calling the evaluo relation. So if you have an evaluator, normally with your evaluator, you would take an expression, evaluate it to get a value. But here, because we don't have a distinction between inputs and outputs, we just have expressions and values. So if you want to think about it, our evaluo takes an expression and it takes a value, and those are related. So the expression has this value, or that value matches up with that expression. Okay, so that's the way it's going to work. So a simple example of this, if I want to, quote, run it forward, would be something like, let me cons 3, 4. And so you can see that if I evaluate this expression, notice I quoted this. Okay, so this is not being evaluated in Scheme, this is evaluated in miniCanron by the evaluo interpreter. So if I evaluate this cons call, I get back the pair 3.4 as the answer in miniCanron, because I'm writing an interpreter in miniCanron that's a relation. Okay, now the interesting thing here is I can now, in this case, run it backwards. Okay, so we'll start with the running backwards example. So I can go the other way. I could say, if I know the value is 3, 4, what is an expression that evaluates to that value? And if I run it, well, first of all, I can see I can quote 3.4. That's one way to get 3.4. But let me ask for a second answer. And here I can see the expression cons 3, 4. That is an expression that evaluates the 3.4. And I could ask for more. I could say, give me 99 expressions that in a subset of Scheme evaluate to 4. And sure enough, I get some more complicated expressions. So here's one that looks weird. So let me try to understand what this is saying. Oh, well, okay. A lot of these I would never come up with, okay, on my own. So this is saying, I'll rewrite this slightly to make it a little easier to read. This is saying that you can have an application of a variadic lambda, a procedure that takes any number of arguments, basically, is what we're going to end up getting from this lambda expression. Take any number of arguments, ignore them, and then return the value of, quote, 3, 4. And what are the arguments? Well, because list happens to be in the interpreter, list happens to be a nice variable. And so we're getting the variable list that's bound to a procedure that creates lists as 3 arguments being passed into this function. And if I evaluate in Scheme, sure enough, I get 3.4. Okay, so those are the sorts of things where now I'm running the programs backwards. And let me just show you a fun example of how you can push this a little bit, which is if I want to evaluate something more complicated, so I can say, I want to evaluate a more complicated expression. Now this version of the interpreter has LUTREC, so we can write recursive programs. So I can define append. Okay, notice this isn't appendo. This is not miniCanron append. This is, honest to goodness, Scheme append. This is a regular functional programming append. So if I define append the way you would normally define it in a functional language, like that, and then I can, let's see, uh-oh, I think I fat fingered it. Hold on a second. let's try this again. Okay, so I can say the output is Q, and we want a letrec append of lambda ls, and we're going to use an if. If L is empty, then we're going to return S. Otherwise, we're going to cons the first element of L onto the recursive call of the rest of L to S. Okay, and now I can make a call to append. Now I've defined it, and I can say we're going to append AB to CD, and we'll see what we got back. All right, and sure enough, we get A, B, C, D. So what I've done here, it's a little sleight of hand, it's easy to miss it. I've written an interpreter in Minikenran as a pure relation that can interpret a subset of scheme, including recursion and so forth, lists and so forth. So I can just put in scheme code. Okay, in fact, I'll prove it to you. I'm not. If I took that letrec and I just ran it in scheme, I would get the same answer back. Okay, so this literally is just scheme code. So I wrote a standard interpreter for scheme, but I wrote it in Minikenran as a relation. So we can evaluate scheme like normal going forward, but that's not very interesting. So I will take the output, the value that you would expect to get back. And so first of all, we can see that our answer is consistent. If I have append defined with that call, then sure enough, I get back A, B, C, D. But the interesting part is now I can start putting logic variables inside of the append code. So for example, if I put the Q, I have to put a comma Q here, this is all quasi-quoted, but basically now I put in a whole represented as a logic variable, saying this is a value I don't know. Okay, this is an expression I don't know. And if you completed it, if you completed that expression, then under a scheme interpreter, it should give you A, B, C, D. So if I ask for one answer back, then sure enough, I get back the list AB. If I try to get a second answer back, I see something interesting, which confused me and confused Michael Ballantyne the first time we tried this, which is there is indeed a second answer. So the reason there's a second answer is that Q represents an expression that evaluates the list AB. And there are infinitely many expressions. So if I were to do a run star instead of a run 2, this would diverge. Okay? If I wanted to make sure that there was only a unique answer, I could just put a quote in front of the logic variable, and then sure enough, the only answer would be AB. Okay, so this is a very subtle thing, but we can play around with expressions of various sorts, and just like we were playing around with appendo and running it differently, we can run append in scheme. We can treat scheme's append now as a relation, even though it's just normally a function. So through the relational interpreter, we inherit this relational behavior even for functional programs. So function is a way to turn functions, to treat functions as relations, basically. But we can go beyond the standard behavior of appendo style behavior. And instead, we can do things like put the logic variables inside the code for the definition of append. So here I've replaced car of L with Q, and if I run this expression, now I've performed some program synthesis where the system has figured out that if you had car of L in this position, that would give the right behavior to append. Okay. And then I'll show you one last thing. I'll change my color scheme real quick. Okay. So if you take this sort of interpreter and you make it much faster, thanks to Greg Rosenblatt, for example. Then you can put this beautiful Swift GUI that I created on top of it, and you end up with this little tool that we call Barlaman. And you can see in Barlaman we have a skeleton of a program. So if we kind of zoom in there, you can see that we have the outline of a scheme function definition. Okay, we're defining some function, we don't know the name. So whatever you see a comma and a capital letter, that's a logic variable or a hole. So we're defining some unknown function, we don't know the name. We don't know the arguments to the function, we don't know the body to the function. So these, we've got a little bit of a skeleton. If I wanted to, I could fill it out some more. So I could say we have a function called append. So I can type in, I could type in as much as I want, give it more structure, but I don't have to give it really any structure. And now what I can do is test-driven development, okay? But real test-driven development, because I can do something like say, if I append the empty list to the empty list, I should get the empty list, okay? So I can fill in a particular test, the input and the expected value, and then I can see sort of a best guess, okay? So the Barlaman interpreter, relational interpreter, figured out, okay, from that example, it looks like you're trying to define a function called append. It's variadic maybe, who knows? And it's just going to return the empty list because that was the result of the example we gave. Okay, so that's consistent with the example, but that's not really what I'm thinking. So I'll give it another example. So how about A and B should be AB. Okay, now think about it a little more. Okay, so now in order to make that work, say, okay, you're defining append, it takes two arguments, I don't know what the names of the arguments are, and I'm gonna have an if in this case, and we'll have the null test, so it's guessing more of the structure, but you can still see it's over-specializing to AB, for example, and it hasn't figured out the recursion. So let's add another test. There are various ways to do this, but in this case I'm just doing pure example-based programming. So, okay, C appended to D is CD. So at this point, it prevents the over-specialization, and you can see that now we're talking cons and cars. Still hasn't guessed the recursion. So let's give it one more example. So append of EF to GH. Okay, and this one might take a minute. Let's see if it can figure out the recursion. Now, one point in time, I calculated, okay, so it took 14 and a half seconds, and so it figured out the recursion at this point. Now, we still don't have any variable names, so if I wanted to, I could do things like say, actually, I want the variables to be L and S, okay? And so, I could do things like give it specific variable names or hints or things like that. And so now you can see that when it synthesized the program, it used the variable names I specified. Okay. Now, there are a couple of interesting things here to note, I think. So one is we now have a program synthesis system that can slowly do things like synthesize recursive scheme programs by example. And the interesting thing to me about that isn't so much that we have a synthesis program system. There are many synthesis systems today, but it's that we got the synthesis system automatically by just writing an interpreter as a relation. So we just committed ourselves fully to this relational style, and the output is a synthesis system because we can put logic variables anywhere we want. Now, making it fast enough to do this small example took some work. As Kent Divig says, optimization is the art of cheating without being caught. So we had to do a lot of cheating without being caught. So this The tweaked interpreter is still a relation. You can still put logic variables anywhere you want, but we've had to hand code some things to make it faster in cases where we can take advantage of structure. Right now, there's a whole bunch of other work going on by different people in different groups to try to make the systems much faster still. Things like staged evaluation, supercompilation, using types like the O'Canran work from the St. Petersburg group and so forth, to try to be able to reason better about these programs, to be able to make it more efficient, to require less human work to try to tweak it. So I think you see both the promise and the challenges. So the promise is you can write your program as a relation, and you can encode the semantics directly. We have different versions of mini-Canran that support different types of logics and things like nominal logic programming from Andy Pitts' group. So we have alpha Canran. You can implement those sorts of rules like capture avoiding substitution and so forth. And there's higher order mini-Canran now. There's lambda Canran and so forth. And there's lots of work on trying to be clever about efficiency related things. But there's still a lot of work to be done. I'll also say that it took us about 13 years of work to get to the point where we could do this. Okay, and this is a tough road to climb. But if you think about how long it took the notion of lambda to get from lambda calculus in the 1930s into Java, it took something like 70 years from the theoretical work to getting it into Java. So yes, it's taken a while. It will take more time. However, I'm optimistic. If you think of the longer term time scale, I think that's the way the time scale in which some of these things work. Also, more recently, there's been a lot of progress in things like neural guided search or using LLMs to guide search, and sort of the other styles of AI. So this is symbolic AI, sort of traditional search-based symbolic AI and constraint solving. But now we have all sorts of generative AI and neural networks and so forth that work very well. So that's a challenge also, is to tie these sorts of things together. And then there's also lots of other things like, what happens when you tie dependent types to a language like mini-Canran? Because it turns out dependent types and relational programming have a lot of similarities. In both cases, you're sort of encoding this logic, and in full versions, it might even be undecidable. So it feels like that's a similar sort of thing, and in fact, I'm interested in encoding Idris, doing something with Idris, for example, in mini-Canran to see where that goes. Okay, I think we've got about 18 minutes left. I could certainly show more, but I think this is kind of the nice broad overview, and I know that we have people here, maybe people online, who are experienced mini-Canran programmers, or at least have seen probably most or all of this before. And so I'm curious if anyone would like to ask any questions, or say anything in response to this, or propose directions in which this might go, or talk about some experiments that they've made maybe that are a little bit different than what I've shown. Yeah.
So it's very thrilling to see this.
Yes, microphone, please. Yeah. Well.
All right, VC from used to from Indiana University.
Okay, another former. We have in the room at least 3 PhDs under 4 PhDs. Oh, well, a new PhD in training. So yeah, we have four generations of Dan Friedman's mini-Canran students in this room.
So you mentioned there was some fiddling to make this work, this appendal to be generated. And I'm wondering, so this kind of improvement, did you do it on, say, mini-Canran level or a lower level?
Okay. Yeah, so in order to make the Barlaman version of the relational interpreter work, there were 2 things we had to do. So one was we had to extend the language of the interpreter over the very simple interpreter to be able to handle things like append nicely. So that that was more like just writing a nice interpreter and being very, very careful. And we also had to add some new constraints to Minikenran to handle certain things so we could get the shadowing right. And Scheme's kind of a tricky language to handle in some ways because you're allowed to shadow any of the operations and redefine how Lambda works and all that. So we wanted to be able to handle all those aspects. So it required some very careful representation of the programs and introducing some special constraints. We had disk quality constraints, absento constraints, symbolo, numbero constraints that aren't in, for example, the Reason Schemer books. Although maybe we'll be able to put those into another edition. Oh, who knows? But it required some extra constraints. That was part of it. It also required, having a faster version of Minikenran. So we have a very simple version of Minikenran, like the microkenran work. A very nice, simple version of Minikenran. It's easy to implement. But on the other hand, if you really want to do something that's going to take a lot of computational power, you want the fastest implementation you can get. So the faster Minikenran implementation has various optimizations, or at least more efficient data structures for representing substitution and things like that. And then the last part of it was Greg Rosenblatt made a whole bunch of hand tweaks to both the Minikenran language in the search and to the interpreter. And if you haven't looked at the code, so if you look at the, you can find the Barlaman code on GitHub. And if you go into the Barlaman, let's see, Barlaman Coco, Barlaman MK, and RHEL interp, and then if you look at the interp, that SCM, there's a parser up front. But then when you actually get to the real interpreter, you'll notice that, okay, so here's the interpreter. And you can see that there's some weirdnesses here. So first of all, there's a let star. Okay, so Greg is mixing scheme code and Minikenran code. And he's also walking variables, and then he does things like check in the lookup code if the environment is sufficiently ground where you can just call regular scheme lookup, that type of thing. And then also you can see he's got this weird cond $ depth first search, and then he's got these hand tweaks of how much of a priority it should be. And then the other thing that's really important is that when it comes to procedure application is tricky because it turns out that you have to make at least 3 recursive calls for a procedure application. You have to evaluate the operator, the operand, and then the body of the lambda, the closure you get back. So you have to do at least 3 recursive calls, and the order in which you do those recursive calls is dependent, the optimal order is dependent on the groundness of the arguments. So there is no one right way to do it. It's sort of like I was talking about with the append example, where when you have multiple recursive calls, there's no optimal way to do it. So what Greg does is he does a dynamic check on the groundness of the different arguments and then dynamically reorders the recursive calls at runtime to try to get better ordering. But it's not perfect. So that's the sort of thing where hopefully you could do it statically. Hopefully the programmer maybe could give hints. There are a whole bunch of ways that you can imagine trying to solve that problem. This is a partial solution, but it also, you can tell, it requires a lot of low-level hand coding, so it would be good to make that automatic, and also it'd be good to make it static. And also these numbers, Greg basically just made those up and tweaked those by hand. It would be good if we could have maybe machine learning or profiling or things like that to help us generate those sorts of numbers automatically. And also, I could tell, there's work by Nada Men and Michael Ballantyne, for example, on staging the relational interpreters. There's also work by St. Petersburg group on supercompilation and so forth. There's a whole bunch of techniques we're using to try to figure out if we can get better performance. Also, Lisa Zhang and her collaborators have a paper on neural guided search. That's another approach. We've been doing some work with Rob Zinkoff and Michael Ballantyne on using n-gram guided search on a small corpus of scheme code and so forth. So there are a whole bunch of ways that you might go. And we're not using types here that could help. But it's tricky right now. So So Greg did find that there are a couple tweaks that help a lot. The application, the two ones that I understand that have a big impact are checking groundness of the environment to see if you can do a regular scheme lookup instead of lookup-o. That's a huge win. And then the other one is dynamically reordering the recursive calls to application. That's a huge win. So if you could only implement two things, those would probably be the ones to do.
That's really awesome. Thank you. An additional question is, so I have this feeling that anything that is relational is slow. I mean, if you look at that equal, maybe in a functional programming language, it happens instantly, right? But here we are at least doing unification, which is linear or worse. Right?
That's right.
So I'm thinking maybe if we try to move the work from the relational world to the functional world, it'd be faster somehow. And for example, in this particular example of this interpreter, maybe if we move beta and alpha just to, or in higher order unification, so it happens in scheme rather than mini-kernel, maybe it could help.
I think you're right. That's something we seem to have learned, that anything we could do, say in scheme, or whatever host language we have, versus doing it as a relation, we should do that when we can tell we can do it, right? And so that's why Greg uses lookup instead of lookup-o when he can, or you really can use like an assoc or askew or something in scheme, which is, I don't know, 10,000 times faster or something. I mean, it's much, much faster. So the work that Jason and Michael Ballantyne are doing with the optimizing compiler, that I think that's also part of the idea. And also things like, I know Jason, you've looked into removing occurs checks for unification. So occurs check for unification is very expensive. So it's not just the unification itself, it's the occurs check also. And there are times where you can guarantee that the occurs check can't be violated. And also one of the optimizations in faster mini-canron is that in certain cases when you introduce a new fresh variable and then immediately unify it before you hit a cond, you can actually just mutate a cell that contains the value instead of having to extend the substitution and all these other things. So there are times where you can avoid putting things in substitutions. And also we're not garbage collecting our substitutions in terms of we're not doing environment trimming. So once something gets added to the substitution, it never goes away. There are problems like that as well. So I think there's a whole lot we could do, but you're right. The best thing is to just not do something as a relation if it's not absolutely necessary. And if you look at the Mercury language, the Mercury language takes a different approach where you write something as a relation and then it gets compiled to individual functions, like kind of regular functional programming with different modes depending on the arguments. So that's another thing we could do is like if we actually are just running in one direction and we don't have compound terms that contain logic variables in them, then we could do a Mercury approach and we compile to functions that go in different directions. So I think there's a whole lot we could do. I think it's still wide open. Yeah.
Thank you.
Yeah. Thank you.
Hi. Walter Schulze, Go Mini-Canron.
Go Mini-Canron.
Yes, go. I was wondering again about these recursive calls and the order. Like if you have a simple example, maybe just a calculator with plus where you have to go down both sides, right?
Yeah.
And you mentioned this groundness check. What is that?
Okay.
We can take it offline if it's too complicated.
Sure.
That's
Well,
fine.
I will. It's such an important thing. I will try to, kind of show you real quickly.
Yeah, I'm pretty sure it's going to be tough.
Yeah. I mean,
Sorry.
I can lead. I mean, it's not that hard to understand, I think, but it is. It's important here. So, let's see if I can find the app case. If you look through this code, you will find. Okay, here's the closure, same length. I don't know if I'll find it. Let's see. Okay, eval application, here it is. Okay, here's the eval application. So you can see this code is kind of it's not super long, but this isn't just 3 recursive calls. There's a lot more going on, okay? To me, the canonical example, by the way, of the reordering is if you write an interpreter that has to handle cons recursively. Because if you have cons of E1, E2, then you have to evaluate E1, and you have to evaluate E2, and then you have to put the results together. Well, you can put the results together first, but you still have a recursive call on the first argument to cons and the second argument to cons. And I can write very simple examples where the call to cons and the expected output value are such that with one ordering of the recursions, you'll get failure, and another ordering, you'll get an infinite loop when there is no answer. And whichever ordering you pick for the recursion, I can trivially, swap the 2 positions of the input cons expression and the output expected pair that would defeat your ordering. So you either have to figure out a more sophisticated way, to do the conjunction, and there are approaches, by the way. There was work on Andorra Prolog, for example. Andorra Prolog, there was a lot of research on how to do parallel conjunction, or how to evaluate things separately, or do dependency analyses. I mean, so people have done a lot of work on trying to understand this problem and how to try to do better. But there are cases where it's all entangled and it's tricky to make it work. So you can see in this application case. Now, first of all, this is general application where you don't know how many arguments you are. Okay, so it's a little more complicated. But you can imagine already, as soon as you have, some function applied to an argument, you already have 3 recursive calls, it turns out. So here you can see what Greg did versus the standard application. And here he's got let values, he's getting suffixes of the rands. Okay, list split ground. So he's doing an analysis at runtime to find where are the ground values, or the ground expressions. And I think you have to go through this code and maybe talk to Greg Rosenblatt about it as well. But it's a little bit tricky. And the key part is, he can reorder things based on groundness. And part of the problem, though, with this approach, there are a couple of problems. So first of all, there's a lot of overhead because you have to do all these checks at runtime for groundness and walking things and so forth. It's expensive. So you just have overhead. Even if you have the right ordering, you have a lot of overhead. But another problem is, the groundness rules are a little complicated. And one of the things you'll notice with Barlaman is there are times where you can make your program a little more ground. You can add structure, and you would think, oh, this is really going to speed things up. But actually, it slows it down enormously. And the reason is you've changed the groundness of one of the arguments to an application, and now everything's reordered. All the applications are ordered differently. So it's not like this is guaranteeing an optimal ordering. It's more like a heuristic, and it works sometimes, and sometimes it actually does the wrong thing, and it actually makes your program slower. The St. Petersburg group has done a lot of work on trying to use structural recursion properties on the operation, on the arguments, so they can statically guarantee that certain orderings work well and things like that. Peter Lozov in particular has done work on this with Dmitry Buchalov's group. So that's something to look at as well. So if you have types, if you have static knowledge, if you know that you have a primitive recursive relation, things like that, then you can do much better. And in fact, you can do things statically as well. So this is an area where I think we're very naive. We figured out some things work, and we've got this one cool program, which is like the relational interpreter, which is very powerful. So we now know that we can do these things, which I think people hadn't suspected in the past. But trying to make this efficient is going to require, like Edward Commett likes to say, throwing all the computer science at it. We've thrown a tiny bit of computer science at it. We're going to have to throw a lot more at it. Yeah.
Thank you.
Thank you. Okay. I think we have time for one more question, if there are any. Otherwise, I think it's about time for the break and to get ready for the next session. Okay, I think this is a good time in. Thank you very much. So let's see here if I can. I will go ahead and... All right, welcome back, everyone. I'm Will Bird, your host all day long for the 5th Mini Canron and Relational Programming Workshop. We are now into the first of 2 paper sessions. And then hopefully we have people online watching from YouTube, and we have an audience in person, which is great. After years of not having an audience, it's great to have an audience finally. And we have lots of mini Canron expertise in the room, which is great. So we've got 2 papers in this session from people from St. Petersburg State University and also from JetBrains in Hawaii. And the first paper is going to be on K-logic, which is mini Canron and Kotlin. And I believe Dmitry Kosarov from St. Petersburg State University will be presenting. We're having a little bit of a technical issue. We've got the Zoom working. I think we've got the YouTube working. We got a projector working. We got the microphone working, but we have to get them all working together. And they were working together, and now they're not working together. So we're resolving that right now. We got some technical expertise to help us right now. So hopefully that will be resolved in a moment. And so the good news is we do have plenty of time per talk. We've got 45 minutes per talk. And so we should have plenty of time also, I think, for questions. So if you have questions and you're online, please use our Discord room. We've set up Discord. There's a Discord room for ICFP. There's a room for Mini Canron Workshop. And I've set up threads for each paper. So please ask your questions in the Discord thread in the Mini Canron room for this paper, the K-logic Mini Canron and Kotlin paper. And if you have questions in person, we can just hand around this microphone. So Dimitri and everyone else at St. Petersburg State University in Hawaii can hear our questions. So hopefully we've got a team working on resolving the issue. Hopefully we'll be done in a minute. And was it? Oh, they need to share a screen? Okay. All right. Looks like we've got the Zoom working. And you all, Dimitri, you're muted, it looks like. So if you can unmute and share your screen, please. We now see you on the Zoom. All right, Dimitri, still looking to see your desktop, I think. And you're still muted. I should take this moment to point out that for anyone interested in Mini Canron and research, we have a monthly Mini Canron research seminar that's held online each month. And that's currently organized by Kate, who will be presenting or associated with the next paper. So if you want to have the online experience every month with Mini Canron, you can look forward to that. If you're interested, let me know and I'll tell you how to sign up for that. Okay, looks like we got some screen sharing. Looks like the slides are kind of off the screen, though. Oh, okay. So it's starting to... We're getting there. We're very close. Okay, we still can't hear you, though. Yuri, are you presenting?
So
Okay, Yuri is presenting. Okay, my mistake. Yuri Kamenov is right. Okay, so Yuri's presenting. Yuri, you're not on mute, although we're currently not hearing you, and your video is not on. I don't know if you're able to turn your video on. We're working on the audio, I guess, on this side also. Oh, I heard something.
To be more familiar with
Oh, okay. Okay, we can hear you.
with minigun,
Yuri, can you hear us?
so we chose Kotlin as a target language.
I don't think Yuri can hear us.
Okay, we have implemented some key features, mostly
Yeah,
taken from
but also
Kotlin
it's important to
implementation.
be able to hear us, right?
First of all, it contains strong typed logic values and variables. What does it mean?
Yuri, can you hear us?
Yeah.
Sorry to interrupt you. We had some audio technical problems on our end. We couldn't hear you for the first few minutes. I'm afraid I'm going to have to ask you to start over again if that's okay. We do have 45 minutes, so I think it'll be okay. So
Okay.
my apologies for that. We had some problems with the audio.
Oh, okay, that's a problem.
Oh, also, one more request. If it's possible, if you have a video camera or if you're in a location where you can share the video, we can't see you right now. So if you're willing to turn on the video, that'd be great. Okay, great. Okay, thank you, Yuri.
Yeah.
All right, so let me do the intro real quick again. So
Yeah.
we have Yuri Kamenov, part of the very capable team at St. Petersburg State University in Hawaii. Will be teaching us about K-logic, which is miniKanren in Kotlin. So, all right, thank you very much, Yuri, and looking forward to your talk.
Yeah, thank you. Can you hear me right now?
Sorry, say that?
Can you hear me right now?
We can see you. Yes, that's right.
Yeah. Okay.
Like, actually, if you can wait one more second. One more second. We're having a little trouble getting the screen set up exactly right.
Okay.
Okay. I'll let you know when we're ready, okay?
Okay. 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 Let me start.
One second.
Do you hear me well?
Yeah, we can hear you. It's maybe a little quiet.
Okay. Okay.
One moment, please. We're still adjusting. Okay, I think we're ready to go. Let's just do a volume check. Can you just say a sentence real quick, and we'll see if everyone can hear you?
Yeah. Yeah. How does it?
I think it's a little low. Is it possible to increase the volume?
Well, I will try.
Okay. Not quite that much. Can you say one more sentence, please?
Yeah. How can you hear me?
Okay. Yes, I think we can hear you fine now, and we can see your slides. Okay. Thank you very much. And Yuri's going to be presenting on K-logic, miniKanren, and Kotlin. Thank you.
Yeah. Thank you very much. Well, so actually, you have presented my team already. Yes. So, what does logic about? Our topic about? Well, actually, the most popular implementation of minikandran are in functional languages, so like Haskell, OCaml, Clojure, Scala. But most programmers use imperative languages, and one of the widely used language is Java from the JVM platform. Well, according to the JetBrains survey, it is top 5 used programming language. So we would like to make more developers be more familiar with relational programming. So we would like to implement minikandran in imperative language Kotlin that is run on JVM platform, and is, well, let me say, improved version of Java, the more modern version. So we were inspired by OCandran implementation. So we have some key features. Most of them are taken from the OCandran implementation, actually, yeah. So the first one is the most important, as we think. It is strong typing of logic values and variables. Well, what does it mean? The original implementation in Scheme, for example, has dynamic typing, so it allows users to try to unify terms of different types. For example, unifying strings and numbers, or strings and lists. So it could not be successful, and we would like to check it at compile time. Kotlin is a compilable language, so we can try to use it. And we want to store type of the logic term in itself to forbid unifying terms of different types. The second key feature is disequality constraint. It allows us to not only unifying logic terms, but also we can say that logic terms could not be equal. It's very useful in some real applications that we have. So what also do we have? It's mostly about convenient usage. So we have implemented some template logic terms. So mostly logic terms contains no more than 1 or 2 values. Most of them. So we have made some templates that allows to just implement some interfaces, and you have your logic terms very easy. And the last key point is relational event observers. So we have some key events during relational programming, like unifications on terms, disequalities on terms, and some stream operations like bind and lose. So we can observe any of these events and do whatever we want, whatever we pass to these observers. For example, we can just collect number of unifications, maybe interrupt the execution, log it, or process somehow. Okay, well, there are some implementation details. This is how we implement our hierarchy of terms. Each logic term is one of 2 types. It could be either a logic variable that are distinguished by integer index, or it could be a logic term that was defined by user. It could be any of them, like linked lists or pairs or whatever. So it is it contains a lot of generic parameters to support strong typing of them. So as you can see here, if you are a bit familiar with Kotlin syntax, it means that any term could be a type of logic term. So any logic variable could contain only logic values. It's very important, so we cannot unify not logic objects. It's impossible to unify, for example, logic list and just a simple number from the host language. You should use logic wrapper for that. Okay, so how does process of unification look? First of all, we have two terms that we want to unify, and the current unification state that stores the current substitution of the logic variables. So to unify two terms, we need to evoke the first logic term with the current substitution, evoke the second term with the current substitution, and unify these two logic terms. So unify impl is a virtual function defined for the logic variable and for the any custom term. So for unifying variables, we just need to look at the substitution. What does it store? To unify custom logic terms, we need to know what nodes of tree should be unified. So what values that are represented by this logic term should be unified. For example, for unifying logic lists, we need to unify each node of it consequently. It is implemented by a virtual function called subtrees to unify. That should be defined by user. So user can say what fields of the system should be unified. For example, unifying cons means unifying head and unifying the rest. Well, it is stable. Okay. But how does type checking work? There is an example of the appender relation that work on list logic lists. So you can see here that we cannot unify terms of different types. So here variable xy is list, but variable head is just element of this list. So we cannot unify list and just a single element. So here we get a compile time error. Okay, this on this slide we present how does it look in some real applications. This is taken from the client's task definition. Here we define two types of terms. It could be either symbol or sequence. and there are two different type of results. It could be closure and wave. So this is just how does it look. Okay, there are some qubits, some difference with, for example, Ocanton because of different type system in Java and Kotlin and Ocampo. So this is an example of defining a relation that checks that logic list is new or not. We need to put an empty list, unifying an empty list with an argument on the right side of the unifying operator, because type inference could not check that it has the same type as the past argument if we moved it as the first argument. Unfortunately, that's actually, I guess, the main difference between Ocanton implementation and key logic implementation. Also, there are some hidden problems with delaying relations just because of different implementation. In scheme implementation and in some places in Ocanton, they used a lot of macro. But unfortunately or not, we don't not have macro in Kotlin, in Java, and JVM at all. There are no of them. So we need to implement it manually. So in recursive invocations, we need to plan to put some implicit delays to prevent hanging of the execution. Also, there is maybe a little boilerplate in implementing some relations, because we need to define type annotations for creating type variables. According to Ocanton, we don't need to define it because type system can check that we have the same type on the left side and on the right side. But in Kotlin, it's impossible. So we need to manually put, as you can see on the slide, this type annotations like element of list and logic list itself. But yes, in scheme, because it's dynamically typed, and in Ocanton with a different type system, it's redundant. Also, there are some points for the improvement. First of all, we can implement set var-val optimization that is described in faster mini-Canron implementation. I guess all of you are familiar with it. Also, disability constraints are not very well optimized. It could be a bit more lazy calculated. Well, there are also some missed API methods like simple or number, but for now we think they are not very needed. On the slide, you can see some benchmarks between K-logic or Canron and fast mini Canron on some calculations. First of all, it's calculating the power of 5, calculating the logarithm of 245, free, creating 100 clients, 15 clients, and 2 shrines. Well, as you can see, actually, Kotlin works much more slower than the Racket implementation, unfortunately, mostly because of strong typing, as we believe. But unfortunately, it also works a bit slower than Alcantara implementation. But we believe that implementing some improvements that Ivan has mentioned before could help. So our future work also is just we want to find some non-trivial sub-trace methods that could well show our advantage of such implementation, just not traversing the whole value stored in the logic value, but only some of them. For example, we can skip some metadata and so on. And for the more real applications, we want to implement a translator from a Kanban to Keylogic because we have a large code database from a Kanban that could be very useful in some Java applications, in JVM applications in Kotlin. Well, thank you very much. That's the end of the topic. I'm ready to answer your questions.
Thank you, Yuri. Let's thank Yuri for the talk. And questions for Yuri. We have plenty of time. Oh, there's someone, sorry? In the Zoom room? Oh, there's someone waiting in the Zoom room? Oh, that's probably for the next talk. Well, they can wait a minute, I guess. Okay, yes, Wishi.
Hi, it's Weishi. I have a question. First off, very interesting work, and I'm a little bit surprised to see the performance comparison. How come Racket is much faster than say JVM? And also, you mentioned you kind of get rid of some say symbolo constraints like those. So I would imagine if you're running coins, you are actually running fewer constraints than the Racket counterpart, right?
Well, we were a bit surprised by these equations actually, because we believe that our implementation is quite good enough. But also, we didn't profile our applications a lot. So I think there are some key places that could be improved. For example, there are some missing optimizations in implementing conjunction, for example, and in the stream implementations. So we believe that we could achieve at least the same performance as Okanron shows. I don't really think that we can achieve the same performance as in Racket, but we will try.
I think this is the first time that I've heard of the blazing performance of Racket compared to OCaml and the JVM, but we'll take it. Okay. And so this is Racket, not Shea Scheme, right? This is Racket, not Shea Scheme?
Well, our benchmarks were mostly collected by my colleague, Dmitry Kosev. Dmitry, could you just help me asking this question?
Usually Shea Scheme is significantly faster than Racket.
Hello, Will. Can you hear me?
Yes. Dimitri.
This is Racket compiled with the chess scheme backend, recent addition to Racket, compiled to native code, and it is the fastest Racket I could run on my machine.
Okay, great. All right, well, thank you very much. Other questions?
Question about this. My name is Yafan. So my question is, when you use Racket, are you using the faster Karen implementation or just the when you do this benchmark? Yeah.
Yes, it is faster mini-control, yes.
Okay.
Okay, so you haven't implemented the set var val optimization that Michael Ballantyne added to faster mini-Canron, for example. And your substitution representation, how are you representing substitutions? Oh, because you're representing them as objects, but are you doing like the hash table? I think I missed that part. Are you, for your walks, you're not using association lists, are you using hash tables or trees for a fast lookup in the substitution?
We use persistent map
Okay,
for some substitutions. Yeah.
okay. So that should be efficient. All right, thank you. Other questions? Okay, so other than efficiency, what do you think that with the Kotlin type system, if I understand correctly, the Kotlin type system isn't as sophisticated as that of OCaml, is that right? Does Kotlin support Henley-Milner, or is it closer to the Java type system?
Yeah, it has the same type system as Java has, but yes, it's different from the Karen. There no Gary Howard algorithm for checking types, so it's just a bit more different.
Okay. One problem with mini-Canron in Scheme or Racket is that when you get a logic variable back in the reified answer, you can't tell what type that variable might represent unless you explicitly have a constraint on that variable, like a symbolo or numbero, or you use explicit tagging of the type. So it seems like with your type system, you should be able to tell the type that a fresh logic variable in a reified answer would correspond to. Are you able to do that?
Well, actually, the real types are removed in the runtime of execution, but well, if you had made a variable of the particular type, the type checking will allow you to get the resulting type, actually.
Okay.
So, yeah, it's very hard to lose the real type.
Okay, so you're doing something like the type erasure that's happening in OCanron? Is that something similar happens, so you don't actually see the type in the output because they're removed beforehand?
Yeah, in Keylogic, there happens type erasure, yes.
Okay. That would be something I think would be really helpful for mini-Canron programmers if they could somehow see in the reified answer, sort of what the corresponding type is. I think that would be helpful in terms of interpreting. I know that the compiler and runtime system can keep track of the types, but if you're looking at a complicated answer that has reified variables in it, it can be very tricky to keep track of that yourself as a human, and you might misinterpret what the types are on those variables. So that's something I encourage you to think about.
Yeah. Thank you.
Let's see. Any other questions? Okay, one more. I know that at this point we have implementations of mini-Canron or mini-Canron-like languages in many hosts languages. So implementations in OCaml and Kotlin and Go and Scheme and Racket and Python and all sorts of other languages. Um, do you think that that's something like the K logic is better off being embedded in Kotlin, or do you think we should spend more effort trying to do standalone optimizing compilers for Minicanron as more of a standalone language? Is the benefit of Minicanron largely because it's embedded in a host language, and that's you want to combine Kotlin with a little bit of Minicanron, or do you think if we had a standalone Minicanron where we could do all sorts of optimizations and make it much faster, that would be beneficial?
Well, we believe that this implementation in Kotlin could be good enough to be used in all JVM-based projects, such as using Java or Kotlin or Groovy, or even a functional language such as Scala and Clojure, just because it's quite lightweight. Well, like core logic in Clojure is very big library, so it gives a lot of functionality that not all developers need. I believe that this lightweight implementation could be very useful for simple for the developers that are mostly familiar with imperative languages, not with functional languages.
Thank you. If for
And
core log,
I probably answer again this question. I think we should not ask the question in the forum either we should have this, either we should have that. We should have one implementation that takes both best features of two approach and smash them together and have the perfect implementation, which is embedded, but there are possibilities to have some domain-specific optimizations and compilation techniques during the load of relational program. Your question reminded me of the Husky, where we can have in a library specify some API and also specify some rewrite rules which allow compiler to optimize some domain-specific calls of arrow functions using our domain. So in case of Minicanron, probably it is an interesting idea to study this approach and to write relational programs, write down some properties of the relational programs, and later a compiler should be able to somehow rewrite relational applications of relational programs together and optimize something using this human-provided domain-specific knowledge about the domain.
Thank you, Dmitry. Okay, I think I've got probably one more high-level question, which is the biggest library I know of, which is on the JVM, as you've already mentioned, for Minicanron is core.logic, David Nolan's project, and there was a successful startup company called ThreatGrid that based their product on Minicanron and ran Minicanron on a cluster and all these things. And they were sold to Cisco for a lot of money. And the way people in the Clojure community use core.logic is more like a traditional Prolog or maybe also kind of data log. And the people in the Clojure community are very pragmatic. They don't seem to care about relational programming as much. And so they don't care about things like relational interpreters. They think it's funny or interesting, but that's not really why they are interested in a language like Minicanron. It's more that they want to have very practical uses. So do you think in Kotlin, the sort of the non-logical operations like conde and condu and project and the equivalents of cut, all these non-logical things, copy term, do you think it's important to have a library in Kotlin that has all the non-logical operators or extra logical operators, or do you think it's important to stay purely relational?
I just want to say that it's very difficult for common developers to use some libraries that are taken from the another paradigm. For example, we had a project that written in Java and Kotlin. They are mostly imperative languages that was using a library from Scala. And for all my colleagues, it was extremely difficult to use it to debug this library because they are absolutely not familiar with functional languages, functional programming used in Scala. So it's like it's possible to use core.logic in Kotlin and Java, but it will be very difficult for most of the developers to debug it, to understand this code, to understand this functional code. And we believe that the code written in Kotlin will be much more understandable for them, much more simple.
Okay, thank you. Dimitri, do you have any comments?
And also about your purity question, I believe that non-pure constructions in relational language are important because, first of all, they will allow easy hacking and tracing, debugging what is happening during relational search. And secondly, it looks like from our experience, our functional relational codebase, that they will help a lot during connecting relational and functional code with group. And we very often prototype something using Condo. Yes, I think it is called Condo. And later we managed to write a pure relational implementation without it, but to have an ability to hack something with these non-relational operations, it is useful.
Okay, thank you, Dimitri. And let's thank the speakers once again for a very interesting presentation. I look forward to using your implementation. And we have the second paper for the session coming up now. So I think we've got Kate online. Great. Okay. And Kate, can we hear you?
Hello, everyone.
Okay. I think we can hear you.
You can hear me, you can see me.
We can hear you, we can see you, we can see your slides. That's great. Okay. So, so Kate Verbitskaya. Okay, how do you pronounce your last name, Kate?
It's Kate Verbitskaya.
Okay. And Kate's going to be talking about semi-automated direction-driven functional conversion. This is work out of JetBrains research, and I'm looking forward to seeing what Kate has to present. And also, once again, I'll mention that Kate has been organizing this extremely interesting monthly mini-Canron research seminar online. So if that's something you'd be interested in, please let us know, and we're always looking for speakers for that. Okay, Kate, please take it away.
Okay, thank you for the introduction. Let me start. I will be starting this talk, and then Igor will join me for the second half of the talk. So let's start. And my cat is always in my face when I start doing any presentation, so sorry for that. So we all love relational programming because it allows us to express non-determinism. It also guarantees us completeness of search. But what's more important for me, at least, it's that one relation allows us to solve many problems. This is used in this idea of using relational interpreters for search problems. Here we use usually you either already have a relational interpreter which you run then to solve a greater problem, or you can even translate a function. So you just write a interpreter in your favorite functional language, translate it into a mini-Kandron relation, and then you run it in some direction to solve a more complicated problem, such as search or generation or whatever. And here this approach is very nice, but of course it struggles with performance. And the performance is something which we try to improve with our in some of our attempts to do some stuff statically. So when we are talking about directions, we don't usually only limit ourselves with a forward and the backward direction. We always have more. We can actually express almost an infinite number of directions, but we will only talk about the principal directions here when each of the arguments of a relation can be either completely known or input, or it can be completely unknown output, such as a fresh variable. We don't allow any partially known terms, such as this constructor with unknown head. This is not allowed. Otherwise, it's all good. So, for example, for the addition relation, which relates two numbers with its sum, we have 8 possible principal directions, some of which have names, some of which don't. So for example, forward direction can be called addition. The backward direction can be called decomposition. We can also have subtraction when we run it with unknown either x or y. And we have some other notable directions such as predicates and generators. Predicates, they check that 3 values are indeed in this relation, and generators enumerate every possible triple of numbers which are in this relation. Each of these directions basically works as a function. Well, kind of. Some of these directions are indeed functions. They can only produce at most one possible answer given the inputs, such as like addition and subtraction, of course, are functions. They always give us only one possible result. Predicates is also can be viewed as a function which produce some kind of a like Boolean or something like that. But other directions are often relations. And what I mean by relation is that they produce multiple results, multiple answers. They are non-deterministic. But of course, as you probably know, you can express non-determinism in a functional programming language as using some kind of a monad for that or some kind of other technique. For example, like in Haskell, it's very common to use lists to express non-determinism, and we will use streams to express that non-determinism. So basically, what I'm trying to say is that each direction is a function, and it's it would have been really nice to be able to run these functions on their own. Unfortunately, when you run mini-Kandron in any direction, it always comes with an overhead, which we already discussed at length, right? So we have unifications, which are costly, occurs checks, which are even more costly. We have scheduling complexity, which is another big thing which impacts the efficiency. And what we would like to do to get rid of as much overhead as possible. So one person during the talk, which Will gave earlier today, asked how maybe it's possible to combine functions and relational programming language and use relational computations only when it's needed. And this is one of the things which we try to achieve using our functional conversion. So a functional conversion is a process which, given a relation with a principal direction, constructs a functional program that generates the same answers as mini-Kandron would. And here we want to preserve the completeness of the search. Otherwise, it wouldn't be like mini-Kandron in the spirit of mini-Kandron. And here we always assume that both inputs and outputs are ground. So why it's important, why we can expect outputs to be ground. It's because we usually, when we interact with minicanron from the functional world, we don't even know how to deal with fresh variables, right? It's something which is foreign to the functional program. So in doing our functional conversion, we want to produce ground results for each output which the user expects from us. And let me start by introducing several examples which demonstrate functional conversion, which illustrated, and then I will talk about how it's done, and Igor will talk also about how it's done. So here at the slide we have a addition relation implementation. It works over piano numbers representation. It examines the value of x, and we know that if x is 0, then the sum of x and y is z, and if x is not 0, then we can do the recursive call, and then we just add a successor to the z to get the result out of that. This is one of the implementation of this addition relation. Of course, it can be different. So let's consider the forward direction of this relation, this function which sums two numbers together. We usually use this notation of using i's in place of ground variables known as inputs, and o's for the output variables. So add IIO works as a forward direction for the add-do relation. Here we know x and y, and if we know x, we know that these two conditions, these conti branches, they are disjunct by x. So it's based on the value of x, either the first conti branch or the second conti branch can hold, otherwise, and the other would fail. So it's natural to translate that into a pattern match. We do the pattern match on x, and then we consider the rest of the conjuncts within these conti branches. In the first conti branch, we see that the result z is the same as y, so we can return y as a result in this pattern match branch. If x is a positive number, then we know that after this pattern match, we know the value of x prime, x1. So if you know x1 and y, we see that this add-do relation works in the forward direction. We can call it to get the number, the value for z1, and that value of z1 with another successor constructor will produce us the result for the whole call. So we do the call, the corresponding function for this direction with x1 and y, and then we add the successor on top of that to get the result. It's very easy when we talk about forward directions, but of course it's not that simple. So for example, if we consider the backward direction, when we only know the last argument, we cannot say that these two conti branches are disjunct based on z, because z is indeed a positive number in the second branch, but we don't know anything in the first branch. So in this particular case, we need to produce answers for both of the branches and then combine them together. And as I already said, we can express non-determinism differently. And the most natural solution which we can when we are working on minicanron, on relational programming, is using streams, which is one of the basic structure which which holds all the substitutions, which holds all of the answers. And stream is nice because its concatenation, it's a monad which has this bind operator, which allows us to express conjunction, and it also has m+ operator. M+ concatenates streams, and with binds, it makes sure that streams are interleaved. So we never have this problem which prologues usually have, that you start to explore the search space somehow wrongly, and then you get you never get any new results. So to make sure that we still have completeness of search, we use streams to represent answers from each of the Kandi branches. So let's consider these branches. The first branch generates us a singleton stream of answers. So it's only gives us one possible result when x is 0 and y has the same value as z. So to construct a singleton stream, we use return, which creates this stream of one particular tuple. And the second Kandi branch, it starts as a pattern match because we know that z is always a positive number. So if z is 0, we return an empty stream. This is like a failure. It can never happen that we got in this second Kandi branch and z is 0. But if z is not 0, then we proceed to examining other conjuncts, and we can run the addition in the corresponding direction. We get the x1 and 0 and y results, and then use the constructor to construct the resulting tuple here. And I've been using Haskell's do notation here, which is like a syntactic sugar for binds. Binds are one of the basic stream operations, and returns just create singleton streams, and empty streams just express the failure here. So I hope this is readable, this Haskell notation. If not, just ask me a question. And one other notable thing here is that I reordered conjuncts while I was doing this functional conversion. I don't know if you've noticed, but I did. So in this conjunction, I first used the last unification, then I used the call, and then I used the first conjunct to get my result. And this order of conjuncts is something which we have to figure out during the conversion, and I'll try to talk about it a little bit more later. One other complication which can arise is that in some directions, we are left with values with variables which are unified with no value. They are not unified with any value. For example, when we only know the first argument for the addition, the first disjunct here, the first Kandi branch, it unifies y with z, but we don't know either the value of y or the value of z. In this particular case, Mini-Kandran would just return a fresh logical variable, but we decided that it's not okay to do so, so we use generators. A generator is a stream of all possible values which a variable can take. And generators is something which we leave to users to provide, but the only thing which matters is that it's supposed to be a stream, because otherwise we would not be possible to do the completeness of search, to guarantee the completeness of search again. And everything else is in the translation of this particular direction is mostly the same as the previous two examples. So, all right. Let me proceed to doing the conversion scheme, to explaining the conversion scheme itself. So we have three steps: normalization, which is like a helper step, mode analysis, and the functional conversion. So normalization is just a way to make a Mini-Kandran goal to be a little bit less complicated for the steps ahead. We limit our terms to be either a variable or a constructor applied to a list of distinct variables. We disallow constructors within constructors, we disallow repeating variables here. And it is a simple syntactic transformation to get rid of these kind of terms. They are translated into a conjunction of corresponding unifications of corresponding variables. When it comes to goals, we have a little bit more restrictions. So first of all, we only allow disjunctions on the top level. So we can see that we can think of it as a conD on top. Every relation starts with a conD. And then we have conD branches, which are made out of non-empty conjunctions. And each conjunct is either a flat unification or flat curl. Flat here means that we have all the variables distinct. We only use variables. And unification unifies a variable with a flat term. So we only have constructors on the right-hand side of the unification. After we've done all of this normalization, then comes the hard part of actually doing the conversion. We start by this mode analysis. The prime goal of mode analysis is to determine an order of conjunctions. The order of conjuncts base goals within conjunction in such a way that it makes sense. And what makes sense is a complicated thing here. Let me just walk you through a couple of definitions first. So each variable in each term can be either ground or free. Ground term does not contain any fresh variables, any logic variables. It can only be a term such as this example here, a list of two numbers, 0 and 1, and we cannot have any logic variables inside of it. Free variable is a fresh variable, doesn't have any constructors in it. And once something becomes a ground term, it always stays ground in the later conjuncts. And this is the idea which helps us to order conjuncts more or less in such a way that they make sense. So this groundness or freeness, it's called in the instantiation of a variable. Of course, there are more complicated instantiations, but we only limit ourselves with these two for now. Mode of a variable explained is a mapping between its instantiation before and after some base goal has been executed. So we have two modes, I and O, which we've already seen. And I means that something has been ground before and it's still ground now. A mode O means that something has been free. We had no idea what the value of that variable is, and then it became ground. And this idea, of course, is not new. It's used extensively in the functional logic community. Mercury, for example, uses more complicated modes. But our job was to limit ourselves as much as possible to get as best result as possible through our conversion. Because I still believe that we don't really need to write a separate compilator or translator for minikandron. We have to try to do it in the embedded way. And to do so, we need to make it simpler. So the goal of mode inference or mode analysis is to assign modes to every variable and make sure that they are consistent. So no ground variable becomes free. We have these four possible ways the unification can be moded. So we can assignments, where we have one output variable at one of the sides of the unification, and the other side is input or completely known. It can be seen as a regular assignment in a regular programming language. There are these guards, where we have ground terms on both sides of unification. In this case, it works just like an equality check. The more complicated ones are matches and generators. Matches is when we know a variable and we try to decompose it into a set of into a term. So on the right-hand side, we can have a term which contains ground and free variables. So at least one free variable is at the right-hand side. And generators are the worst out of these moded unification types, where we have output variable on the left-hand side and a term which contains output variables on the right-hand side. So let's talk about how inference work. We start by initialization. Initialization just puts input mode, associates it with input variables, output mode with output variables, and this question mark mode with all other variables. The question mark mode is maps a free instantiation into a unknown instantiation, which is supposed to become ground after we have done our inference. To do the mod inference, we start by examining a disjunction. To do so, we examine each of the candidate branches separately because they never interact by variables, so it's safe to do them each on its own. When we have a unification, we just propagate the groundless information. So we knew that, for example, here we knew that X is input on the left-hand side of the unification, and we have the question mark mode on the right-hand side, which means that X1 has been free before this unification, but we know that it can become ground after it's done because we know the value for X. So this unification after mod inference becomes this unification where we have input on the left-hand side and the output on the right-hand side. The same goes for other combinations of different variables. The most complicated part of mod inference is treating of conjunction. Here, as I've already said, we have to reorder conjuncts in such a way that it still makes sense, and we also try to not introduce any more inefficiency in the system. We try to instead reduce it. So each conjunct can be seen as one of these 6 types. One of which is guards. Guards is the safest conjunct to execute because it can only trim our search space. It can either fail or succeed, and when it succeeds, it doesn't introduce any new variables, it doesn't do anything. It just succeeds with the check mark. It doesn't introduce any variables into our search space. So whenever we see a guard inside of conjunction, we can pop it right away, put it the first in our conversion, and proceed with other conjunctions. Then the safest 2 out of the rest types are assignments and matches. Then they don't. They can also fail during. They can fail and trim the search space, but they don't really make a lot of computations when they are processed, right? Assignments don't even introduce variables. Matches introduce variables, but they don't do any associated evaluation during that. The 3 remaining types of conjuncts are worse, and the worst of them is the call with all 3 arguments. It is the worst possible way to run a relation, a control relation, because it produces all possible arguments, all possible answers to it. So we try to push it as far as possible in the hopes that previous conjuncts would make some of the arguments ground and then trim the search space. The second worst is unification generators. They always produce, almost always they produce infinite streams, so it's good to push them down. And calls with some ground arguments, they can be either deterministic or not, and we cannot even tell from the shape of them. So, but we know that they are better than calls with all 3 arguments, right? So we pick those conjunctions after matches, but before generators. So basically, mod inference of a conjunction is picking a conjunct according to this priority. And let me demonstrate. So here we see the conjunct of our addition relation. We don't have any guards here because we don't have any unification or calls with all the input variables, but we have a pattern match. The second conjunct here is a pattern match. So we pop it up. We learn the value of x1 by doing unification. Yes, it becomes ground, and it stays ground in all the subsequent conjuncts. So we can see that add-do applied to x1 and y now works in the same direction as we will be processing now. We're processing now. So it's always in the forward direction. We can run it. because it's not a generator, right? We can get the value for Z1, which becomes output here and input here. And the last conjunct is already moded. We don't really need to do anything, but you can see a safe unification because it does not have any free, so it doesn't have free variables on both sides of the unification. So this is how it's done, the mode inference. And one thing to notice is that one limitation it has, it still have no idea how to order calls which have some ground and some non-ground variables. So for example, if you have the multiplication relation, which uses addition to add, x minus 1 multiplied by y to y, there are two possible orders we can put the addition and multiplication relation calls. So if we try to push the recursive call to mult as far as possible, we get a very, very slow relation because this addition, it generates an infinite stream, which is then sifted through by this multiplication, which is already a costly operation. So this is a case of generate and test behavior, which we want to avoid as much as possible. And this particular order would work much better if we first put the multiplication and only then addition. It's currently not, we don't have any good way to order these conjunctions, but we think we had some heuristics which helped. So, okay, let me pass to Igor. Igor?
Yes, hello. My name is Igor Engel, and I was working on the translation parts from modern Minikanran to functional languages. To facilitate this conversion, we introduce an intermediate language that is a middle ground between functional constructs and Minikanran. It has a few operations, four of which correspond to various model unifications. So that's return for assignment, match bind, and match generator and guard for other unifications. It has a bind operation which corresponds to conjunction streams, and a sum which is interleaving of streams. We treat generators as their own special entity, and we pass them in calls. Next slide. So here's a high-level review of the translation. We translate a disjunction to sum to interleave the streams of various branches. We translate conjunction to bind, also allowing next conjuncts to use variables produced in the previous ones. Relational calls are translated to functional calls and passing of generators, and the indication is depending on mode into one special operations. And the main problem during this conversion is generators. In an untyped Minikanran, we cannot create a generator automatically. Well, we can, but the only one is possible to create is to generate all possible terms, even of mixed types. So, for example, a number successor of a list, which is a nonsense term, but will clog up the string. So instead, we ask the user to provide the generators to function as additional arguments, and we utilize them to mimic type system. We require a generator for every free variable in the right-hand side of unification generators, and also those requirements are transient. So here is an example of multiplication relation that does require a generator by itself, but it needs to pass a generator to addition relation also. In the typed version of Minikanran, it should be possible to generate those generators, to derive those generators automatically from types that will produce all values of a given type. After we convert modern Minikanran into intermediate language, we can convert intermediate language to some functional languages such as Haskell and Camel. We've written both converters. For Haskell, we use employed Haskell to generate code and stream unattended notation process it. And with a Camel, we use handcrafted printer, or Camel version of stream monad and what's syntax for its users. And we also need to have some special care because OCaml is an eager language by default, and Minigarden needs a lot of laziness to work. So after we translated our Minigarden relations, we can evaluate them and see whether we achieved any sort of speed up. We have two evaluation targets, logic formulas generation. So given an interpreter or logic formulas on a given state, we want to produce some formulas, and a multiplication relations run in various directions. For logic formulas generation on a free variable state, providing formulas that evaluate to true, we can see roughly a twofold speed up. It's one of the less impressive examples here, but we can also consider further optimizations for it, which we'll discuss later. For multiplication, we can see a 200-fold speed up, for example, here in forward direction. And in other direction, we also see something along this magnitude even better, backwards direction. And here's an example presented by Kate earlier, when we have two possible functional translations, one of which is very slow, much slower than relational version. That's the one that which is generating test behavior. But if we use faster version, we still get a tenfold increase in this direction. And one of the situations which is not currently implemented, but is in our radar, is monosubstitution. So when a relation is non-deterministic, we need to utilize streams for it. But for a semi-deterministic relation, which produces at most one answer, but may sometimes fail, we can substitute the monad for maybe. And this doesn't require any change to the code produced. So our code is already compatible with this optimization. We just need to figure out when it can be implemented and change the type of the function. This optimization gives another tenfold increase on top of our previous increase in performance of the relational functions. And if we can prove a relation is fully deterministic, so it produces exactly one answer, we can also try to have a non-bonus version, which should be even faster. And we are currently investigating using various determinations check to figure out when it's possible to use this optimization. And another optimization that should be beneficial with combined functional conversion is partial deduction, where if we have some fixed argument for a relation, we can propagate it and eliminate some branches of a relation that should significantly speed up the conversion program. So in conclusion, we present a functional conversion scheme that can speed up relational programs by orders of magnitude. We implemented the conversion scheme in Haskell, and we have a full translator that can take a Minigarden program and output a Haskell or OCaml code. And we have some way to order the conjunct that works most of the time, but first work is needed from this. We currently are working on determinism checks for seeing where optimization can be used, integration with partial deduction algorithms to further optimize the code, and the integration into framework of using relational interpreters for solving for synthesizing programs. Thank you. We are ready for questions.
Thank you very much. Let's thank the speakers for a very interesting talk. Okay, I have a lot of questions, but does anyone in the audience have questions? Okay.
Hi, Walter Schulze, Go Minigarden. I was wondering, you're generating functions from a logical proposition, essentially. Have you thought about also generating a proof to show that these two are equivalent?
I don't think we've thought of it because it has not been our task. Do you think it's going to be easy or beneficial or?
I think a lot of times, like in Coq or Lean, you write a logical proposition to describe your function, and then you write like the optimal function and you prove that they're equivalent. So this would be the function you're generating might be something in the middle where it's not necessarily the optimal function, but at least a function. And like even having the proof that this function is equivalent to the logical proposition is a big step that might help prove the optimal version. It would save a lot of time. Like proving is very expensive, so.
Well, that's basically amounts to formal verification of our translator, right?
Yes,
So
yes, it doesn't, like, we don't introduce anything which can break currently the function. I mean, we can prove that our converter works. That's should be enough.
Yeah. So it should be possible to provide a formal verification that a converter is accurate. We haven't yet done so, but it's possible future work.
Cool, thank you.
Thank you.
Thank you. That'd be interesting potential future work. Any other questions? Okay. Oh, we got another question. All right.
I was also wondering, have you looked at the rewrite rules that Verse has for its logical expressions? Like maybe there's some cross-collaboration work there possible?
Yes, the verse is something which I really want to explore more. Currently, like by the time we've come up with this project, verse hadn't even existed back then. But we had the Mercury and Cari and other examples of functional logic programming, which we explored. And this particular work is heavily influenced by Mercury, the way Mercury works. But neither of these tools guarantee us the completeness of search, unfortunately. And I also believe that by simplifying as much as possible and employing, instead of employing like something like partial deduction or supercompilation on top of that functional conversion, which we're already doing, it should be enough and it should be beneficial already. It's a little bit different approach, I would say.
Yeah, I really appreciate the way it's very simplified. Like, yeah, well done, great talk.
Thank you.
Thank you. Okay. Any other questions before I ask questions? Okay. I too, by the way, am very interested in verse and verse calculus and how that might tie into Mini-Kenran. Now, speaking of functional logic programming, I think what you've implemented, as far as I can understand, isn't really functional logic programming like you get in something like Curry. It's really a more efficient way to try to do relational programming, right? So like the Kent Divig says, optimization is the art of cheating without getting caught. So you're cheating without getting caught, just you're noticing that certain relational patterns you can just do as functions. But that's different than having a functional logic language where you have lambda in the language, for example, or where you can do traditional functional programming. Do you think that it would make sense to extend this work or to play around with this work where you could do sort of a functional logic version of Canran or O-Canran or something like that, where you actually somehow combine the functional programming, relational programming more deeply, where you get something more like Curry or Verse?
I would say that we are already halfway through there, because currently what we currently are doing is getting rid of all Mini-Kenran. We don't need to do that, actually. We can do that only for deterministic relations, or directions, or we can do like for stuff which we know is finite. For example, like AND or whatever works, which works on the Boolean or other finite domain terms. So if we have these ones, we can translate it into a host language and then interact by Mini-Kenran with this host language. like because we already have this miniconron embedded into a host language, we already have some kind of functional logic programming, right? So
Okay.
this is how I view it.
All right. Although right now you still can't do things like use lambda and do higher order programming. I don't think
No, higher order is. I think it's out of the question right now. It's too much.
I think that's the tricky part is really using lambda and higher order things. You know, so okay. So I
But
think that's worth.
do we need it in miniconron?
Well, that's a good question. I don't know. So, right now we kind of encode lambda through writing an interpreter for a language that has lambda, and that's sort of a cheat to kind of get around it. But it is an interesting question: do we really need lambda? You could argue that in standard miniconron, we can't do things like implement capture avoiding substitution nicely. So unless we have nominal logic or we have something higher order where you can do higher order abstract syntax, we can't even implement capture avoiding substitution properly. You know, we can't do gensim relationally and things like that. So those are areas where maybe we would benefit from having something more higher order, but I'm not sure.
Yeah, but I mean, given how it's hard to optimize miniconron as it is.
That's fair enough. Speaking of which, you know, one thing Dmitry mentioned in the last talk was that it would be great to have sort of this, I don't know, macro miniconron. You know, it's a big miniconron that has all of the optimizations and all of the special, you know, versions. Right now we have a whole bunch of different implementations of miniconron in different host languages with different logics and different optimizations and different constraints, and you know, you have a very nice set of optimizations here. I think part of the problem is we haven't really figured out how to have a single system that combines all of these approaches in one system. So have you given any thought about how you might, you know, have a system that combines all of the things we've learned about how to make miniconron and relational interpreters and all that fast in a single system? You know, you're also doing, you know, partial deduction. That's one piece of it, but there are a whole bunch of other things that we've figured out over the years might make programs faster. But it seems tricky, or maybe it's more of a software engineering issue. But we haven't successfully combined them all in one implementation. Have you thought about that?
Well, I'm currently trying to think how to combine partial deduction with functional conversion and make it all live as an embedded language. And it feels like I have my plate full with that.
Okay, fair
But
enough.
I do believe that this is a beneficial approach to combine different optimization. I would definitely want to explore it more. And Igor is very talented software engineer, so we can, I think, tap into it.
Great. Was there a big difference between the Haskell implementation and the OCaml implementation? Like, did one feel much more natural than the other when you were implementing this?
Well, Haskell implementation was much more natural because we were writing the translator in Haskell. It was a losing battle for OCaml.
Well, I mean, this functional conversion into the target language is the very last step, and I think that I whipped the pretty printer for OCaml in maybe a day after everything has been done by Igor with that intermediate language. So I don't really think that it's hard to include any other target languages. But it was pointless to use our Haskell implementation and compare running time of miniconron because my Haskell interpreter for miniconron is even worse than anything else. It's just a basic microconron implementation. So we decided to put it into a OCaml to be able to compare it with the OCanron. So all of this evaluation was done in OCanron. And it seems to give us some kind of good improvement.
And do you think your approach could be applied to scheme or racket implementations in miniconron, or is there something about the types that you need?
Currently, we don't even use anything about types. We only need streams with their binds and plus operations, and
Okay.
nothing more.
Okay, so this should be applicable to scheme as well. It'd be interesting.
Yes, because generators are up to the user. You can write whatever generator you want, and it's the only place where you actually need types.
Okay, great. That's definitely something I would like to explore. Well, thank you very much. And let's thank the speakers one more time.
Thank you for the discussion. It was really nice.
And I'll add the plug one more time that Kate runs this monthly Mini Canron online seminar, research seminar. So if you're interested in that, let me know or let Kate know, and hopefully you can share your research. All right, thank you very much. We have a lunch break now, and then we will resume with the second paper session. Thanks.
All right, so let's get started. First thing is introduction. So we already see from today's tutorial about like, okay, where's the logic programming idea coming from? It basically is turning a unidirectional function into the bidirectional relation. So function from the mathematical definition is like one-to-one mapping. So we can have the input and output goes to one directions. But for relation, we have one-to-many or maybe many-to-many. So that's what we call it bidirections. So in logic programming, there's no input or output. It basically is just relations. So Prolog, everyone knows about it, is one of the example language. It's based on two algorithms called unification and the resolution. Today, like our work basically is focusing on how to extend the unification and the resolution to give you support of the stable model semantics. Okay, so this is an example used everywhere. Like Will said, it's hello world examples, the Prolog append. So most of the time you will see the first, the upper one versions. So it could have the base case and the recursive cases. So the basic case say, okay, when empty list is there, so we unify with those two things. So this is a syntax trigger about like, okay, unifications, you can write in the Prolog. Then the second line, this is also the syntax trigger about like, okay, break down a list into head and tail. And this is the second parameter, and eventually we assemble these two things together. So that's why I write down the unification specifically here to help us understand like later on. Okay? Then the researcher, like in history, like researchers believe function language should be used for implementing such systems. But I don't know why there are some deviations. It goes on a different route. But that's why, like Mini Cameron, I'm a believer in like here, we want to use the functional language to build logic programming or maybe relational programming systems. So some systems like Mini Cameron, log list have been developed over the years. Let's look into like how the append is work in the Mini Cameron. So Mini Cameron append, though, we already saw this in this morning. On the left-hand side is the Mini Cameron version. Right-hand side is the Prolog version I just showed. So we can see some connection. Like, okay, this in Prolog may make it a very concise syntax, but the behind the scenes is still the same. So first we can look into like, okay, two clauses, base case, recursive cases. Then for the Mini Cameron, we also have like count D. We have a base case. It basically is saying the same thing when the input list is empty. We unify in S and the output. So it's the same thing for the second part because we don't have the syntax trigger like okay, H vertical bar T to break down a list into the head and tail. So we have to write it specifically saying okay, we are creating 2 or 3 fresh variables is a head and tail. You can see in the Mini Cameron versions. This line car row, so basically it's breaking down the list into the head and tail. Like this is the input list, right? First parameter breaking down head and tail. Then we do append. We append the tail with the second parameter, and we get the result. Then the last step, okay, same thing here because Prolog is a syntax trigger. We're combining the rest and the edge into the answer to output. So in the last step in the Mini Cameron version, we have to consoles head and rest into the output. Okay, so this is just simple connections, and then later on I will show like more connections between Mini Cameron and logic programming. So from that example, you can tell basically Mini Cameron replicated the essence of the Prolog using macros. It's one nice feature I really like in Scheme. I recently found out it's not all the functional programming have these features. Using macros to create a static search string connected through the continuations. This is the second features we want to focus on because our algorithm is modifying these continuations a lot. Using macros, modify continuation. Still forming a search string, but this time, because we want to do non-monotonic reasoning, we are turning the static search string into kind of a dynamic ones. Okay, so this is the main idea. Then this syntax level, we can see, okay, they are the equivalent Prolog, Mini Cameron. What's the semantics behind these two systems? The declarative semantics underneath this we call monotonic reasoning, is minimum model semantics. So basically, minimum model semantics is like, okay, we assume this goal is true, and we try to use minimum amount of the truth variables to make the whole programs hold, like to satisfy the whole programs. Now, still back to 1970, maybe 1980s, because the monotonic reasoning achieved a huge success. Then the researchers in logic programming community start thinking about like, okay, how about we add one thing called negation into a logic programming? It will give you like more expressiveness to the program. You can express more problems, solutions in logic programming. Then we open up a new word called the non-monotonic reason. It basically, because the negation in there will create some contradiction. So we can think about the monotonic reasoning. It's like as the search we goes by, the truth goes, we accumulated goes monotonically, or not monotonically. And we introduce the negation at some certain points. The model we obtained, we call it stable model we obtained, it will goes down. Okay, so just high level overview of it. So once we have this negation, as I have mentioned, for monotonic reasoning, we have minimum model semantics. With the introduce of negation, so this is one of examples. Back to 1970s, people using a two-person game. For example, okay, in the game theory, we want to think about, okay, what's the opponent will think about my moves. Then I need to think about, okay, my opponents will think about my moves, I need to think about these things. Then this is a very simple game. So it's showing the status like, okay, the winning position. So if we have two players, Alice and Bob, playing this game, the winning position is defined as, okay, there is the move that will make the opponent has no move. So for example, if I'm Alice, I want to make a move. So if I choose the C as my starting point, I make a move going from C to D, then it's Bob's turn. Bob cannot go anywhere. So he lost, Alice won. Okay, so in here, we can see, okay, this is definitely the winning position. Then how about this? When Alice goes from like here, Bob go back and forth, we need a semantics to define this kind of behaviors. Okay, so this one negation, and this is what we call the loop. Later I will formally define, okay, what's the loop in the normal logic program. So eventually, the stable model semantics is a generalization of the minimum model semantics. We will see, okay, why this is the generalization of the minimum model semantics. Because from the declarative semantics definition, you will see there's one step trying to verify the model you obtain from the things called radar. Actually, it's the minimum models of the radar program. All right. So because of the stable model semantics being developed, and later on, people were coming up with all different constructs, not only just the prologue. They extended the prologue with some other rules, like constraint rules. What else? Yeah, anyway, it added a lot of like other rules into a system, forming up a new language programming paradigm called answer set programming. So with the help of answer set programming, the ability for the programmer or the user to encoding some solution for the NP-hard search problem becoming possible. So like multiple tons of application being created since then. We can see some like about like nurse scheduling problems, modeling like living system, train table arrangement, and other hybrid problem solving approach. It's mainly because, okay, well, we are doing planning or scheduling, they have a lot of conflict or maybe contradiction for human beings. So for example, I may have some expertise, I don't want to work with some people. I can specifically state these things. Okay, this is my availability, and let the computer to generate a perfect solution for us. Also, like some application like flight route arrangement system, like last winter, the Southwest had a meltdown. The same thing behind it. Just because like a sound constraint cannot be satisfied, it just propagate and break down the whole systems. Okay, so ASP has some application already, but solving this stable model semantic is very difficult and challenging. That's why like we can see some solvers are shifting from the top down, as we mentioned, is the resolution and the unification approach, into a kind of like bottom up grounding and the constraint propagation approach. Okay, so doing the bottom up, yes, it gives us some like performance improvements to solving these kinds of problems, but these grounding steps actually is a heavy memory, it creates a heavy memory footprint. You have exposure issues in there. That's why like people are always greedy. They want both. I want it fast, want it less memory. So some researchers start thinking back, okay, how can we go back to the top-down approach? We save some memory, and we also maintain a good solving performance. Yeah. And we observed that, okay, no such ASV solvers actually is implemented in the functional language, like the mini-kernel for in the scheme, and using this top-down approach. That's why like we are here. We developed the stable kernel to bridge this gap. Okay, so we realize that constructs like we mentioned, the macros, continuations can help us to solve normal logic programs. And basically here I try to show how these two things can help. Then also mini-kernel provide a very easy access to the underlying unification and the resolution, make the changes like to implement our algorithm into it easily. So overall, this is a relationship. We have like two domains of the languages. Like some solvers may implement in like Python, Java, C, or C++. It's a non-functional programming domain. Previously, I had Prolog, then extended into like a ASP system, like Lingo, basically built on the C++, SAS on the Prolog. And in functional areas, we have mini-kernel. So Prolog, mini-kernel, they are equivalent to each other. So here, like this is our stable kernels. We extend this mini-kernel, and it's equivalent to the answer set or the Lingo systems in the non-functional programming domain. Okay? Oh, good. Now, second part, some background and related work. First, let's take briefly look into the functional programming and the mini-kernel. It's a quick review. This is our understanding or our feeling about like, okay, what's the benefits of using the functional languages. We realize, okay, macros make the code look very simple and concise, and some immutable variables leads to fewer side effects, so less bug, easier to debugging. And the last steps, even though like each small piece of the function looks very simple, but we can use the combinator to combine them into complex features. Then quick overview about mini-kernel. I'm assuming everyone already knows about mini-kernel. It's a huge family and already have multiple host language implement the mini-kernel ideas. So mini-kernel is a system that shows a way to build features of logic programming, especially relational programming, atop of the functional language. And in this case, we really obsessed with the original implementation hosted on Scheme. Many features from schemes help us. We are using the core implementation. This implementation, as this morning, we already introduced, have like three key constructs from the logic programming, equal sign for unification, flash means the existential, and condy for the disjunction. Then we have additional one run interface. Don't have the conjunction because the flow we are executing basically is the conjunction. Then this is the definition in mini-kernel. They use a special syntax notation to define the lambda g@, to represent the internal Go definition functions. So usually like it maps one substitution into the order sequence of 0 or more substitutions. So we are heavily relying on like making changes to the continuation of this lambda g@, as well as introducing more macros on top of it. So make sure like you remember this, even though it's simply just return the lambda g@ into lambda, but it's just telling the user, okay, this is the Go function definition. You know, if we are focusing on the Go function. Then next time we are trying to connect, okay, the relationship between this Go function to the predicate in the logic programming. So if you are using other implementation of the host language of the mini-kernel, make sure you find the right target, then later you can implement the stable model schematics into your mini-kernel. All right, finished the review about functional language and the mini-kernel. Now let's take a look into the logic programming and the stable model semantics. First, we need to have a proper definition about like what is the normal logic program. So on the left-hand side is the definite program, or the prolog is using. So for a definite program class, it usually looks like, okay, A is the head, and then we have B1, B2, till the Bn as the body. All these things imply A to B2. So in this case, we call the A, B1, Bn is the atoms. Then A you call the head, B is the bodies. Okay, so definite program class, put multiple class or the rules into a thing called a definite program. So similarly, like I've mentioned, like, okay, in logic programming community, people are interested about like, okay, negation, how about we introduce negation? So we can see it just extended the representation with some literal has the negation in front of the atoms. So going from B1 to Bn, we have not Bn plus 1, not Bn plus 2, until not Bn. So this is normal program class. So put everything together, we have normal program. Okay. Now, the semantics in the normal logic programming we saw in the previous slides, they have the multiple versions of the normal programs because like people cannot find the answers to the eventually the final version directly. So we have some like progress in the history. So it basically is based on the unfounded set defined in the logic program. So it means like, okay, it's a set of atoms. They are forming a cyclic in the program. So this is the loop definition. And based on the unfounded set is a loop. This relationship between the loop and the negation, we can categorize the normal logic program into 3 versions. The first version we call the tight programs. So it basically, given a normal program, it is tight if there is no unfounded set. It's like there's no loop in there. Okay, we can have negation, but it cannot be showing some loop into it. So Clark, back in 1978, came out with the negation as a failure and a NAF, and the Clark's completion was an attempt to define the semantics for these tight programs. Okay, then later we will say, okay, how about we have some loops? But these loops cannot interact with the negation. So still, given a normal logic program is stratified, and if the loop do not contain any negation, so we can have a negation and the loop in between, negation loop, but these 2 things cannot mix up together. Then the well-founded semantics by Alan Van Gelder et al. Was the attempt for this like non-tight but stratified programs. And eventually, like we come into the ultimate goal. Okay, now we want to remove all the restrictions. The program or the users can write whatever way you want. You can mix the negation and the loop together, like in the 2-person game. Then this is stable model semantics by Michel Gelfand and Vladimir Lifshitz, seen as the generalization of the normal programming semantics. Okay, we talk about the stable model semantics a lot. What is exactly about the stable model semantics? We can take it into the declarative semantics definition of the stable model semantics, which is like given input program P, the first steps in the stable model semantics is that you want to get a propositional image of P. So a propositional image pi actually is obtained from grounding each variables. So we saw these things a lot, grounding. So we're turning the predicate version of the logic programming into the propositional form. So after we obtain this pi, we have a propositional image. The second step is that we want to enumerate all interpretation I of pi. So for example, if pi has like n atoms in it, we will get 2 to the power n interpretations in it. And the third step is like, okay, we already have this interpretation, and we want to using each of these from I to create a readout program. And to verify that M is the minimum model of the readout. That's why we said, okay, stable model semantics is a generalization of the minimum model semantics. So here is where the minimum model in it. So to create a reader program is also very simple. We just replace whatever negative, like a negation, show up in the program. So for example, in this case, not bi in a rule with button if bi is part of the interpretation. Okay, otherwise we replace it with top. Once we have a reader created, it's negation free. So boom, we can use just Prolog or whatever things to solve to see if the unique model m prime, if m and m prime are equal, we call m is the stable model of the original program P. Okay, so from the declarative definition, we can derive a nice property about the stable model semantics. So from stable model semantics, we will see the relation between the stable model of pi, the propositional image, and the minimum model of the reader. So we will say pi and m to be the interpretation. M is the stable model of pi if m is the minimum model of the reader pi m. So stable model semantics will consider if there is a minimum model of the corresponding reader program to be one of the program's stable model semantics. So this will be our goal. We try to implement the top-down solver to obtain the minimum model of the reader program at the same time, like simultaneously. We have a reader program, and that model is minimum, then that's the stable model of the original program. Okay, all good? Now let's look into some examples of the stable model semantics. So for example, like we have one simple program, P'22, written in the logic programming form, and we have one inference rules. Okay, Pxy and not Qy derive Qx. So here's the negation. Then we can see the domain of the x and y is the 1 and 2 respectively. So we can create, like we mentioned, we ground it into the propositional image. So in the propositional image, this is already grounded term. There's no variable inside. We copy it, the same thing. And this is the variables we want to replace with the whatever domain value it is. Because in this case, it's very simple. We only have 1 and 2. So this is the ground propositional image. Then, because this is x, y, and we have tons of atoms, 1, 2, 3 atoms inside. So we have 2 to the power 3, 8 kind of interpretations to the propositional image. Then we try to use kind of the, we need to enumerate through all different interpretations. So here we just use 2 examples. First is M1. So for example, M1 is the Q2. So basically it means that Q2 is true. So in the model, right? In the interpretation, it's not a model yet. And the Q1 and the P'12 is false. Then we can create a reader using M. As we mentioned in the stable model semantics, if Q2 is showing up, so this is true, true. So not true, we place a button here. Okay, now we have the reader program. We can run it in Prolog or something to see, okay, what's the minimum model of the reader program? Because there is no negation inside. And we can see it's false, so Q1 cannot show up. It only has P'12. So this is the minimum model we will obtain from the reader, is the P'12. Is it the same as the original the interpretation? No, this is the Q2, this is the P'12. These two are different, so this assumption doesn't hold. M1 is not the stable model. Okay, then the second example is like, okay, let's pick another interpretation. Maybe it's P'12 and the Q1. So in this case, Q2 didn't show up, means that Q2 is false. So when we create a reader, Q2 is false, not Q2 is the top, means the true here, okay? Now, same thing, no negation inside. We compute the minimum model of this M2 prime. It is the same as M2, see, the P'12 and the Q1. So now we can say M2 is the stable model of the original program P. Okay? Now, we know the declarative semantics is very exponential time complexity, I believe. So we have like 2 approaches to solve this logic program, as we have mentioned. It basically is the top-down versus the bottom-up. So the top-down is still using resolution and the unification. And for resolution, we already know, okay, we starting from the original beginning query code goes. all right? We pick out one goal, we try to expand all the sub-goals inside the rules body, and to prove it, each one is true until this stack become empty. So then we obtain the model of the program. So same thing like for unification. You have two rules in here. One is like we assign the choose value to the goal. So for example, I want to know P1 is true or false. So this is the one rule of the unification. It tells you the choose value of the predicates. And another thing about unification is like it can bounded the value of the variables. So if Px, x can take 1 and 2, after the unification, x may have some domain of like 1, 2. We will look into the more detail about the unification and the resolution and the unification rule later, and to see how we can extend each rows to support the stable model semantics. Some like goal signature and how we use the signature to define the loop and to see if we encounter the loop later on. So still like talking some like history about like, okay, why we try to go from top down and we switch to the bottom up is the constraint. The main idea in the bottom up is that we can do constraint propagation approach. So constraint propagation, as we mentioned, achieve the good performance, solving time performance improvement. However, there's a grounding stage. So it leaves the heavy memory loop footprints in there. So that's why, like, okay, later the Gupta et al. They introduced the co-inductive logic, co-LP, and the co-SLD resolution. But co-SLD produced the greatest fixed point of a program. Then later, Richard Main evolved the co-SLD with some negation and failure called the co-SLD NF to achieve a normal program solvings. So we believe we want to stick with the least fixed point of SLD, because this is a very nice property. We're assuming the minimum amount of goals, and also very close to the stable model semantics. And we believe the transition from here to stable model semantics is simpler. So therefore, like in contrast to the co-SLD and the co-SLD NF, our algorithm still produce the least fixed point as the original resolution, and focus on adding stable model semantics into the finite Hilbert models. So as we have mentioned, we want to add the semantics, make the changes to the resolution and the unification. Then we need to categorize the roles of the unification and the resolution played in the prologue. Then we can extend it to the features, right? So originally, resolution only has one rule. So you're just selecting some goals, assuming this goal is true. Eventually, it produces the minimum models. This one we will keep, and we'll add 4 more rows to the resolution. Then for unification, you have 2 more rows. One is to assign the choose value to a goal, and assign the value to variables. So they have 2 things in unification. Then we will see like how the mini-Karen, you're using one goal functions to achieve these 2 rows. Then we want to extend 1 more rows unification to produce the choose values under the negation, but it does not assign any variables to the values. So this is a very important assumptions. I will go into that later. Now is some like a connection between the logic programming and the mini-Karen. So in true and false, so this is the, let's look into the propositional logic first. So in the, like I just mentioned, the unification have 2 rows. It actually coming from the function, okay, we extended the substitution set. This is how we assign the values, right? After we executed the unification, the substitution set will get updated. These variables will bound into some values. And this unification will return success as the choose values to the goals. But in the propositional representation of the mini-Karen, we only use the unification to play 1 rule, which is we only return the choose values, right? The substitution set in this case, it doesn't change. It's always empty under the propositional cases. Okay? So this is how we connect from the mini-Karen representation to the logic programming. So basically, with a 0 arity of the variables, of the propositional logic. In mini-Karen, same thing. The variables, the logic variables, we just leave as empty. So this is one simple definition of the succeed and the failed. You can see the succeed and the fail, it doesn't take any input parameter or the variables. Okay, it only uses the unification to produce the choose values. So we try to unify two different values. Okay, we produce false. We try to unify two same values, we produce succeed. So there's only one rule is using under propositional logic. Then once we move into the practical logic, unification has one more thing, one more job we can do. It's like, okay, I'll try to unify the variables with some values. This be achieved through the, like I said, the substituted set. Okay, one functions, two returns. As you successfully return is the choose values. If you also have the substitution set updated. So let me see. Time is running out. I probably will skip this one. Just to talk about different representation of the logic programming in mini-Karens. And we briefly mentioned about the grounding, and why grounding will create a huge memory footprint. So for example, the last program, if we read them in the predicate versions, is very simple and easy. But if we try to ground each variables with the corresponding values, it will generate tons of the programs. Okay, so grounding is not good. We try to avoid. Now finally goes into our work. So the theory foundation and algorithm overviews. This is the property we just derived from the stable model semantics. As I mentioned, we want to produce the minimum model and its corresponding readout program simultaneously. Okay, we want to find the minimum model and the readout program simultaneously. Then the unification, the resolution, original goals, rules, we already mentioned. So here we try to let unification to do one more thing. It only produces the truth values for the negated unification. So it does not bind any variables to a values under negation. Then for the resolutions, we want to do four more things. First thing is we try to distribute in the negation into the unification levels. Then you also need to take some responsibility to produce the truth values once we encounter the loop. Okay, so unification cannot do the job for under loop cases. Then the third one is like we want to get the domain of the variables. Once we have the domain, we can go through the all the values. This one is because for the fresh or the existential, under the negation, for example, not fresh, not exist, it flips the semantics into the for all. The quantifier turns into the for all. So for the resolution, we want the resolution to get the domain of the variables and iterate through all these values. And the last thing is like we want resolution to continue execution even after we obtain the partial result. This one is because the NP-hard problems, there's no optimal substructures. Okay, so even though it's a partial result, we cannot guarantee it's a global result. So this is our system overview. We get a user input. This is all the user input. User can have defined the original program. User have the input query. Original program still here. And we have using some like a construct from the mini-Karen and the scheme. In the blue part, we have macro, transformers, run interface, still from mini-Karen. And our outputs, for example, the stable Karen program, we will complete the program, put in here. We have for all values, the domain values, and some other helpers, for example, loop detection, partial result set, and negation handler. All right, so this is the big assumption. We have already seen it so many times, like unification under the negation. It doesn't produce any values. So you only can produce the truth values. So we need to make sure the variable is safe under the negation. So for the safe, means like, okay, there's no free variables. Okay, so this is the key takeaways. And it's just like, okay, in Prolog, or maybe in mini-Karen, the ordering of you are writing the program matters. And the same thing here, the ordering also matters. We can do some rule rewrites later, but we just, in our algorithm right now, we're just assuming the variable is safe. and we leave the safety issues to later. We can resolve at the compilation time and the runtime as well. So we want the input program to follow this clause. Okay, we put all the positive goals behind the negation goals, and we assume all the variables used inside the negation goal will get the values. Okay. And with this assumption keeping in mind, then we can start our journey into the integration or implementation of the our systems. So first thing is that we want to meet with some new friends. As I've mentioned, this is a very important construct, the lambda G add. We try to add more things into this continuation. So we introduced two new friends here. One is called negation counter N, and the call stack frame CFS. So for a negation counter, it basically just do one thing, to record how many negations we have seen. There's one negation, okay, 1, 2, 3. I will show how to use it later. But as long as like there's a notal, so there's a not operator here, we just do simply +1. Okay? And same thing for the call stack frame. So call stack frame is recording the calls to help us to detect the loops, right? So as the stack going up and we see the goal we tried to prove previously, means like we are in the loop. Then we start handling the loops. So this is the two new friends will help us to achieve the normal program solving. Now the first thing is like I mentioned, we want to give a new role to the unification. It's turning upside down, right? From positive to the negative. Originally, this we already mentioned unification 2 roles, but under negation, you only want to provide 1 rule, which is assign a truth value to the negative goals. Okay? It's doing nothing else because a huge assumptions there, whatever input you give under a negative unification is all bounded or grounded. So we can safely produce the truth value of this goal, negative goal. So this negative unification, we treat it kind of like the base case in our algorithm where the negation direct applies to the unification. So in this case, you only produce the truth values. Then later we will see how we distributed the negation to these unification levels through the resolution. Okay? We'll call it down to the base. We already have the base case. Now we want the negation to be distributed to the base case, the unification level, through the resolution process. So how to do that? We start from the propositional logic first because it's simple and easy, and it can be done using the De Morgan's rules. Okay? Because in propositional logic, there's no variables inside. It's just a bunch of the single things like here, the Q and R, no variables, S and the T. So we want to make sure, okay, this is the positive versions, and the complete negative goal is like, okay, count D is the conjunctive, is a disjunctive normal form. So it's like, okay, to prove P is true, we have 2 ways, either it's QR or ST. Then once the negation applies to here, under the De Morgan's rules, right, we turn in the DNF, disjunctive normal form, into the conjunctive normal form. See, this negation coming in, the count D is a disjunction, it becoming conjunction. Right? We have 2 big conjunction. First one, conjunctive is the next one. Then the negation goes inside. The first rule is the conjunction, Q and R, turning into Q or R, and the not goes inside, right? The not P, the not right now, it eventually reach the unification levels. So this is the De Morgan's rules will be used for the propositional case. So this transition can be implemented in the macro very concise and easily. You can see the count D. So this is a transformation. Once we match the goal with count D. This is a high-level disjunction. We want to convert it into the conjunctions. And inside each clause is a conjunction. We want to turn it into the disjunction. So this is basically these 2 macros doing, flipping things around. So we can distribute the negation from a very high level all the way to the unification level. De Morgan's rule for the propositional logic only. And one thing we need to notice about, like, okay, in the previous slides, there is the negation, like not for the how can I say, the template, or sorry. There's a negation in front of the goal. But here, like, we don't showing up this here. This is the reason, because the count D happenings under the negation only. So they're already carrying a negation counter is the odd numbers, indicating, okay, implicitly have the negation inside, okay? Just one small thing. Only 2 minutes. Maybe after I finish this one, then I would say there have more things about, like, how we deal with the variables and the domain of the variables, turning the execution route, a lot of things. But there's one thing, like, we want to wrap everything into one goal. So even though, like, user only define the positive goal, we want to generate the negative goal as well. So that's why we have a definer. It's a naming convention to have O appended after the define. So definer is basically combine the 2 things together, the positive goal and the negative goal, into one thing. So the user don't only need to write or define positive goals, then we will generate the negative versions implicitly. So stretch out basically tells about, okay, how we're moving from propositional logic to the predicate logic. The De Morgan transformation does not work for sure. Under the predicate logic, you need to analyze the property in there, because these 2 things are not mutually exclusive. They are connected. They have some relations together. So you need to come up with the transformation. So this is our transformation to replace the De Morgan's rules under the predicate versions. And we also need to update the macro we defined on the previous slides to support this kind of variables inside. Then later, once we introduce the variables, we need to know, okay, what's the variables domain is. So for the variables, once you get assigned to values, we identify the generators. We have saw many concepts in the previous talk already. This generator basically is the first unification to turn the unbounded variables into the bounded variables. So once we encounter these generators, we want to let the resolution to change the execution course. Okay, previously you are like essential going through one by one. Now let's go all the way to find out all the values. That's why we call it code on the fly. So this is the dynamic search graph in here. So this domain value obtaining process need to based on the context. So once we obtain the values, once we obtain the values, we need to have a for all things. For all is basically iterates through all the values of the domains and to check if they still hold. Now I have some like loops we need to handle. We categorize the loops into positive loop, negative loop. Furthermore, negative loop have odd negative loops, even negative loops. All these loops creating some troubles, but it's not a strange loop for sure. We can, like I said, we already record how many negation we have counters. So during the computation time, we can see, okay, this is a positive loop, negative loop. We assign the proper semantics to it. Let me skip through this. Some examples about like, okay, what's the empty models, where is no models coming from? Now for the loop, it creates some situations. For example, the odd negation loop, it creates a contradiction. If all the contradiction in your program cannot be resolved, your program is unsatisfiable. That's one very important concept. And also, like when you have even negation loops, your answer set actually is splitting. That's why we may have like multiverse issues here. So one easy example about the multiverse issues is the example slide. No, it's not showing on the slides, but it's like, okay, Alice and Bob go into a conference. So they are like stating out the preferences. If Alice is going, Bob is not going, or Bob is going, Alice is not going. So this kind of like even loop over the negations, right? It will create splitting like two stable models. One is like Alice go, or maybe Bob goes. So we need to kind of use the partial result set to maintain the universe we already obtained, to make sure these two universes don't interfere with each others. Then this is the thing I mentioned, because the NP-hard properties in the problems, once the resolution already obtained one solutions, we don't want it to stop. You still need to check the rest of part of the program to make sure, okay, your partial result is the global result. Okay, then we're back to the game. Once we finish the implementation and algorithms, we try to run the two-person game with the stable models or semantics behind, and we can able to obtain the results. Some conclusion and the future work. Sorry about running over time. So overall, we're still using resolution and unification, but we just extended it, okay? Resolution got 4 more rules, unification got 1 more rules, and now we can have stable model semantics in the mini-kernels. And we need to add a proof for the stable models algorithm we introduced here. And want to have some proof about a discussion about variable safetiness. So to prove about the stable kernel algorithms, like I said, we can go back to the property of the stable model semantics to create a proof from there. This is a more detailed discussion about like a variable safetiness issues, why we are writing different orderings. So for example, put a not here, and we cannot get a result. User have to specifically mention the values. Or like I said here, like we put a not at the end of the program, then we will be able to get a result. And some detailed discussion about variable safeties. We want to address that. And we also want to support, like I said, in answer set programming, it's not only just a stable model semantics, it also have like constraint rules, choice rules. Some solver will support infinite Hilbert models and some inequality constraint. It could be a future work. And also we want to have a bottom-up. This is a very nice algorithm, conflict-driven, no-good learning algorithm to the top-down word. That's all. Thank you, guys.
Thank you very much. That was fascinating, and I look forward to playing around with this implementation. I'm afraid we're over time, so we're going to have to move on to Evan Donahue from University of Tokyo, I believe is on Zoom. If you have questions about this work, which I hope you will, hopefully you can ask the questions during the coffee break in 30 minutes
sure.
or 45 minutes. And also, I hope you'll present this during the monthly online mini-Kenrin research seminar. I think people will find this very interesting. Thank you very much. All right, so our last speaker of the day in terms of the papers will be Evan Donahue, who's at the University of Tokyo. And he's going to be presenting on very interesting work on using goals as constraints in mini-Kenrin. Obviously, we have many types of constraints, and so it's interesting to see an alternative approach to implementing constraints. After this, we'll have the coffee break, and then after the coffee break, we'll have a discussion on what the future for mini-Kenrin relational programming might look like, and I hope you all just join us for that discussion. Okay, Evan, take it away.
All right, thank you. Hopefully you can hear me. If not, someone jump in and let me know. I'm going to try to share my slides now. Keep your fingers crossed. All right, so we just got one share button. So let's click that and presenting. Hopefully you should see the slides. Not to flag me down. All right, let's get going. So, as Will mentioned, my name is Evan Donahue, and I'm currently a postdoctoral fellow at the Tokyo College Institute for Advanced Study at the University of Tokyo. My talk today is entitled Goals as Constraints, Writing Mini-Kenrin Constraints in Mini-Kenrin. And in it, I'd like to talk about some work I've been doing trying to make it easier to express complex constraints in mini-Kenrin and still have them run efficiently. I've divided today's talk into 3 sections. The first one, I'd like to describe the interface to the constraint system and what it would look like to program in this dialect of mini-Kenrin. Go through a few examples. Next, I'd like to talk about the implementation, which I think I can simplify enough to basically give you the whole idea of how to do it in this talk. And then finally, I'd like to talk a little bit about the issues I'm currently working on and a little bit about performance and kind of the current state of the system, which is a little bit of a work in progress, but I think is far enough along that we should have plenty to talk about. So let's get started. In comparison, so many non-trivial mini-canron programs require some form of constraints to run efficiently. And the problem is that each new constraint generally requires, all else being equal, extending the mini-canron implementation itself, which means that only implementation maintainers can really add new constraints. There has been a few examples of work in the past that have created constraint authoring frameworks, which make it easier, although it still does require time and a degree of specialized expertise to author new constraints. And moreover, I would argue that there are some potentially desirable constraints, the sheer complexity of which is beyond what it's realistic or feasible most of the time to express in such frameworks. So in the limit, and this is a slightly beyond what we can do at the present implementation, although hopefully not by very much, if we imagine all the way at the extreme end, implementing something like an entire relational interpreter as a constraint, that's a whole order of complexity above something like Absento, and that's what I'm aiming to be able to do with this implementation, because I think that could open up some really interesting new architectures for relational interpreters and other related types of programs. I wanted to bring that up as an example in particular so that we could think about what would be required for that level of undertaking. Right? We wouldn't want to implement a relational interpreter entirely in scheme code or in the host language code because that's what we have mini-canron for in the first place, right? And that's exactly the idea of this talk. So if we view constraint solving as search, then the constraint solver is just another mini-canron interpreter nested inside mini-canron, and we can use that to express things that mini-canron makes it easy to express over and above writing our constraints in scheme or another host language. I think mini-canron is an ideal constraint language for mini-canron because now we can express constraints over the same kinds of structures that we can generate and even potentially reuse the same code to do both in a single program. So in order to do that, we're going to need three new forms for constraint authoring. Constraint, which wraps an arbitrary mini-canron goal and specifies that it runs as a constraint. P-constraint, which defines new primitive constraints. So normally unification is the only primitive constraint, the base system. But if we need to constrain some infinite quantity like symbols or real numbers when writing symbolo or numbero, we can define a new p-constraint, which works similarly architecturally to other constraint authoring frameworks in the sense that we fall back to scheme or host language code to do what we can't express really in mini-canron. And then notto, which is a simple form of negation, which helps us write a whole new set of constraints. All right. Let's look at some examples of the constraints we can write with these new forms, starting with Booleano. So here on the left, we have a normal generative mini-canron relation Booleano that just enumerates true and false. And on the right, we have the constraint version, which is just the normal version wrapped with constraint. So this works exactly like you'd expect. If V is ground, then we fail or succeed right away. And if it's free, we suspend in the constraint store. And then if V is ever constrained to be not true or false, this equality, it immediately unifies with the other one. So this is, note that this implementation, this whole implementation of mini-canron that we're talking about here is a first order mini-canron. So constraint is not really a syntactic form per se. Condi is going to return a concrete Condi goal structure, and constraint just accepts that as a function argument and wraps it in a constraint structure so that we can also just write the normal relation and turn it into a constraint at the call site like so, which is useful if both the constrained and unconstrained version are important. We can extend that pretty naturally to something like a simple arbitrary finite domain, just dynamically building a disjunction of unifications that are over all the domain elements and running it as a constraint. So note that in all cases, when we see in this talk, when we see the double equals unification there, we're referring to the fully general normal mini-canron unification. So we can have free logic variables just about anywhere you want in these constraints. We can also handle recursive structures like lists, as in proper listo. As a normal relation, this generates an unbounded number of lists, but running it as a constraint, it simply runs until it hits a free variable in the tail, and then it waits, suspends itself and waits in the constraint store. And then when that becomes bound, it continues constraining. The problems like this show up frequently in normal mini-canron, such as in relational interpreters, constraining lists of arguments to lambdas to all be symbols, or testing whether something is a valid number with one of the usual mini-canron numeric representation schemes without having to generate a bunch of numbers spuriously. So it's a very natural thing to express these relations in mini-canron, and constraint just lets us get rid of that middle step where we generate all those useless numbers, which frequently makes what we want to express somewhat awkward to express in unconstrained mini-canron. Now, one minor limitation I'll flag here is that if the constraint, since the constraint itself never fully grounds the tail of the list, so if we never ground it ourselves, the reifier shows us this sort of ugly constraint on the tail instead of a fully proper list. But I think that's probably a minor implementation issue we can fix in the reifier. That's one of the loose ends I'm kind of currently working on tying up in the code base. So another thing I wanted to flag in this example before it becomes important later on is that I actually rarely use fresh in this code base. Instead, when I need to structure a pair, I use a pattern matching form more like this. Matcho binds L to the pair of free variables H and T, and it runs its goals in the lexical scope in which those free variables are bound. Matcho is proven much easier to optimize than fresh, especially in the context of this constraint system. So I'll sort of mostly be talking in terms of that. And I think actually, fresh is not currently implemented in the classic sense for compatibility with this constraint system, although I've done it in past versions of the code base, and there's no problem with it. It's just an sort of current state of the code base comment. And then finally, we get to presento. So you can think of presento as the negation of absento. So rather than saying a value must not be anywhere in the term, presento says the value must be somewhere in this term. And the implementation is exactly what you'd expect from that description. Either the term unifies with the value, or else it's a pair, and either its head or tail contain the term. The thing that makes this such a pain to implement in traditional constraint systems is that, unlike absento, we can't simply check the presento constraint on our head and tail independently. If the value is present in the head, then the constraint on the tail must not cause the branch to fail, even if it would otherwise, right? So there's a dependency between them. What we have to do instead is implement a single constraint that walks the tree, and whenever it comes to a free head and tail in a pair, it has to suspend itself on the head, but remember the tail for later, in case it fails somewhere down inside the head and has to jump back to an earlier tail to keep walking the term. So as it walks the tree, it may build up an arbitrarily large list of unvisited branches that it needs to finish visiting to confirm that the value is somewhere in one of those branches. However, our misery isn't over there, because what if we want to check that a complex tree term is present inside another complex tree term where both of them may contain free variables, right? So now we have to suspend ourselves on some collection of the variables within that unification. And then only once the unification fails on one of those subterms do we want to resume the higher level walk of the tree. So all of this is doable in a sort of Turing complete anything is doable sense, but it's just really obnoxious to write. So I think anyone who's tried to write presento can probably attest. And so as we'll see when we get to the implementation section, what we're looking at here is essentially just a disjunction of conjunctions, and we can handle that in a principled way without having to re-implement it for every new constraint. The next two sections are a bit shorter. P constraint just lets us define basic constraint types other than unification to use inside our freshes and condis. It's useful for dealing with non-enumerable host system values like numbers and symbols, and we need it to implement things like symbolo and numbero in a sane way. So mechanically, it works a lot like previous constraint systems in that you have to define what happens to bound values and interactions with other P constraints manually in whatever your host language is. Although crucially, you don't have to define its relationship to other complex constraints, right? So symbolo and numbero will never have to worry about absento or anything else that's written with the combinators, because those are already handled automatically in the system. We only need to worry about other P constraints like unification and other symbolos and numberos and whatever else we've defined with P constraints, because as long as we handle those interactions between primitive constraints, the system will automatically parse absento and whatever else into its component unifications and P constraints and test the interactions individually as needed. So let's see here. Looking at this code, which just defines a generic typo constructor. For type constraints, we first just check whether V is ground and then return a trivial succeed or fail goal if so. But if it's a variable, we use the P constraint constructor. This creates an object with three properties, which is a list of variables on which the constraint depends. So here, list V, a reference to the function that handles the checking of constraint satisfactions, in this case, type check, and a list of auxiliary values that get past the type check, which in this case is just our predicate function T question mark, which might be symbol or number or pair or whatever predicate from the host language we would be passing in here. So we can then define all of our type constraints in terms of typeo. I'm not going to show type check because it just sort of currently requires little knowledge about the underlying system architecture and probably needs an API redesign, if I'm being honest, but basically just receives either a value to which V is bound or else another unification or primitive constraint bound to V, and then has to return succeed, fail, or another primitive constraint that's a simplification of the current one, and kind of just works on in the host language in that way. You just define a function that does that for that particular return signature. So finally, that brings us to Nado, which lets us negate arbitrary mini-Canron goals and constraints. So disequality is just negated unification, and that's exactly how it's implemented internally. A Nado sort of structure wrapper just wraps around the primitive unification constraint, first order constraint. We can similarly define other negated primitive constraints the same way. Nado just creates a structure that wraps whatever primitive constraint in a Nado container, and that gets handled by the interpreter. And we can even handle complex relations as well. So negated conjunctions and disjunctions become disjunctions and conjunctions of negated constraints via De Morgan's laws, as you would expect. To negate fresh and lista, we really just run fresh normally and then negate whatever goal comes back, like any other negated constraint. I've only tested this negation of the pattern matcher. Like I said, fresh isn't completely supported enough yet for me to have tested negated fresh, although I think in principle it would work the same way. But yeah, and we can also sort of implement absento and presento in terms of one another by just negating them if we wanted to do that. As I don't know if there's any particular limit to this. As far as I can tell, it works on all the things I've tried it on. And then finally, we get to implement absento. So the absent value term is disequal to our complex term, and the term is either not a pair, so we're done, or if it is a pair, our value is absento from both the head and tail. So before I go on, I don't know if we have a good format for asking questions over Zoom, but I'll just check if there are any questions about the interface here before I talk about the implementation, or meta check whether we can even really ask questions in this format. And if I don't hear any response, I'll assume that one of the answers to those is logically a negation, and we will continue with the implementation while I get a drink of water.
Questions online, but there might be some questions in person. And if not, I have a question. So my question is, if you go back a slide or two, for the for the disequality constraint, and also for the not Boolean but for this disequality constraint, that's fine. The equal/equal. I'm trying to understand exactly what Nado means, because disequality or disunification is not the same as saying two terms cannot unify. It's saying that two terms represent different values. So if X and Y were fresh logic variables, then it's fine to say that they're disequal. But if those do unify, so it's not like they don't unify. It's just that they could be different values. So I'm trying to understand what the Nado means here.
So what the Nado means is basically, and this is kind of one of the things one of my kind of like open conceptual questions with implementation I'd be kind of curious to hear other people's thoughts on. So thank you for the question. Let me see if I can make that clear what's going on here so we can kind of see where this fits in the kind of greater scheme of logic. But basically, I'll talk about this a little bit later, but what Nado does is that there's kind of a very, like a generalized form of the case analysis that we usually do when we implement disequality constraints. It runs its internal goal and then analyzes whether it succeeded, failed, or simplified into a different goal, and then either fails, succeeds, or wraps that in another Nado for future negation. So if we run it on unification, it's exactly equivalent to to implementing disequality in the way that we usually do. And that the inspiration, I'll talk about this later, but the inspiration behind this kind of whole approach is just generalizing the way we implement disequality to other primitive constraints and other general goals. So basically it does De Morgan's laws to conjunction and disjunction in the obvious way, and then it does the kind of disequality case analysis to unification and other primitive constraints. But there's no, I know like other works have kind of done various sort of deeper dives into negation and quantification and kind of other sort of forms of logic. And this is really just a very straightforward sort of device to implement disequality and disequality-like constraints, which turns out to be seemingly very useful in implementing a lot of common constraints. Does that make sense?
Yes, thank you. Any other questions from the audience? Okay, I think you can go ahead. Thanks.
Alrighty, thank you. Let's talk about the implementation. So the core of this implementation is very simple. And I've simplified the code down to use in these slides by stripping out a lot of the performance related details. So I can't guarantee the slide code would run as advertised because I haven't run it, but hopefully it will communicate the key ideas, and then you can look at the implementation of the paper for more details or ask me later. So the way I think about the constraint solver in this implementation at a high level, high sort of metaphorical level, is as a conversation between two mini-Canron interpreters, which I call the goal interpreter and the constraint interpreter. So the goal interpreter's main job is to create the branches of the search tree using Condy and Fresh and to assign new constraints to the appropriate branches. When it assigns constraint, it passes control to the constraint interpreter, which simplifies the constraints within a single branch, possibly to failure, and returns control to the goal interpreter. So if we view a mini-Canron program as a set of constraints, mini-Canron interpreter's job is then to find all subsets of mutually non-conflicting constraints logically entailed by that initial set. So the goal interpreter separates the constraints into all possible subsets, basically, and the constraint interpreter searches for a set of constraints within each subset that does not conflict. So to make this conversation possible, one of the key ideas behind this implementation is that there are no dedicated constraint objects. Constraints are in all cases represented by first-order goal objects. Conjunctions of goals are stored directly in the constraint store. In all of the following examples, just remember it's goals all the way down, right? There are no separate constraints. So let's look at a few of the implementations of some of the main pieces of the solver and see if we can get a working understanding of roughly how they're working. So I've got some scheme code here. Unification will seem hopefully broadly familiar. There are 3 steps, one on each line. Do the actual unification, check for failure, and if needed, continue solving any constraints that depend on the unified variables. So a few comments about this code should hopefully help clarify the interpreter and how it works as a whole. So let's look at the function arguments first. The constraint solver as a whole has the same signature. G is the constraint that has just been added that we're currently solving. So for argument's sake, let's say we're solving the unification x equals 1. S is the current state. CTN is the conjunction of all constraints in the program to the right of G. So let's suppose that before this, we were solving the conjunction x equals 1 and z unifies with 3. The first thing we would do is pull off z equals 3 and any other right-hand goals and thread them through the interpreter as CTN so we can solve them later, which gets us back to solving x equals 1. So CTN is an abbreviation for continuation, because this pattern just sort of metaphorically feels to me like a kind of continuation passing style pattern. So I've been calling it conjunction passing style, just sort of mentally, even though we're not working with continuations or even literal functions here. I think of the right-hand goals as the future of the computation, and we can actually treat it in ways very similar to a continuation in some circumstances by manipulating it or running it several different times in different contexts, which sometimes comes up in probabilistic implementations, as I think is often done with continuations in other PPLs. So resolve is conceptually an extension of CTN. It's just additional goals that are conjoined into the future of the right-hand solving process. But it is for constraints that started out in the state when the constraint interpreter was called and that have been pulled out so they can be rechecked or resolved, hence the name. So it's important that we keep these separate for reasons I'll discuss later. But for instance, if x was already constrained to be disequal to 2, but then when we start solving x equals 1, that would get pulled out by the unification and added to resolve to be rechecked later, and CTN would be moved to the current constraint to solve. So we move Z3 up, we unify x equals 1, and we pull out the constraints on x and we put them in the resolve variable. Finally, committed is a conjunction of all the constraints that have been added to the state so far during this call to the constraint interpreter. So it's the delta of changes made to the state. Since we previously unified x with 1, committed will in this case just be x equals 1, along with any other changes we've made to the state so far. So if we look down through the code for the moment, unify on the first line returns 3 values, the newly extended bindings right here. which are equivalent to the prefix of the substitution in an association list-based substitution. So it's a conjunction of any constraints, it's a conjunction of all the simplified unifications we just made to the state. We have a recheck variable, which is a conjunction of any constraints on any of the bound variables that we pulled out of the constraint store. And we have S, which is the new state extended with the unifications made. So if the unification fails, we return two values down here. And the signature for the whole constraint solving function is two values here. So one of which is the state, which is the right-hand side failure stream in this case. The other, which is a goal, which in this case is the trivial fail goal. And that fail goal conceptually corresponds to committed in the input arguments. So although we're returning a failure here, if we had succeeded, we would have returned committed instead. And the central mechanic that drives this whole interpreter is that we're not only operating on a state, but we are simultaneously constructing a constraint goal, which remember constraints are goals, constructing a constraint/goal that reflects all of the changes that have been made to the state so far. So in this case, if everything succeeds, we'll ultimately return a state with x equals 1 and z equals 3 in the substitution, and alongside it, we'll return the conjunction of those two unification goals. So technically, we could probably get away with just returning the delta and not the state. We mostly return the state for performance reasons, but I thought it would probably be illustrative to see both together because they illustrate the same thing, and they kind of represent the same data. And the reason that we need to return the constraints alongside the state is that we may later need to negate or disjoin them with other constraints, which is hard to do with the way that I've represented states. So assume that we do have further constraints to solve because resolve is not yet the trivial succeed goal. Then we would call the top level solver in the third line here with solve constraint, which has the same signature as solve unification here, down here. Succeed goal at the front tells it that we've finished solving the current constraint, and so it can pull the next conjunct off the CTN continuation and solve that. Or if that's empty, it can start solving resolve. And if all of those are empty, then we run out of goals to the right-hand side, and we've finished solving the computation. And if we haven't failed by now, we must have a consistent set of constraints. So we return committed and the state together. Note that bindings here are a reified goal, as I mentioned. They're a conjunction of unifications we've just made to the substitution that we get back from the unifier. So we can join that in this last line to our delta constraint here, the committed constraint, to track the fact that we made these changes for the rest of the program. And we also take any constraints we need to recheck and can join them onto our resolve goals so they get checked later as we call down into the recursive call there. So if we assume there are no unifications or disjunctions in this particular program, then the return goal and the return state will basically be the same information, and we can just toss out the returned goal and use the state, just like we would be doing in a kind of a normal mini-Cameron interpreter. That was like a bunch of details there about the implementation. Does anyone have any clarification questions they're wondering about that real quick before I go on? Because that was kind of most of the structure of the interpreter, and the other things are just sort of specification or specializations of that. Get another drink of water while anyone thinks if there are any clarifications they need about.
Or clarifications needed? I think you can go ahead, Evan.
Alrighty. So now hopefully we've got some sense of that. We can use that to define the remaining complicated bits of this interpreter. Nado, to further answer our previous question, hopefully. So let's talk about Nado here. G, a little bit confusing in the signature here, but G is actually going to be the negation of the negation. So if we're solving the constraint x is not equal to 1, G is x equals 1, and we're just so we can kind of solve the positive constraint and do our case analysis. So at this point in the code, we've already taken the internal goal out of the negation, and we're solving that for case analysis. And we're just going to try solving the positive version of the goal and doing that case analysis. And this is exactly the way, as I was saying earlier, it's analogous to the way that we normally do disequalities, right? And in fact, this whole system, as I kind of alluded to, came about because I was really just trying to implement a simple type of negation operator. And I was thinking about what it meant to negate a disequality constraint. And since disequality constraints contain all the basic mini-Cameron logic operators, they have conjunction, disjunction, negation, and unification all packed in there, I realized that we could just straightforwardly generalize the way we handle disequalities to arbitrary mini-Canron goals. So this whole presentation you can think of as basically a generalization of disequality handling, and the implementation follows that basic logic. If you understand disequalities, then you can kind of see where we'd be going with this. And the last real piece of this was just realizing that if I then negated the negation, then we would kind of be left with these positive versions of the constraint, like a positive disjunction constraint and unification constraints that were in the constraint store because they were like tucked into disjunctions, but not in the substitution because we couldn't guarantee that they would be constrained in all cases. And then we basically have the full set of constraints that this implementation gives us coming out of that basic disequality case analysis. So just like disequality solving, where we unify these terms, and that where we unify two terms, right? And then we check whether the unification succeeded with these changes, succeeded with changes, succeeded with no changes, or failed, and then kind of either invert or just kind of package it up for later. We do the same thing here for arbitrary primitive constraints. So unification gets handled in exactly the same way that it always does. We either succeed with no extensions, and then in which case we invert to failure, or we fail, in which case we invert to succeed, or we have some extension of unifications that we repackage as a negated disequality constraint and get on with our lives. And similarly, P constraints work the same way in this context as unification constraints. We just wrap them and do the case analysis. You can see that happening basically on the first line where we solve the constraint and get back a state S2, which we immediately throw away, and the constraint C, which is corresponding to the kind of committed that in this whole architecture returns the constraint, the goal representing changes made to S that are present in S2. So C is all the changes we just made solving this positive constraint. We then negate C right there, and we store the negated C in the original state and also in the delta constraint, right? Because we have to track both in the constraint and in the parallel state all the changes we make, and then we continue solving, and that's it. The one remark I need to make here is that it's important. The real only kind of conceptual thing going on with the rest of these relations here is how we manipulate the constraints, the kind of the continuation and delta constraints that we pass to these subsequent solvers. It's important that when we solve G, we need to pass the trivial succeed goals in instead of continuation, resolve, and committed right up there, right? And this is because, as I mentioned, C represents that cumulative delta of all future solving. So if we passed in real goals there for continuation, those goals will show up in their solved forms in C when we get it returned. And then when we negate C, we're not only negating the original goal G, we're negating all the goals to the right, which is not what we wanted, right? So for example, if the goal is X disequals to 1, then G is going to be X equals 1 in this case, the positive version. And then suppose our continuation is Y equals 2 that we're going to make subsequently. Then the return C we get will be X equals 1 and Y equals 2 in the substitution. And then if we negate that, we get X is not equal to 1 or Y is not equal to 2, which isn't the goal we were solving, right? We were solving X is not equal to 1 and Y equal to 2, right? So we've negated too much. So we have to pass those succeeds in so we only get the result of solving this one goal, and then we negate that, and we're okay. Likewise, if we passed in the real committed constraint, C would be conjoined to all the past solved goals, and we would negate those, which isn't correct either. So committed is the past conjuncts to the left of G. G is our kind of current conjunct we're solving, and CTN and resolve together are the future conjuncts to the right of G, right? That's kind of the metaphor we have here. But we only want to negate the result of solving G in our case analysis. So we solve it in its own hypothetical context where all of the others are trivial, and then put that in the store and continue solving, which will guarantee that it's compatible with all future constraints that will pull it out if needed and check it. Condi or disjunction works in a very similar way. We solve the right-hand side and the left-hand side of what I basically, my disjunctions are just binary structures. And then we disjoin the solved forms, conjoin them to our committed delta, and pack them into the state and return. The biggest difference here, again, is that we can feel free to pass in CTN and resolve this time to the solver because we don't need to negate anything. And what we can't pass in, or I think I should say shouldn't pass in, is committed. So think about it this way. Both the committed left-hand side and CRHS committed right-hand side there contain all the changes made to the state within their respective solving processes. So if we pass committed into them both, which represents the whole past of the computation, then both will contain copies of committed. This essentially distributes the past conjunction over the disjuncts and yields multiple copies of the same constraints, which isn't technically wrong. But my informal experiences so far have convinced me that what we really want to do is factor out as much as possible from the disjunctions to get good performance. So you'll notice instead of disjunction, or you get disjunction constructor, I use dist factorize there to combine the two disjuncts. And all that does is just normal disjunction, plus it searches all the disjuncts for identical constraints that are common to all disjuncts and factors them out when possible. So if x equals 1, x unifies 1 shows up in every disjunct, then we just write x unifies 1 and the whole disjunction. So the key thing to note here is that we never add the disjunction back to the state. That happens only at the end of the solving process, and that's important. I've been referring to this constraint solving approach as a kind of search, but here's where that actually becomes apparent, because without disjunction, search is kind of a little bit trivial, right? So you can think of what we're doing here conceptually with this whole solver as taking all of the disjunctions out of our constraint store. And this is kind of a naive, simple version that we're doing a little more efficient than this, but you can think of it as equivalent. If we took all the disjunctions out of our constraint store, so now we have a state that is purely a conjunction of equalities, disequalities, type constraints, whatever. And let's imagine that so we have some disjunctions here. Let's imagine that the first line is one disjunction we pull out, and the second line is a second disjunction. Then each disjunct individually is kind of a contained disjunct goal. Then to the extent to say that we're searching these constraints here is basically saying that first we would take our state, we pulled out all these disjuncts, and then first we're going to add disjunction 1, 1 to our state and make sure it doesn't fail, make sure it's consistent. And if it is, we add disjunction 2, 1 to our state. And let's say that fails now, maybe it conflicts with disjunction 1, 1. Okay, well, we back out. It's a depth first mini-Cantor search. We add disjunction 2, 2 to our constraint. And eventually we're going to find one disjunct in every disjunction that doesn't fail. Otherwise, everything fails and we just return failure. And then we can stop at that point if we want and pack all of these disjunctions up without their failing disjuncts into a goal, and stick that in the constraint store, kick it back to the goal interpreter, and get on with the search, the global multi-branch search. The code I presented here, the sort of simplified disjunction code, isn't going to do any early stopping. It's going to search all the branches of everything, but you could potentially stop early. And there are kind of various ways you could do that. And that's kind of one of the big things I'm working with now is exactly how lazy to be and whether it's worth it and whatnot. But if we wanted to stop early, we'd change our last line to something like looks like this. What this is doing is essentially conjoining the continuation, right, all the future constraints, the right-hand side, to the unsolved right-hand side of the disjunction, and then disjoining that with the solved left-hand side. And this is exactly analogous to how the normal mini-Cantor search will bind a goal to an incomplete stream, incomplete right-hand stream, which implicitly conjoins it with all the subsequent answers that stream produces. Right, so we are binding the continuation constraint CTN as the yet unexplored stream represented by the right-hand side of the disjunction. And we also don't need to worry about divergence because fresh or macho in this case is going to stop expanding when it runs out of ground terms before we have to start speculatively binding free variables and such. And with macho, what the pattern matching is, that's very trivial to do. You just check if there are any free variables in the pattern, in the variables you're pattern matching, and then pause if there are. Fresh is a little more obnoxious. You have to check if you get any disjuncts back when you solve it, but you can conceivably do it in an analogous way. And the final thing that we have to talk about are attributed variables. So by which I mean this is the practice of storing constraints in the constraint store indexed by the variables on which they depend. So we only have to recheck a constraint if one of its variables has been modified. So putting x is not equal to y in the constraint store, for instance, will often in many implementations, including previous ones, the previous versions of this code base, will create two entries in our constraint store indexed by x and y respectively, right? And once we solve a constraint, once we solve a constraint, we need to figure out which variables it depends on and copy it to all of those variables in the constraint store. So for most constraints, this is easy. Unifications depend on all their variables, negations and conjunctions depend on all the variables of their children. One caveat there is that since the constraint store itself is implicitly a conjunction of the constraints it contains, if we want to store a conjunction directly, we can just store all of its children independently, and they're implicitly conjoined. And then disjunction is the tricky case, because if we solve all disjuncts as we do in the simple case above, we could make it depend on all its children. But depending on our objectives, we could also get away with less, which is kind of what I'm currently working on. How much of the disjunction do we need to solve / do we want to solve? And then we have to sort of store an appropriate number of disjuncts in the store. So to wrap up this section, those are the main implementation details. I haven't really touched on Fresh too much, like I mentioned, but the pattern matching case is straightforward, mostly because I don't have a reference implementation anymore of the normal Fresh, because I haven't kept that updated with the architecture. So in order, I think we'll probably need classic Fresh in order to like rate the sort of constraint I'm hoping for, like a constraint on that's a relational interpreter. But I'm currently sort of exploring that, like I've been talking about. Let's see, I think this ends at 7:30, so I'm going to skip a discussion of solving levels here. I'll come back to it if people want to hang around, or I don't know how we're doing that. But basically, it's just me kind of ruminating about how lazy to be with how many disjuncts we solve, because we don't need to solve every disjunct to guarantee failure, to guarantee we don't fail. But if we don't solve every disjunct, we have stale variables running around, and that becomes tricky to analyze. So there's just some trade-offs there that I'm currently working through, is the basic summary. I have a few performance benchmarks that I've been keeping that are kind of unofficial. I haven't included them in the paper just because they're not super scientific at this point. But I can just share them here as a general sense of where the code is at the moment for people. So these are benchmarked against FasterMK, which is the implementation that I'm sure many people are familiar with. Both of these implementations are in Shea scheme, so it's at least somewhat comparable in that respect. Of course, there are many differences between them, and so exactly what can be attributed to the constraint differences and what to other random details is kind of requires further analysis. But just at a high level here, so these are a bunch of disequality related constraints, and I'd have to kind of more time could get into like what each one is testing, but it's just kind of a handful of disequality benchmarks. And on the right hand, we have the percent faster than FasterMK, if indeed faster. And the way to read that is that 84 in the middle there would be that FasterMK takes 184% of the time. So positive numbers mean faster, negative numbers mean we're kind of slower. And in this case, disequality is faster in all cases. There are some possible reasons for this aside from just writing bugs in the testing code or something, which is always possible. Just speculating here, but so there are some basic differences in like how the constraint stores are optimized that may come in. So like this implementation stores constraints directly in a substitution, which kind of saves you a bunch of walks. There's no separate constraint store. Since it has a separate unique index for every variable, we only have to store disequality constraints on one instead of both free variables if needed. Things like that. It could also just be that these tests the access pattern happens to be better for the substitution data structure I have in this implementation than the one in the FasterMK, and that a different test would have a different access pattern. But there is one important difference here that I can attest to, which is that there's a slightly different meaning between the way I've implemented disequality here and FasterMK, which is that I've implemented disequality lazily. So if you look at that penultimate test there, laziness, if we check there's a special lazy unifier that I use for disequality. So if we check the first disequality primitive check and that doesn't fail, we know the whole thing won't fail. So I just wrap the list up in its own disequality constraint and return without checking the rest of the list. So whether that's net gain, net positive, long run, still sort of waiting for experience to teach that. But for a simple test, it leads to kind of hilarious numbers that, are just, it's a very, testing a lazy versus an eager implementation, of course. And then Absento, it's a little more complicated. I have two tests here. The first one tests, removing and replacing one constraint by unifying it with pairs with one variable free. And the second one is expanding all the trees in the store by unifying with two variables free. Slower in the first case, faster in the second case. Don't have any great theories about that aside from just differences in the constraint store optimization, maybe handling better the expanding collection of absentos. I'm almost certain that the implementation of Absento itself is not faster than it is in FasterMK, just because it's sort of composed of those three constraints, which is sort of three potential lookups. But just, this is kind of just me speculating. They're just sort of internal performance benchmarks I use to kind of test regressions in the code base. So I don't have any strong claims to make about them, but that's just kind of what I'm looking at. So here it is, and make your own interpretations, I suppose. And with that said, I think we're pretty much out of time. We're a couple of minutes long. Sorry about that. And here's a link to the GitHub. I tried to hastily scrape together some documentation last night that would just basically orient people to using it, but feel free to take a look at it. Let me know if there are any bugs. I'm hoping to sort of maintain this as a sort of fully featured Minicanner implementation for future research, and perhaps for anyone else who is interested in these things, or hopefully can integrate my probability work as well soon and get to work on that. So feel free to look around. Let me know if there are any issues. Happy to answer any questions at this point if we have time, or just call it there, and looking forward to the discussion later. Thank you.
All right. Thank you very much, Evan. Let's thank our speaker. We're starting to get into the break, but I do have a question online from Greg. Question for Evan. Is there support for efficiently checking satisfiability across combinations of, possibly even different types of, constraints? For example, will the system recognize the unsatisfiability of a conjunction of these constraints? Boolean X, Boolean Y, Boolean Z, all different X, Y, Z, for otherwise unconstrained X, Y, and Z. So that sounds like a sort of finite domain type of things, where if you had finite domain solver, you could prove that there's no satisfiability. But would you be able to do that with your constraint approach?
I would have to look at that in print and or possibly run it to be certain. My guess is that there's a good chance that we're handling the kind of thing you're describing, just because of the way that I described the search. What we're really doing is we're looking for some. So in terms of unsatisfiability, I'm a little more confident. In terms of if we're looking for some subset of disjuncts that can all be compatible in the same state. And so we're going to kind of, basically in the limit, just iterate over all combinations of true and false for all the variables you've constrained. And as long as there's some satisfying collection of those, we'll succeed. And if there's not, we'll fail. And then moreover, if we also solve aggressively enough to try to look for situations where we don't necessarily fail, but we can commit unifications. And I've tried to make at least those two pillars pretty robust in terms of if the constraint SOAR implies failure, we should fail if it's unsatisfiable. And if the constraint SOAR implies a unification across all disjunctions, we should extract that and unify it. If there are gaps in the reasoning, I don't know. Please test it and tell me, or please send me a description of a test and I'll test it. But my guess is that probably if it's an unsatisfiability question, we should solve that.
Okay, thank you very much. Let's thank Evan one more time. And we've got 25 minutes until we start the last session, which is on the future of Minicanner. Thank you.
Hello, hello. Okay, yeah, that would fix it. Started. Let's give you my try. We are gonna. Yeah. We're gonna like put a dumps count on this one.
I think we have a couple other people who'll be joining in a minute, but I can go ahead and get started. Hi, everyone. Oh, I guess, okay, yeah. Okay. Hi, everyone. We are about to begin our last session, which is on sort of the future of mini-canner relational programming and what sort of avenues we might pursue for research, implementation, education, outreach, anything else. I don't know. Maybe the whole thing is a bad idea. Maybe we should say, no, don't do it at all. But we should talk about that. I know we have a few people who I think are on their way here. We also might have some people looking online. So I have a Discord channel set up. So the official Discord, and it's under Mini-Canron discussion on the future of Mini-Canron. So if you are online and you want to ask a question or make a suggestion, please use the Discord channel, and I'll check periodically and add your comments or questions. Okay. All right. I think we have a couple more people coming, but I think I'll probably get started in 1 second. Let me just see if those other two people, if I flag them down. 1 second. Mind holding? Okay. We might get a couple more people coming, but if not, that's fine. So let's go ahead and get started. So I guess I can make a couple opening comments. So I think at this point, work on Mini-Canron proper has been going on for something like 18 years. It's been a while now. Or maybe 17 years that Mini-Canron has existed. Before that, there was Canron. Before that, Dan Friedman had worked on logic programming, largely in an educational context for many years. But for Mini-Canron itself, that language has existed for something like 17 or 18 years now. And it's changed over time. Now there are many versions of Mini-Canron and different types of logics that have been implemented. At the same time, I think we've only scratched the surface in terms of exploring this gigantic space. There are many, many types of logics we haven't tried implementing. From a software engineering standpoint, we don't have a modular single implementation of Mini-Canron that combines the different features or all sorts of things with type systems and formal verification and theorem proving and proof assistance and all other things that are close in spirit maybe to constraint logic programming we haven't really explored or have only explored a little bit. And there are also things like modern uses or integration with different types of AI technology, machine learning, neural networks, large language models, and so forth. It's been a little bit of work on that so far, such as the neural guided search paper at NeurIPS from 2018. But I think there's a whole lot more that could be done in any of these areas. We have one sort of really, really interesting example, I think, which is the relational interpreter and the idea that we can take an artifact, like a functional program, and by interpreting it in an interpreter that's written in a relational style, we can inherit this relational behavior. So that's something that seems to get people's attention. We can also do that with type inference, which Kiselyov showed a long time ago, that if you have a type inferencer like this, you can also run it in a way to do type inhabitation and synthesis that way. And you can also do similar things with parsing. One of the big problems that we have in Minicannon and also in Prolog, and as far as I know, all general purpose logic and constraint logic programming languages have, is are conjunctions not actually commutative. We can say conjunctions commutative up to modulo, like modulo divergence versus failure when there is no answer you're asking for. And also in terms of performance differences, reordering conjuncts can have disastrous performance implications. So that's a very serious problem. There have been a number of people who have tried to explore that problem in Minicannon, also in Prolog and other logic and constraint programming domains. One approach is to restrict the language, do something like data log or answer set programming as a subset. But that's one of the problems. And then there's a whole range of research from various people in the Minicannon community as to try to make Minicannon faster with things like staged evaluation, supercompilation, trying to do static analysis, figuring out when a relation is primitive recursive, and do all sorts of tricks. We saw some discussions of that today, along with hand annotation and different types of performance tweaks that people have figured out. So there's a whole range of I should say, obvious things in the sense that they're continuations of things we've already been exploring to some extent. But it'd also be interesting to hear what are areas we haven't explored at all that maybe we should look into. And more broadly, Minicannon still isn't very well known. And can we articulate better what is interesting about this style of programming? Because it's weird. And one thing I found, and I found it during this conference, that I can't explain to someone what's compelling about Minicannon without giving them an hour-long demo. Okay, that was actually why I created Barliman initially, was so I could show to a Java programmer what's interesting about Minicannon without spending like 3 hours explaining lambda calculus to them or something like that. So that I think is also an issue. We have 2 books, 2 editions of a book. We have various papers and theses and online and tutorials, but at the same time, we're far from having mainstream materials to teach people how to actually do this. And most people, even who know functional programming or logic programming, they maybe have heard of Minicannon, but they haven't used it, that sort of thing. So that's another thing I've thought about a lot. How do we teach people how to use this? How do we show them what's interesting? And what is interesting about Minicannon? Is it a one-trick pony? You can write a relational interpreter and that's it? Or is there sort of a grander vision of this? Okay, so those are just a few opening thoughts. I know people like Evan have a grander vision of what you could do with the system, or Greg have a grander vision of what you might be able to do with such a system. And I will say that there have been some real world use cases, such as the threat grid system in core logic, and at Precision Medicine Institute, Hugh Precision Medicine Institute at University of Alabama, Birmingham. Greg and I and other people have been working on Medicannon. Greg's implemented DBcannon, which is a graph database system. In all these cases, we're using mini-canron or a variant of mini-canron, not exactly like Prolog, but more like Prolog or Datalog or things like that, in a more pragmatic way. So maybe in practice, there's going to be some mixture of pragmatic uses that are more like Datalog or answer set programming or things like that, and then also some this longer term project to try to make the relationality weird. It's already weird. To make it real, to make it more practical. Okay, so there's like this kind of long term vision. Oh, what if we could write everything as relations really? And then there's a shorter term thing like, well, what about having a practical tool more recently, and maybe you have to use extra logical things like Conde or Condu, or use restricted versions of language for answer set programming or Datalog. So, okay. So those are a few things to think about, but I'd like to open it up to discussion, either people online through the Discord channel or people in the room, some of whom have all sorts of logic programming and functional programming experience. Actually, I think everyone in this room does. Does anyone have anything that they would like to share or ask questions about or think about for future of mini-cannon relational programming?
Questions. So I have a few questions. First,
can you give your name?
My name is Yafei. So okay.
The camera for the live stream, hello, is up there, and also this will be recorded for posterity on YouTube. So
Okay.
yeah.
That. So my question about this. So my first question is, because mini-cannon, its core its idea, its implementation, its first implementation is so simple. So because it's simple enough, so people could understand it, and everyone could implement their own canons, their own version of mini-canons, and this is good in one sense, but in another sense, because it's so easy to implement, there are so many different implementations in different languages, and every kind of implementation, more or less, they are a bit different from each other. So my question about this is, since there are so many different implementations and maybe they have different features, so is there some way that different people can communicate, different implementers, they can communicate with each other about those different features in a better way? Because they all extend it in some way, but maybe they all extend the carry in different aspects. Yeah. And that's one of my questions. And my second question is about its use. In fact, I'm looking forward to seeing more how people can use mini-cannon. We can have powerful interpreters, and we can use this to solve some logic problems. But I'm still looking forward to seeing more use of mini-cannon. And I'm really curious how people can use them to solve more problems, other problems. But this is something that I cannot figure out for now. And so speaking of this, so the verse, we can see that yesterday, the talk about the verse, it attracted so many people. So, but it's also kind of logic program language. And so in that talk, people, they also asked, well, why do we need this verse language? And I think if verse can do that, why we cannot use mini-cannon for all of that kind of thing, right? Yeah, that's my question. Yeah.
Okay, thank you. So I had a couple questions there. I was wondering if anyone has answers to some of those questions. I see, Jason's here. Jason is largely to blame for the fact that everyone who's ever used mini-cannon has at least one implementation.
So, and by the way, I see that kind of as an offspring of the Scheme heritage, where my friend Aziz said that he thinks Scheme is the most implemented language of all time because everyone who learns Scheme ends up implementing Scheme at least once. I mean, I've implemented Scheme probably hundreds of times at this point, and so that's sort of the tragedy and beauty of Scheme is that there are literally many thousands of implementations. At the same time, there are only a few implementations that have all the bells and whistles and engineering and so forth. There may be maybe 5 to 10 really actively maintained implementations. So that, I guess that might be one way you could look at mini Canron in the future, is that there'll always be a micro Canron where you could implement it in an afternoon and really understand what's going on and hack it. But at the same time, we probably need bigger systems. Probably the biggest systems that have existed so far would be core.logic enclosure and also maybe C-Canron. Claire Alvis at one point had been building out C-Canron with a whole bunch of different constraint solvers and so forth. I think it's a real challenge to integrate all of the different logics and solvers and techniques within a single implementation. I also think it'd be worth trying, but I'm curious if anyone else has thoughts on this issue of proliferation of implementations and so forth. Come on up if you have a thought. Okay, please introduce yourself and please keep the mic near your.
Okay. Hi everyone, Xiang Yu again from Arizona State University. So quick answer to the question about why we have so many different languages, right? PHP is the best language in the world. That's a simple answer. But if we go into a complicated situation, it's like, okay, different people may have different beliefs, understandings, aspects. That's why we create a diversity in the world. So basically just like a gene in your body, the mutation, if we allow like the varieties of the different things out there, we give it more chance. Like some gene may be mutated into some like very good variations. And people will start like, okay, look into that implementation, take some ideas. That's why like Java, right? Taking the lambda calculus finally after 70 years. So simple answer is like PHP is the best language in the world because people are always arguing about like, okay, this is my approach, mine is the best, you are bad, kind of this. So this is one thing. And the other thing is like from the Bible, like also like in human world, we have different languages, right? If we all of us speaking the same languages, we build a tower, go to the sky. So that's probably another reason why we have different implementation. We cannot unify into one thing because otherwise we just conquer the world. So yeah, just my thoughts popping in my mind. So it's good, like Will mentioned, maybe in the future, one system has absorbed into like more and more things. We improve the expressiveness because the ultimate goal is like, okay, the fully declarative, right? Go to bake a cookie and computer will do the rest for you. You figure out the recipe, what's the flavor you like most, what's the temperature, and then just start executing, serve the cookies. That's our ultimate dream. But currently, I believe we can only slavery some people to do that. That's the best AI out of the world. Like, okay, there's a human being right next to you. So, yeah, hopefully this is our big dream, right? That's why we have a workshop. We gather together. We want to extend this system, add more expressiveness into there, improve performance, and maybe 100 years ago later, the AI will say, okay, this is one of my ancestors built me. Yeah.
Thank you. Anyone else have a thought on pros or cons of having many implementations? Or, I guess I could turn around and say, what should we do either as community or individual implementers in the future, or researchers? Should that be a major direction of research in the future, trying to combine all these different techniques into one? Dimitri had talked about in an earlier talk about having one Uber system or giant system that had everything in it. Is that something that really needs to happen? And maybe we could coordinate a whole bunch of people to try to make that happen? Or do you think it's better that at this point, at least people just kind of experiment on whatever they find interesting, and maybe someday the pieces come together, but if they don't, it's kind of, that's fine. Maybe it's more like an idea language. Come on up.
I'm Walter Schulze from, well, let's say Go Mini Canron. And I think, yeah, it would be nice to have a uber fast optimized mini Canron, right? But there is still value in the mini Canron that's implemented in all these languages. So if we start thinking about very senior engineers, right? And we also think about junior engineers learning how to program in verse. And how they're going to come from verse with all these logic programming constraints to more mainstream languages and go like, what the fuck? Why can't I just do a equalo disjunction existo fresh variable here? Like, and it's going to be hard for the senior engineer to really understand what they're, because they have not had any exposure to logic programming. But if by learning mini Canron in their own language that they're familiar with, they can bridge the gap between this junior engineer who's come from logic programming being second nature to them like having to learn something new after 30 years of programming. So, yeah.
Thank you. So you're suggesting that after people learn verse, they'll move to a mainstream language like mini Canron. I think that's a good idea. I actually do hope that it's possible to sort of piggyback onto the verse train, and so we can have, kind of ride the coattails of, Epic and Fortnite, all those Fortnite skins and downloads and DLC and stuff. We can piggyback somehow on that infrastructure. Well, we'll see. It'd be cool to be able to compile to verse, for example, compile mini Canron to verse if that'd be possible. Or maybe this would be similar to, what Kate was showing, where do mode analyses and whatever. There may be large subsets of mini Canron. In fact, I think there are. I've been talking to verse people quite a bit to try to understand better the design and the future of it. I think there are large chunks of the types of programs that we have written where at least in certain modes you could compile directly to verse or verse calculus. And, hopefully they'll end up with, a top-notch, really efficient implementation. So that might be a compilation target. That might be worth exploring, sort of like what the WAM did for Prolog and the JVM for a bunch of languages. Maybe, you can look at verse as, sort of a compilation target. That might be neat. Okay. Any other thoughts on where we should go implementation-wise, or the size of implementation, the complexity, or any of these other things? What was the second question? I got fixated on the first question. Oh, okay. What are other uses? Yeah. Okay. So this is one that comes up perennially. It's like, okay, this is cute. What are you going to use it for? And so you can use it for different things. You can use, mini Canron for learning how to implement mini Canron. Okay, so that's a great use case. You can use the tried and true, sort of like the great thing about functional programming languages is you can use them to implement a compiler for a functional programming language, right? We're, maybe like that, except times 10 for mini Canron in a way. You use mini Canron to write an interpreter for scheme in mini Canron that then you can implement mini Canron in. That's actually my goal. So those are the sorts of things that maybe even worse than sort of the functional programming curse. But it's certainly the case at this point that people have made a lot of money using mini Canron, or at least the core logic version. The amount of money they've made is secret, but I suspect it's on the order of $1 billion. Whether or not that was the right language for them to use, well, they used it and sold a startup well. So people have made money, but it was always in the context of something very pragmatic, core logic, and had sort of relational things in it. But they could always get out of kind of the core language. This is true, DB Canron for MediCanron. That is not 100% pure, and it's also more restricted in ways, more like a data log in some sense. So, I think there are lots of uses of more restricted languages, or where you have an escape hatch and you don't have to be 100% logical. Maybe that's one reason that the MediCanron family has had some success, is that if you're embedded, then you can always escape to the host language. And then, if you look at the optimizations Greg added to Barlaman, he's escaping to Scheme and doing all sorts of things there that you wouldn't otherwise be able to get away with. So the fact that we're embedded in a host language in almost all implementations might be a great benefit in a way. And I think this is maybe one thing that's held back Prolog more recently, is that Prolog's not a particularly popular language these days, and you can write web servers in Prolog, but most people probably would want a web server in another language and then do the logic-y stuff in sort of a subset. So I think that's a sweet spot for MiniCanron. But I am curious what people think about other sort of use cases or the direction that MiniCanron research and development should go. Should we try to be more pragmatic? This is a thing that came up in the Scheme community as well. Right, so there were things like R4RS Scheme standard that very much wasn't a pragmatic thing, and then R5 became a little more pragmatic. R6 arguably became more pragmatic because there was a much bigger spec and more libraries now. You actually had libraries for the first time, and then R7 Large is trying to do that even more. But at the same time, the success of Scheme is partly because there's a tiny core language anyone can implement and understand. So it's got all sorts of teaching, educational aspect. There's also, it's a hacker's dream. You can hack on Scheme implementations all day long. And you can also, hopefully do programming, more sophisticated programming in large and commercial uses. There certainly have been uses of those. But it's hard to have the same language satisfy all the different users, right? And so MiniCanron, I think, has a little bit of that issue. There's educational uses. There are things like, microcanron, like, hey, here's 50 lines of code. And then there are things like faster MiniCanron or ccanron, which are much larger and more complicated. And then there's forget the whole relational thing. Let's just be pragmatic, like core logic, where you add a lot of features that are more like Prolog extra logical features. And so those do feel like different things to me. And so maybe that is the reason that we should keep different implementations and not, if we're going to have an Uber implementation, maybe we have an Uber research implementation. Maybe we have an Uber pragmatic implementation. I don't know. Anyway, thoughts? Come on up. Please introduce yourself and keep the mic near your mouth.
Hi, Lisa Zhang, University of Toronto. This might go in the opposite direction that you're trying to lead us, but this might also relate to some of the earlier questions. I'm just curious about what your thoughts, Jason, other folks in the room, what your thoughts on what exactly is a canron, and whether there is agreement in the community about what constitutes a canron.
I believe my name was called, so I get 60 seconds to respond. Jason Heeman, Seton Hall University. Let me try and throw out what I got on both of those in order. What direction should the MiniCanron community go? What are we adding of value to other communities? And then maybe what makes a canron in my view lately. I think one of the big benefits that we've got is a really nice sandbox to play in. it's a nice sweet spot of an implementation that you can hack on and get really good performance out of. That's not to say that all implementations are eminently hackable or that you get really good performance out of every one of them, but there's a nice spectrum of if you've got an idea and want to see how it works, or if you need just a little bit of logic programming for stitching together whatever other thing you're working on, this is a good repository of knowledge and a community that knows how to get some of those things done. As I'm thinking about what people are interested in doing in the LLM space, I've seen a couple papers now recently on, man, it's sure great to have constraint logic programming available to help either explain or describe what's going on with my LLM answers. So I think some of it is having a group of people and a place to play. Some of the things that where do we go next would be, I think, making sure we keep a clean sandbox. That the things that we know how to do, that somewhere that's organized and archived and made available. Will had talked a while ago about, I guess, a series of like tech reports for here are the things we know how to do in Minicannon. Here are the things that we don't know how to do and don't quite work. And I think having that kind of repository available for, you've got an n-dimensional matrix, here's as many of the spots as we've explored, would be a good thing to have, so that when the next idea strikes or the next person wants to come and grab it off the shelf and do something with it, it's easy and eminently available, as opposed to being difficult to hack on in other spots. What it is that makes a canron particular, my answer has been an interleaving depth-first search and symbolic constraints. Our style of symbolic constraints. That's not to say nobody else gets to be a canron. Another answer is whatever the people in this room are working on implementing. There's a sociological or historical answer, but if you wanted my answer to scope out the core of the technology, that's what it would be.
Thank you. I guess my take on what a canron is, it's somewhat ill-defined, but Minicanron originally started as a teaching language for students at Indiana University who knew Scheme. And so that's why the syntax looks like it does. That's why fresh looks like let. That's why cond looks like cond, things like that. So there is, for good or for bad, kind of this baggage of sort of a tradition of where things came from. I think another thing that makes a canron isn't so much the syntax, but it's more this idea that we're going to try to simplify the language to focus on purely relational constructs. So if you look at the first edition of the Reason Schemer, there were two versions of cond. There was cond and condi. Condi was the interleaving version. There were two versions of equal. There was equal without the occurs check, which was the default, and equal with the occurs check. There was all and all I, so interleaving conjunction and non-interleaving conjunction, which meant that any person who is writing a program with a disjunction, a conjunction, and a unification had 8 different ways of writing their program, and it was a mess. And so over time, we simplified things, made it more general, and we defaulted to the more general operation. So we always use the occurs check for unification, even though it's more expensive. We always do the interleaving search, even though it can be more expensive. And so now it's sort of like going back the other way. We went general, and now we're trying to think, okay, where are cases we can be more efficient? Maybe we can use a depth-first search in some places. Maybe we can get rid of the occurs check, but we defaulted to the safe and general approach, which is the opposite of how Prolog did it. Prolog was much more about performance, which makes sense from a language from the 70s. And it was also much more about controlling the search, which makes sense given the AI context, the search-based AI context in which it was created. So we made different choices. So the way I see it is every once in a while I'll meet an experienced Prolog programmer who will look at miniCanron, look at what we can do, and say, you can do that in Prolog. There's nothing new. You can do it in Prolog, and that is true. However, by the time you're done making it work in Prolog, you've basically turned Prolog into miniCanron, to do those sorts of things. And the fact that we tend to give real emphasis to the relational aspect of things. So even if you do use a conde or condu, the way we teach things, that is sort of the exception to the rule normally. That's the sort of thing that you would avoid. If you really had to, maybe you would use one every once in a while. The Prolog people try to avoid cut often, but for us, we have a much stricter notion of what we consider a non-logical thing. So we, anything like copy term or projection or things like that, we also consider non-relational because it inhibits the ability to run backwards. So I think we're much stricter. We have a much stricter way of looking at things, sort of like, someone approaching scheme from a functional standpoint has a different view of how you use the language than someone approaching scheme from, this is a multi-paradigm language and I'll use, mutation and, whatever. So it's just a different point of view. Okay. All right. We got another. Oh, okay. All right. We have a question online from Evan. Okay. All right. I'll give my computer 1 second to wake up. Otherwise, I will ask someone else to read the question. Anyone have the question I can share? Okay, come on off. Oh, here we go. Okay. All right, here's Evan. Evan said 9 minutes ago. Sorry, Evan. My 2 cents is that it would be interesting to try to discuss how complete a miniCanron one could assemble from the various improvements made to individual implementations. The ability to hack specialized versions of MK is a great strength, but I frequently find myself wishing whichever implementation I'm using had features from some other implementation, and my own work has trended towards trying to create a more featureful implementation, which has driven some sometimes very interesting developments. I'd be interested in having a conversation about what a megaCanron would look like at the very least. Okay. Moreover, my experience so far has been that sometimes you reach a phase shift and the more complete version is actually as simple or simpler than the simple version, which sort of happened with this constraint system talk. Okay, Evan's referring to his last talk on using goals as constraints in miniCanron. And I think Evan's right. I'll give you an example is if you have something like nominal unification for nominal logic programming, which we borrowed in Alpha Canron from Alpha Prolog, or you can also look at Alpha ML. So if you look at that sort of system, that gives you capture avoiding substitution and other things that are useful. And if you don't have that sort of unification in your system, well, then good luck implementing some of those things. You're going to have to do all sorts of encoding tricks or De Bruyne notation or something like that. And it gets really tricky to encode certain things. So sometimes having a more complicated system, sort of makes your life easier overall. And certainly one of the Achilles heels we've had with miniCanron is you want to do program synthesis via a relational scheme interpreter, no problem. You want to add 1 and 2, have a seat. We need to have a discussion, right? That's kind of the way it's worked out. And we have implementations of finite domain solvers and arithmetic systems of various types and delay goals and all sorts of things like that, and constraint solvers and calling out to SMT solvers and everything you can imagine, but they're all in disparate versions, and none of them are in faster miniCanron, which is the implementation most people are using, at least in the scheme community for research, or in OCanron. As far as I know, none of those features are in OCanron either. So the 2 big research implementations don't have any of those special bells and whistles. Okay, so I agree with Evan that it would be nice to have, nice to be able to write an interpreter that could do addition. That'd be awesome. Okay, and especially if you want to do something like probabilistic logic programming, that becomes important. Okay, other thoughts? Or what would a megaCanron? Okay, I mean, okay, so here's Evan's question. What would a mega canron look like? What would we want in a mega canron? I know some people here have opinions because we've talked a little bit about, bigger systems. So don't be shy, please. Yeah. Oh, yeah. Okay, here we go. Walter said, wouldn't it be kilocanron? It wouldn't be because we don't have a millicanron. Okay. Okay, well, nanocanron, exacanron. What would an exacanron look like? One of my friends is building a supercomputer, RISC-V supercomputer with 1 million cores on it that fits in a single rack. And so I want to run minicanron on that. So what would we do if we had 1 million cores and ran what was that? Gigacanron, yeah. Sounds like something Elon Musk would do. Yeah. Okay. Well, what would you want to have in a mega canron? What would that look like, and how would you go about doing it? Like the SMT people have kind of figured out how to combine theories, so that's maybe something we could copy off of. Okay, but are there other approaches or other things you could think of that you would find useful, either from a research standpoint or pragmatic standpoint, in a mega canron? While you think about it, I'll tell you what I'm thinking. I think I've already said I really want a system where, first of all, we have a modular design. We actually have modules, right? So that's one problem with minicanron right now. So most of the implementation, at least the scheme versions, we don't really sort of modularize things well. But I want to be able to do things like in Chow Prolog, where you can have different searches for different predicates or different relations. So I want this to be depth first search, or I want this to be breadth first search, or this is IDDFS search, or whatever. Okay, so you should be able to parameterize things by search. Right now, we don't have a way of doing that other than going in and hacking a low-level way. So that's an area where we're lacking modularity. And sometimes you can get away with the depth first search because something's finite, and you really should take advantage of that. Another thing is having different logics. Olin Shiver says always use the most, always use the simplest language you can get away with, or the most restrictive language you can get away with. So if we can do something in Datalog, we shouldn't be using full minicanron. If we can do something in answer set programming, we should be doing that. So there's no reason to go to full minicanron for everything because it's very hard to reason about. We don't have termination guarantees or complexity class guarantees, things like that. Another problem we have is we're not doing environment trimming. So as soon as you shove something into the substitution, it never goes out again. Okay, so we don't have the equivalent of garbage collection inside of a substitution. That's an issue. Another issue is, from an implementation standpoint, I think we could probably make another try at getting away from triangular substitutions, which are nice in a way, but union fine has advantages, and composing substitutions has advantages. I think that's something worth exploring, and different representations. Another problem is we only have really one data structure in the scheme version of minicanron, which is the pair. So we have atoms and we have pairs, and while pairs are very useful, we don't have vectors. In fact, vectors are usually reserved to represent logic variables, and we don't have records and things like that. We don't have sets. Okay, I would love to have sets. There have been times where I tried implementing like parts of TAPL, and then immediately I needed sets. And so I could try to represent sets as lists, but there are all sorts of issues with that. Also, constraints, various types of constraints. I would like to be able to say in this part of my program, I want to have nominal logic constraints, and nominal unification. This part of my program, I want to have finite domain constraints. This part of my program, I want to call out to an SMT solver. Or this part of my program, whatever. Another thing, speaking of solvers, it'd be really great if we could incorporate SAT and SMT solver techniques within minicanron implementations right now. So Nada Min and Michael Ballantyne and other people have done a lot of work trying to get minicanron to call out to SMT solvers, and we can get it to work, but there's this huge impedance mismatch based on the type of the search and other issues, and you have to call out to this external process. And also, SAT and SMT solvers like it when they have all the constraints up front and they solve them all at once. But that's not how we do things with mini-Ken search. Instead, we're incrementally solving things, and we hope to cut off the search space so we don't have to keep going down. And we can also handle recursion nicely, whereas SAT and SMT solvers, you sort of have to unroll things generally. So if we could implement those techniques inside of mini-Ken search, I think that would be great. And also there are techniques like back jumping. But if we had conflict-directed clause learning and unit propagation and all those sorts of things in a high-quality, high-speed mini-Ken implementation that supported other data structures and other constraints and were modular and had, things like data log subsets and answer set programming subsets and all that, that would be a very sophisticated system, especially if they're integrated well with the host language, Scheme or OCaml or Haskell or whatever it is. I think that would be a language that would both be a very good research vehicle and also a pragmatic vehicle for people who are doing, declarative programming and constraint solving. I think that would be nice. And so we could look at things like Zinc. We could look at things like Flora 2. There's a whole bunch of systems we could look at and draw inspiration from. To me, that is what I would like to see in a mega-Canron. Anyone else have a vision of what they would like to see in a mega-Canron? You must have an idea, Jason.
My vision is much more narrow than Will's. I'm Jason again. Will's vision, to me, sounded kind of like Canron the conductor. There's the Canron up there, and now you SMT some stuff, now you answer set some stuff, now you stable model some stuff. I guess my vision of it was maybe slightly different. I was thinking of the Canron being the shop that you go pick stuff off the shelf out of, and if I choose to combine these sorts of theories with this kind of search with that sort of domain, I happen to know what kind of properties that we get out of it as a result. So you go down the shelf, like one of those, or yeah, like a Subway or something, like one of those, one of those, one of those, one of those, and then they ring you up, and at the end you know exactly what kind of properties you get out of a system. And yeah, the mini Canron App Store. Yeah, that's what my Giga Canron does. Greg, are we just calling people out the audience now, Greg?
Okay. All right. Well, maybe we'll hear more about mega Canrons later. Well, I'll throw out another question. Who has tried using some variant of mini Canron in Anger for a real production system? Not writing quines or generating append, but to actually get work done. Okay, there. I know there's someone else in the back who's not raising his hand, but okay. If anyone's willing to share their experience, now, I guess part of it's also tangled up in, if you're using it in Racket, say, it may be hard to separate your view of using Racket versus mini Canron and so forth. But if anyone has views of that, I will say that in as part of this biomedical data translator project, we have been using DB Canron, like on the 5th generation of DB Canron or something like that, written in Racket. And so it's sort of a loosely inspired by mini Canron and inspired by Datalog graph database, where you can write data, Datalog-ish queries and so forth. And we've been using that for precision medicine, for case reviews and things like that, and tooling. And it works. It has some nice trade-offs in that, once again, it's something that's hackable. And it's, we didn't have to use, or we chose not to use things like Neo4j. There are other graph databases out there. We didn't use RDF databases and so forth. We rolled our own. And I guess that's one nice thing about something like Canron or mini Canron is that, you can sort of riff on it and go in different directions. That's not a problem. I know that there was someone who wrote for his PhD thesis in naval architecture, used a version of mini Canron, I think, in Python for a constraint, sort of as a front end for constraint solving, that kind of thing. One thing you could imagine for the SMT solving is like, mini Canron sort of as a front end for SMT solvers. That's similar, I guess, to Rosette in a way. So Rosette's kind of this racket DSL that's a front end for solvers. So you can imagine mini Canron being used that way. But in any case, if anyone's willing to share their perspectives, that's fine. If you're being mic shy, that's also fine. Oh, okay. All right. Lisa's going to ask a dumb question. Oh, okay. So you're trying to understand Jason's analogy is the App Store versus the conductor model. Okay, so I can tell you what I don't agree with Jason that I have the conductor model of Mega Canron. Okay. Okay. So to me the conductor version means there's this giant Mega Canron that's in charge of everything and it delegates things. I'm talking more like the programmer is choosing, or maybe through a static analysis, or maybe some lightweight annotations or things like that, there's some way of specifying this relation really is data loggy, or this relation really can be, or these sets of relations, or this module really fits into ASP. And so it's more like we have a bunch of different implementations of mini Canron. We have sort of the fully general one, which is actually the one you never want to use if possible. And then you have the highly specialized ones that are much more restrictive that you hope your problem will fit into. It's sort of like if you had a problem that really is truly regular expressions, you don't want to use Java, raw Java. You want to actually use like a regular expression library because, if you convert, this to DFAs or whatever, there's all this great theory about complexity classes and which operations you can perform and termination and so forth that you don't get from general Java programming. You can compile it to be really efficient and so forth, and you can reason about memory usage and so forth. And similar with data logs, similarly with answer set programming or whatever. So if you have a special class, or maybe you have a subset that's SQL-like, okay? If you know that parts of your program can be very restricted, when parts of your program can use depth first search and things like that, it's more like either the programmer decides to implement things using those subsets, or the system can maybe prove that certain subsets can be used. Or, like with data log, you have syntactic restrictions, okay? And then having that within a whole system. So it's not like this big mini Canron deciding, you do this and you do that. It's more like you have a system that is composed of different logic languages, and but they work together in such a way you can write an application that has 7 different logics in it, 7 different fragments of logics, and they all work together okay. And you have different searches in different places, and it all just works, and it's not a problem. That's what I'm thinking. So I guess I don't think as a conductor. I think it's more like you have a whole bunch of different DSLs that integrate well together. But as far as the App Store model, I'll give that to Jason to explain.
This isn't worth standing up for. I'm going to stop taking the mic. I tried another way. I guess my vision was a whole lot of options to produce a homogeneous language rather than the kind of heterogeneity that Will was describing, I think. All right, somebody who hasn't talked for a while. Katia? As a prologuer, maybe can I get some outside thoughts? If you please. Sure.
I'm Katya Komendanskaya, and I'm in Britain, in 2 universities now, in the north and in the south. So I head at Watt and Southampton. well, I'm not quite Prolog either, so I do logic for computer science. When I was listening to you, I was thinking, because I know logic and I like logic programming, relational kind of stuff. I go to different communities that do relational programming one way or another. I examined the thesis by Dale Miller, and so there is obviously LP recently coming out of Lambda Prolog. There is Prolog itself, but I'm mainly thinking, when I think about canon, I think about it in relation to languages like Lambda Prolog. So I kind of separate out Prolog, which is clearly first order, and let it compete with SMT solvers, with languages that try to be logic functional, have Lambda on top of relational reasoning. So ALP seemed like an exercise until they worked out that it's extremely useful for SS Reflect and for building up hierarchies. And now it's suddenly, there's a big French community of Coq people and those who build all those nice libraries suddenly say, oh, great, so ALP is useful. So this is one way for such a language to go, is to say, okay, there's a niche for me. This is something that no Prolog, no SMT solver can do, because you have libraries in Coq and you need both relational and higher order. And then you find this sweet spot, and I think this is how, for example, LP is gonna work, right? So there is no Lambda Prolog. No, I don't know anyone who's using Lambda Prolog for everyday work. But they found a niche, and this is one way for these languages to survive. And this is actually, this metaverse is the same story, right? They found some kind of cool application, and then they're gonna say, well, here's what it is. So you want to have like big label. So this is where it's cool, and then use this as a reason to develop the language. And Miniconron is different, because it's not trying to say I'm the language for this. It's trying to be a language so on its own. And I think that's where that's how this conversation comes. How do we survive as just a language? Whereas generally these languages of this kind are struggling to survive on their own. But SMT solvers made it, right? So there's genuine need for languages like this. And I'll tell you maybe a different story. So this tutorial that was running parallel to you, unfortunately, on neural net verification. We were thinking what to do with neural net verification. The SMT languages are very bad for talking about neural nets, because neural nets are functions and you want to have good abstractions, vectors, etc. So my team ended up implementing in Haskell a DSL to reason about neural nets. And then we ship queries to SMT solving, well, to specialized SMT solver for neural nets. And there's so little that actually you can do if your high order DSL links to SMT solver. You restrict yourself a great deal, because so many queries cannot be handled. You cannot nest quantifiers like this. You cannot have nonlinear expressions, because they cannot do nonlinear real arithmetic, etc. So there is definitely, for example, for projects like this, for applied projects, there is a niche. I think if there was a stronger solver, maybe more high order solver, or people ask like, oh, if you've proven this for this region and then you have a higher region, maybe you could prove that you don't need to reprove everything, because you could just compare regions. There are clearly some kind of high order problems that could be automated by something that is stronger than SMT solver, or more abstract than SMT solver. And that's again, we're lacking this kind of languages. SMT solvers want their niche, and we have functional programming, but there is, as someone who's trying to apply these languages in practice, you often see instances when you want some kind of language in the middle. It's just we don't really have them as freely available as an SMT solver to connect to. So take encouragement from this. You are needed. I think it's maybe for us, for all of us, is to find better ways to persuade people that there is something that we offer that's unique, that SMT solvers cannot do, that Prolog cannot do. And that's why I mentioned LP at the start, because they found something, it's nice to have a few use cases when I say, well, no, you can't do this with SMT solving. You need a little bit of a higher order stuff to do more. So LP, yeah, that's the ELPI. Yeah, it's a dialect of Lambda Prolog. There was Lambda Prolog implemented. ELPI. ELPI. It's yeah, they, I don't think they themselves implemented this, but they had a very bright student who re-implemented Lambda Prolog, ELPI, and then moreover went and said, I will also use this to help Coq with connecting mathematical hierarchies, which suddenly said, oh wow, you certainly couldn't do it with the SMT solver because it's too low level. And so such use cases really lift. But LP is easier, it's just language that's only used there, and you're much bigger than LP, and but you're not as used, say, as SMT solvers, and so finding more users, if you like, being a bit more public, or maybe find a few very cool use cases will help you. Yeah, yeah. Yeah, it's yeah, they improved high order pattern matching, and yeah. So it's absolutely clear for me that such languages are needed because they get reinvented. There's ELPI, Lambda Prolog, this now Metaverse. They get reinvented because there will be problems that cannot be done with crunching things like an SMT solving. But it's just your problem is that you're trying to survive. There are so many similar languages that are just for this application, for this use case, and you want to be a language that just lives its own life. I think that's where difficulty is much easier to survive as just a niche, one niche language for something, and then to be like 17-year-old language that wants to live 20 more years, or not 200 more years. What's your ambition? Yeah. Yeah, no, go for some cool project, I don't know, like large language models or something.
So I'm Jeff, and I work with Will and Greg, and so I've been thinking a lot lately about what is scheme, and what different people say scheme is, because I think it's a thing that you can't get by going to one source and saying like, what do you think this thing is? I was talking with Andy Keep last night about what he thinks scheme is, and I think what I see people do is I see people mean there's two. It's like a thing that if you had to write a dictionary definition, you have to at least have two definitions. And definition number one is the thing that is trying to be described in the standard, or that the standard is trying to approximate, right, over successive RNRS. But there's this second, and I'm not saying there's only two, because there's a bunch of different things. Certainly in the top few, there's another definition of scheme, which is it's a physical incarnation of the lambda calculus, right? It's a generally accepted set of encodings of lambda calculus and lambda calculus-like extensions, and that's what people often mean when they say scheme. Like I refer, for example, to the Lambda Ultimate Recursive Knowledge, I think, talk from yesterday or the day before, right? Like they called the thing scheme, but you look at what they're doing and it's like, no, we're generalizing the capabilities of zero knowledge proofs with lambda calculus. And we're going to call this thing scheme, but it's sort of a misnomer. It's like, well, it depends on what you mean by that. So I think for, what is a microcanron, like that to me is like sort of this kernel minimal thing, right? And where I feel like the places to answer Will's question about like, have you used, minicannon and anger? Yes, totally. And where that happens for me, my personal sharing that, I can work is like, Greg is trying really hard to make his little corner of megacanron-like corner. And I feel like I want like the kilocanron version of that, of like, if I could just escape this like n times k joining thing for getting my biomedical data through with some stupid hacks, right? Like I'm willing to accept stupid hacks. Like I have a paper that I'm going to present tomorrow that's sort of like I would file under stupid hacks in some sense. And it's like I'm willing to accept a lot of like less fancy things if I have some knowledge about like the data that's flowing through stuff. And you know, I'm willing to, you know, if I can't have a query optimizer, that's okay. Like I'm willing to sort of do some busy work to guide that search. And if what I have to do is just like fight with really big constant factors, it makes it feel sort of like a self-defeating proposition. Like if you just don't know what's in the data at all, and you're trying to like get your query to run, and then table scanning, like is, you know, like I remember trying to figure out what was in a certain database and table scanning and figuring out that like, you know, the table scanning speed was so much slower than just like writing manual code. Then it's like, okay, it's hard to break down the problem. And so I guess like I look forward to, you know, okay, Moore's law is over, where the hardware going forward the next 30 years is not going to look like the hardware going backward 30 years. And like when we have the million core machine that strangely has only two terabytes of RAM, right? Like that seems like a small number, right? So like, how are we going to pack things into that machine? And in that space, I feel like there's opportunities for finding big wins on you know, some space of problems. And like, to me, it's not about, I don't know that there is like the one ring to rule them all flavor of Mega Canron. Like we can certainly build very ambitious versions. I don't know that like even among the concerns that have like already been explored, like putting them all into one thing is really like, I don't know what that would look like, or if that, I don't even know. I guess I would assume that that's like a non-goal. It was my sort of general sense is it's not one, there's not only one dimension, there's many dimensions, and we know how some of them recombine and not so much others. So I don't know. End of my stream of consciousness.
Thank you. A couple real quick thoughts. One is, it is true that we aren't a specialized language with a specialized application. And, you know, so Prolog was kind of this big language. I mean, it is this big language trying to be general purpose. Lisp, you know, is trying to be general purpose. In the functional programming community, I think we accept that at this point, functional programming, you know, can be used for all sorts of computation. And it may be like the, was it the FIP stuff yesterday, where it's like in place updates, and you know, we may have to use lots of engineering tricks to make the functional programming efficient enough or to do low level enough things. But we accept that we can do in general systems programming and functional programming and things like that. You know, with logic programming, other than Prolog, I don't know of any language, maybe with the exception of Mercury, where you can do general programming, systems programming, and things like that. There are things like Curry, which are functional logic languages that maybe are closer. I don't actually see Minicanron right now as a functional logic language. I think we're just a logic language embedded in a functional context, and you can kind of go between them. Maybe if we had a better integration of the functional aspects, you know, if we did more like Curry or Verse or things like that, then we'd have a language that's more pragmatic and that you could actually use for sort of systems programming. Alan Kay once said that, you know, he made fun of Prolog because he said, "What good is a language that you can't write an operating system in?" And that hurt. You know, I was like, oh, I took that personally. But he also said that, you know, there are languages like concurrent Prolog that you can use for systems programming. And, you know, 5th generation computing project, they had KL1, this kernel language that they could use. They wrote an operating system in it, and, you know, they had custom hardware and all those sorts of things. So there may be variants that we can explore that would be interesting. You know, my hope is that even if we have special use cases, which I think we should look for, my hope is that we don't only end up being this sort of niche language that has one application, be it relational interpreter, be it, you know, use as a proof assistant or whatever, that we do keep also exploring, in addition to specialized applications, kind of getting to the goal that someday you actually could do things like systems programming. Maybe you have to modify the language, maybe you have to extend it. there are at least two ways of going about programming languages research. One is starting with this tiny, tiny core that you know you can be efficient. You have a very particular problem in mind that you're trying to solve. You can optimize it and reason about it easily, and that can work really well. And then the other approach is say, hey, we're going to try to swallow the whole world, and if it's a new or relatively new or maybe underdeveloped paradigm, that can be really hard. And I remember when the Haskell people hadn't figured out how to incorporate monads. It's like, oh, great language. How do you do input, output again? Things like that, right? And I feel like we're definitely in that pre-monad stage where we're trying to be a general language, but we just have no idea how to do a large variety of things that in traditional languages just people don't even think about. It's like, oh yeah, why are you even talking about this problem? It's not really a problem normally. So we're definitely in that domain. Another thought I had was there are languages like Lambda Prolog and 12 that look almost like sort of the relational programming languages that we want to use. Also, Coq kind of feels like this way, but like in Lambda Prolog, the Lambda Prolog book, if you read it, there's a interpreter written as a relation. And when I remember reading it, it's like, oh yes, great, this is awesome. And now they're going to run it backwards. Now they're going to do program synthesis. It's like, no, they didn't do anything. Why? Because they didn't have a search. They didn't have the constraints that they needed. So they got all the way up to doing it, but then they kind of either lack the secret sauce or lack the motivation to do so, or both, right? And so that's another thing I think is worth exploring. Nada Min has figured out how to generate quines in 12, for example. Okay, so 12 is a fine relational language in many ways. It's just lacking the sort of search we have and maybe lacking some of the constraints. So that might be an interesting thing to go back and revisit some of these systems that are almost exactly what you would hope for from a relational system, but for whatever reason, they didn't implement some of the things that we've found over the years to be really useful if you want to do, say, synthesis. And maybe there's a sweet spot there. Maybe we could hack 12. Maybe we could hack, Lambda Prolog or whatever, or Lambda Canron. Maybe Lambda Canron already supports this better than Lambda Prolog, but really try to push those angles as well. And then for Jeff, one thought that I had when Jeff was talking is, I've heard several people say this in the past that, relational programming, one thing that is interesting about it is it seems like it's a pretty good glue paradigm for tying together different types of computation, certainly for data things, because you have, SQL, flat files, graph databases, data log, there's a whole bunch of different things that you have to deal with if you're, say, dealing with semantic web and traditional SQL databases and modern graph databases and whatever, like we have to deal with on the biomedical data translator project, where we have all sorts of different biomedical data in a whole bunch of different formats. And right now what people do is they take all the data and they say, we're going to pick one format and one representation, and we'll shove it into that format or representation, whether or not that's sort of the natural way it should exist. Whereas I think in the sort of relational setting, at least with like a mega canron or kilocanron, we might be able to come up with something that has less of an impedance mismatch, where maybe we combine different types of relations with different degrees of power and so forth, and maybe keep more of the data in its original format, and we lose less of the kind of structure as we try to do the computation across different data bases and knowledge bases of different types. Okay. Let me look online. Okay, I think we're good there. Any other thoughts? Anyone who hasn't spoken who would like to share their ideas? Okay. It's time. Greg's going to come up finally. He's been marshaling his thoughts.
Hi, I'm Greg Rosenblatt. I work with Will at University of Alabama at Birmingham. I have some thoughts about, I guess, the role of mini-Cannerin in terms of pragmatic use cases. So I think that the right way, this is the way that I think about it at least. I think of mini-Cannerin in as sort of like two different components that work well together. So the part that I like most about mini-Cannerin is as Jason mentioned, the hackability, and as Will mentioned, that it's really good glue. So I like the idea of mini-Cannerin as a sort of central shared language in which you can describe lots of things. So basically, you can make statements of first-order logic in it, right? And I like the declarative aspect of that. What I don't necessarily like so much is the default search strategies of basic implementations. They're very good for lots of Jason, you're very amused. Okay, so they're very good for toy problems and for doing basic relational interpreter queries like finding clients. The basic interleaving search is very good for that. But in order to really put it to more practical use, you need to go beyond that. So I know Jeff was mentioning, for instance, the join order problem. That's not going to be solved automatically by the interleaving search. You need to build in a smarter system that can look at your constraints and say, okay, this is the right way to schedule them. This is what you were describing as this would be a query optimizer, right? And so that's the second aspect of mini-Cannerin, which is the operational semantics part. So we have the first part, which is a nice syntax for describing things that lots of different kinds of second semantic, operational semantics kinds of things can share. And as Will was talking about, you could potentially have many kinds of operational semantics depending on the exact structure of your problem. So some kinds of descriptions would be good to solve with like data log. Maybe you can write an efficient data log solver that can solve that portion, and maybe you have a more general backwards chaining semantics that leads down to that. So you might have backwards chaining up until a certain point where you see, okay, at the leaves of this search, we see a bunch of things that look like data log, and we'll apply a data log solver then. And so you want something more like an operational semantics that can change or adapt depending on what the current state of your search looks like. And in order to do this, I guess this is something that Lisa and I worked on a few years ago, which was a first order representation for the program, and which I saw Evan Donahue actually in his paper, he mentioned that he was building off of a first order representation as well. You can think of this as a defunctionalized representation of the search. So instead of using a higher order representation of conjunctions and disjunctions, the M plus and the bind, or is it append infinity and whatever terminology you use now. I like the M plus and bind. Anyway, instead of the higher order versions of those where you're locking a specific operational semantics in the form of scheme lambdas, you instead just say, okay, this is a disjunction or this is a conjunction, and you have a separate interpreter that can then inspect a program, and depending on how your interpreter is implemented, it can dispatch in different ways. So for instance, I was reading in Evan's paper that he actually uses multiple kinds of interpreters, which is really neat. So he has the main interpreter that does a normal kind of interleaving mini-Cannerin search over the program. But then for his lazy constraints, he actually uses a completely different interpreter that interprets disjunctions in a different way. I think that was the main distinction, so that he can achieve his laziness, and as well as figuring out what variables to attribute his lazy constraints to that are currently suspended. So that's I think the example that of something that the direction that we want to go in. So these kinds of different ways to interpret the same program structure. So we can build utilities that sort of do the simple things for the common kinds of program structure that is shared amongst lots of programs. So things like conjunctions and disjunctions and existential quantification, and off of these use different kinds of interpreters as like extensions that we can plug in at various points and say, I want to actually override the operational semantics at this point, when I recognize this pattern, or some other way to hook into it and say, I actually want to apply a different semantics now because I think that's going to be more effective. And when I say that things could be more effective, just based on my experience, I'm talking like billions of times more effective. And like even in Evan's paper, he was quoting performance, I believe, compared to the normal faster mini-cannon implementation of things like disequality constraints. If you do something more specialized for a certain kind of pattern, you get gazillions of orders of magnitude improvements. It's ridiculous. And in mini-cannon logic programming in general, when you're splitting the state of the world over and over and over and over again, little tiny improvements in overhead due to being slightly less stupid about basic patterns has enormous, you can gain enormous amounts by just eliminating little bits of unnecessary work at various points. And the only way you can really do this is to apply programmer domain knowledge based on specific patterns. So for instance, just another I guess anecdote for the relational interpreter that we did with Barliman. Most of those optimizations came just from being a little bit, not even a lot, just a little bit less stupid about the order in which we applied constraints. So, for instance, as something as simple as knowing that a variable, when I say variable, I mean a lexical variable in Scheme that's being interpreted by our interpreter, knowing that that piece of syntax is ground, it's a symbol, and our environment is ground, we might as well just look it up in the environment immediately and get that value rather than going through the normal mini-cannon search, which will continuously delay the search through that environment one binding at a time. That alone gets a large speed up, but even more so, doing something like function application, where you could evaluate the operator or the operands first, and which one you do has enormous consequences for how quickly you're going to be able to run your program forwards or backwards. So being able to inspect the current state, say, is the operator ground, are the operands ground, and based on that status, choose which one you try first. That's the difference between synthesizing a pen from scratch and sitting there for all of eternity and nothing happens. So so I guess my point is we want to do more of I guess a mix of homogeneity and heterogeneity, but depends on which perspective you're looking at mini-cannon from. So program representation-wise, homogeneity is great because we can all share a common language, but from a solver's point of view, we want a lot of heterogeneity. We want lots of different approaches to solving constraints. Best if it's informed by a programmer's domain knowledge. And I don't know a perfect way to express that in a program. Our solutions so far have been kind of ad hoc. You write an interpreter or multiple kinds of interpreters that interpret that language. So I don't know the nicest way to present this to a programmer who's programming in a possible megacanron or a kilocanron or whatever. I don't know what that will look like, but I just know that you will need some way for the programmer to be able to describe these things in the future, and I think that's the direction that we should be going in. All right. A secret third interpreter in Evan's implementation? Sorry, that does what? Prints debug traces. Okay, yeah, that's a great idea too. So I guess sort of related to that, Lisa and I did a neural mini cannon implementation once. That I guess was the thing that led to our first order representation implementation, which is where we can actually have some external agent in the loop, where you presented the current state of a mini cannon program, and it makes a choice about what. So it is the agent itself implements the search strategy. It says, I want to go down this branch. Let's try that. And then the mini cannon portion of it takes the choice, takes that step, and says, okay, here's the new state of the program. What do you want to do now? Or it'll say, unsatisfiable, try something else. And like Evan says, you could potentially do something similar to get you debug traces. I think that's also sort of related, where you can do these kinds of arbitrary introspections onto the program state. I think that's a great idea too. I'd love to see what Evan's implementation looks like, and I hope that's not secret in the GitHub repo that he presented, because I want to take a look at that. But yeah, so going beyond debug traces, debug interaction is also possible. I guess that was my point. So where you can have a programmer that actually interacts with the mini cannon system. Yeah, I guess another thing we were working on was a mini cannon profiler, which also uses that idea as well, where you can actually inspect the state of the program, as well as track. I guess this is another kind of tracing. You can track the contributions to your current state. By contributions, I mean the program points that have led you up to where you are, and by doing so, you can actually see which parts of the program are most implicated in successes or failures of different threads of the search. And by doing this and generating a heat map of your program, you can actually get an idea of how you might want to rewrite it. We might be able to write other kinds of interpreters that on the fly are doing using this for some kind of profile guided optimization style restructuring of the program on the fly. So you can imagine another agent that is watching this, they're consuming this heat map and saying, okay, let me reinterpret these parts of the program in this way and interleave the search in a different way, so that we can avoid all these this waterfall of failures, and hope to get more relevant answers coming through that, rather than a generated and test pattern that might be happening at the moment. All right, have I spoken enough? Does anyone else want to speak? Oh, great. All right, I ate it all up. Okay.
Good job, Greg. That's exactly what we were hoping for. Okay. Well, once more, I will plug the monthly Mini Canron seminar online that Kate runs. And so if you're interested in joining us for that, please let me know. Or let Kate know. And we're always looking for speakers willing to share their hacking and research and things like that in relational programming or Mini Canron or whatever. Thank you to everyone who attended in person and online. Thank you to the student volunteers, and thank you to the program committee, and thank you. Thank you to Nada Min, my co-host, who did a lot of the legwork. And I hope that we can continue meeting in person. It's great to be back in person again, talking about these things. And I hope we'll find great applications and we'll play around with megacanrons and nanocanrons and attocanrons and exacanrons and everything else. That would be great. All right. Thank you very much.